Artificial Intelligence and Robotics Engineering. Third semester. Let's explore together. Slide 20, Semester 3, Specialized Courses and Research. The third semester of the Master in Artificial Intelligence and Robotics Engineering program represents the culmination of progressive specialization, 6 advanced courses converging with rigorous research methodology to prepare students for original thesis work that demonstrates mastery through novel contribution rather than mere implementation. Unlike Semester 1's foundational breadth or Semester 2's integrative synthesis, Semester 3 demands focused depth in emerging frontiers where AI and robotics intersect with physical environments, immersive interfaces, and distributed intelligence. Courses deliberately selected not as isolated electives but as complementary specializations enabling students to develop distinctive expertise while maintaining systems-level understanding. Pattern recognition, AI.716, provides statistical backbone for uncertain perception. Internet of Things, AI.717, connects intelligent algorithms to physical sensor networks enabling smart environments. Virtual reality, AI.718, creates training platforms where reinforcement learning agents practice safely before physical deployment. Augmented reality, AI.719, blends digital intelligence with physical reality enabling spatial computing interfaces for human-robot collaboration. Research. Methodology, AI.720, transforms students from knowledge consumers into knowledge creators through systematic literature review, experimental design, and scholarly communication. Master thesis, AI.760, demands original contribution validated through implementation, analysis, and defense. These 6 components function as integrated ensemble where specialized technical depth enables meaningful research questions, research methodology ensures rigorous investigation, and thesis work synthesizes both into demonstrable mastery, rejecting artificial separation between theory and practice, by requiring thesis implementations that operate in realistic environments with measurable impact. Elective options, AI.721, AI.726, enable personalization within structured progression. Students selecting fuzzy logic and evolutionary computation develop expertise in optimization under uncertainty. Those selecting robotics perception and multi-agent systems focus on distributed autonomy. Those selecting cognitive science and big data analytics develop human-AI collaboration capabilities, each pathway feeding directly into thesis topics where specialized knowledge addresses genuine capability. Gaps rather than artificial academic exercises. This semester's distinctive value emerges through forced integration. Pattern recognition's probabilistic frameworks directly inform uncertainty quantification in thesis perception systems. IoT's edge computing constraints shape deployment architectures for thesis implementations. VR, AR interfaces enable novel evaluation methodologies for thesis human-robot interaction studies. Research methodology provides scholarly rigor ensuring thesis contributions advance field knowledge rather than merely demonstrating engineering competence. Industry relevance anchors specialization through advisory board input. Semiconductor manufacturers requested hardware AI optimization skills now addressed through IoT course emphasizing edge computing constraints. Automotive OEMs requested immersive simulation capabilities now embodied in VR course architecture where students build training environments for autonomous agents. Healthcare robotics firms requested spatial computing interfaces now integrated throughout AR curriculum with usability evaluation components. Research laboratories requested methodological rigor now formalized in dedicated research methodology course teaching systematic literature review, experimental design, and scholarly writing. This semester thus transforms students from system architects into innovation leaders, engineers who not only implement state-of-the-art systems but extend boundaries of what's possible through rigorous research grounded in specialized technical depth, ethical reflection, and human-centered design. Pattern recognition, AI.716, statistical foundations for uncertain environments. Pattern recognition moves beyond deterministic classification to probabilistic frameworks essential for robust perception under uncertainty, Bayesian decision theory, density estimation, and discriminant analysis providing mathematical machinery for quantifying confidence and managing risk in safety-critical applications. Bayesian classifiers compute posterior probabilities P, Cx, proportionality P, XC, P copyright symbol enabling calibrated confidence estimates essential for medical diagnostics, where 95% confidence triggers human review while 60% confidence demands additional tests. Stanford's diabetic retinopathy detector employs Bayesian calibration. Temperature scaling adjusts softmax outputs to match observed frequencies. System reduced false negatives by 23% by flagging low confidence predictions for ophthalmologist review, critical for preventing blindness from misdiagnoses. Gaussian mixture models, GMMs, represent complex distributions through weighted sums of Gaussians. Expectation maximization algorithm iteratively estimates component parameters maximizing likelihood. Soft clustering assigns probabilities of membership across clusters. Autonomous vehicles employ GMMs for road surface classification, modeling wet, dry, icy surfaces through spectral reflectance distributions. System achieves 94% accuracy distinguishing black ice from wet asphalt, critical for adaptive traction control where misclassification causes loss of vehicle control. Hidden Markov models, HUMS, model sequential data through latent state sequences. Forward-backward algorithm computes state probabilities. Viterbi algorithm finds most probable state sequence. Amazon's Alexa employs HUMS for speech recognition, modeling phoneme sequences with triphone context. Left, right neighboring phonemes. System achieves 95% word accuracy on noisy mobile recordings by capturing temporal dependencies invisible to frame-independent classifiers. Conditional random fields, CRFs, extend HUMS with undirected graphical models enabling global sequence optimization. Feature functions capture long-range dependencies, inference through belief propagation or Viterbi decoding. Surgical robots employ CRFs for tool tracking in laparoscopic video, modeling temporal consistency of instrument presence, absence across frames. System reduces tracking errors 37% versus frame-by-frame classification by leveraging surgical workflow constraints, e.g., scissors rarely appear without prior trocar insertion. These probabilistic frameworks transform perception from brittle pattern matching to risk-aware decision-making, essential for applications where uncertainty quantification determines safety margins, human oversight requirements, and fallback strategies under distributional shift. Internet of Things, AI.717, distributed intelligence across physical environments. Internet of Things bridges artificial intelligence with physical world through sensor networks and embedded intelligence, architectures where AI processes distributed sensor data enabling smart environments, industrial automation, and connected healthcare without centralized cloud dependency. Edge computing architectures distribute intelligence across device edge cloud continuum. Resource-constrained devices, ESP32 microcontrollers, perform simple filtering. Edge gateways, NVIDIA Jetson, execute complex inference. Cloud handles long-term analytics. John Deere's See and Spray employs edge computing. Camera-equipped tractors run lightweight CNNs on Jetson Xavier, identifying weeds in real time. Only summary statistics, weed density maps, transmitted to cloud, reducing bandwidth 99% while maintaining 99.2% weed kill rate, critical for rural farms with limited connectivity. Time series forecasting predicts future states from historical sensor streams. LSTMs capture long-term dependencies. Temporal convolutional networks, TCNs, enable parallel training with causal convolutions. NBEATS provides interpretable basis function decomposition. Siemens Predictive Maintenance employs TCNs analyzing vibration spectra from factory equipment, forecasting bearing failure 14 days in advance with 92% precision by modeling degradation trajectories. System reduced unplanned downtime 40% across 120 manufacturing plants by enabling scheduled replacements before catastrophic failure. Federated learning trains models across decentralized devices without centralizing sensitive data. Devices compute local updates on private data. Central server aggregates updates without accessing raw data. Google Keyboard's board employs federated learning, personalized word prediction models trained across 50 million devices with raw typing data never leaving phones. System improved next word prediction accuracy 18% while complying with GDPR data localization requirements across 150+ jurisdictions, critical for global deployment. Event-driven architectures process asynchronous sensor events rather than fixed-rate sampling. Complex event processing, CEP, engines detect patterns across event streams, e.g., temperature spike followed by pressure drop within 5 seconds indicates imminent failure. Oil rig monitoring systems employ CEP analyzing 10,000+ sensor streams, detecting precursor patterns to blow out events 22 minutes before traditional threshold-based alarms. System prevented 3 catastrophic failures in 2023 by enabling preemptive shutdown procedures. Security architectures protect distributed systems through layered defenses, hardware security modules, HSMs, storing cryptographic keys, lightweight encryption, AES, 128, CTR, for constrained devices, blockchain-based attestation verifying device integrity. Smart grid operators employ layered security, HSMs in substation controllers prevent firmware tampering, AES, 128 encrypts meter readings, blockchain logs detect anomalous access patterns. System maintained 99.999% uptime during 2023 cyberattack campaign targeting critical infrastructure. These IoT capabilities transform isolated sensors into intelligent ecosystems, enabling real-time decision-making at source, preserving privacy through decentralized processing, and creating resilient architectures where single device failures don't compromise system-wide intelligence essential for smart cities, precision agriculture, and industrial automation. Virtual reality, AI.718, immersive training platforms for embodied AI. Virtual reality creates photorealistic simulated environments where intelligent agents train safely before physical deployment, transforming VR from entertainment medium into engineering infrastructure for sample-efficient learning, failure mode exploration, and human-robot collaboration design. Physics-based rendering generates sensor-accurate synthetic data. NVIDIA Omniverse replicates automotive camera spectral response, 400 to 1100 nanometers, LiDAR pulse characteristics, 905 nanometers wavelength, 0.1 degrees angular resolution, and radar Doppler effects enabling perception systems to train on rare edge cases impossible to collect physically. Waymo employs VR training generating 10 million photorealistic driving miles daily, simulating phantom jaywalkers emerging from between double-parked cars at night, emergency vehicles with unusual light patterns, construction zones with temporary signage. Perception networks trained exclusively in VR achieved 94% transfer accuracy to physical sensors versus 67% for non-physical-based simulation critical for safe deployment without dangerous physical testing. Embodied AI training leverages VR safety for high-risk exploration. Reinforcement learning agents practice dynamic locomotion, backflips, gap jumps, with unlimited falls. Manipulation policies learn contact-rich tasks, inserting pegs into holes, without damaging physical hardware. Boston Dynamics trained Atlas robots park our policy entirely in VR, 200 years of simulated experience learning dynamic balance through domain randomization, varying friction coefficients 0.3 to 1.2, mass distributions plus or minus 30%, sensor noise plus or minus 15%. Sim-to-real transfer achieved 92% success rate on physical robot by exposing policies to visual and dynamic diversity impossible in physical environments. Teleoperation interfaces use VR for intuitive robot control. Operators wear headsets seeing robots' first-person view with virtual control handles mapped to robot arms. Haptic feedback conveys contact forces enabling delicate manipulation. NASA's Robonaut 2 teleoperation employs VR interface. Astronauts on ISS control robot performing external maintenance through VR headset with force feedback gloves. System reduced task completion time 47% versus traditional joystick interface by leveraging spatial intuition critical for complex tasks in microgravity where physical access proves impossible. Human-robot collaboration design employs VR prototyping, testing interaction concepts before physical implementation, measuring human trust, cognitive load, and safety perceptions in controlled environments. BMW's HRI lab employs VR prototyping collaborative assembly scenarios, testing 50-plus interaction variants, handover distances, motion speeds, signaling methods, in 2 weeks versus 6 months for physical prototyping. VR testing identified optimal handover distance, 60 centimeters, reducing errors 37% versus intuitive guesses critical for production deployment. These VR applications transform simulation from visualization tool into training infrastructure, accelerating AI development cycles by orders of magnitude, enabling safe exploration of failure modes, and reducing physical testing costs while maintaining fidelity sufficient for real-world transfer essential for safety-critical autonomy where rare edge cases determine system reliability. Augmented reality, AI.719, spatial computing interfaces for human-robot collaboration. Augmented reality blends digital intelligence with physical reality through spatial computing, enabling robots to communicate intentions, humans to understand system states, and collaborative tasks to unfold through context-aware overlays that enhance rather than replace physical interaction. Spatial mapping reconstructs 3D environment geometry in real time. Microsoft HoloLens 2 employs depth sensing and SLAM, creating mesh representations with 2 mm accuracy at 3 meters. Persistent world anchors maintain hologram positions across sessions, enabling multi-user collaboration. Boeing Aircraft Assembly employs spatial mapping. Technicians see holographic wire routing diagrams overlaid on physical fuselage with 2 mm accuracy. System reduced wiring errors 47% and assembly time 30% by eliminating constant reference to paper manuals critical for complex assemblies with 1.5 million fasteners per aircraft. Intention visualization communicates robot plans before execution, projecting planned trajectories as holographic paths, highlighting uncertainty bounds as translucent volumes, displaying tool affordances on physical objects. Boston Dynamics Spot employs AR intention visualization during facility inspection. Holographic path shows planned route 5 seconds ahead. Red zones highlight areas requiring human verification. System reduced human intervention requests 63% by making robot intentions transparent versus opaque operation where humans couldn't anticipate movements. Collaborative assembly interfaces guide human-robot teamwork. Holographic fixtures showing optimal hand positions. Virtual jigs constraining tool motion to safe paths, real-time feedback on task progress. Airbus employs AR collaborative assembly. Humans and robots jointly position 12-meter wing spars with sub-millimeter alignment accuracy. AR interface shows robots' planned motion path, humans' optimal hand position, and real-time alignment error. System reduced assembly time 50% while maintaining 0.2 mm tolerance, critical for aerodynamic performance. Maintenance and repair guidance overlays procedural instructions directly onto equipment, highlighting components requiring attention, animating disassembly sequences, displaying real-time sensor data on physical locations. Siemens Industrial Maintenance employs AR guidance. Technicians see holographic arrows pointing to faulty components, step-by-step animations for replacement procedures, and live thermal readings overlaid on motors. System reduced mean time to repair 42% and training time for new technicians 68%, critical for minimizing production downtime, costing $220,000 per hour in automotive plants. Medical robotics employs AR for surgical planning and guidance. Preoperative CT, MRI scans visualized as holograms overlaid on patient anatomy, critical structures, nerves, blood vessels, highlighted during procedures, instrument trajectories previewed before execution. Johns Hopkins Augmented Reality Surgery System employs HoloLens 2. Surgeons see tumor margins as holographic contours overlaid on physical tissue during resection. System achieved 3 mm resection accuracy versus 8 mm for traditional methods, reducing positive margin rates 27%, critical for cancer outcomes where incomplete resection causes recurrence. These AR interfaces transform human-robot interaction from abstract command sequences to spatially intuitive collaboration, leveraging human spatial reasoning and motor skills while augmenting with AI capabilities essential for complex tasks requiring both human judgment and machine precision, where transparency about robot intentions builds trust and prevents accidents. Research methodology, AI.720, from knowledge consumption to knowledge creation. Research methodology transforms students from consumers of existing knowledge into creators of original contributions, cultivating capacity to identify unsolved problems, design rigorous investigations, navigate uncertainty, validate claims through reproducible methodology, and communicate findings with scholarly precision. Literature review moves beyond superficial cataloging to strategic mapping, citation network analysis tracing intellectual lineages through forward, backward citation tracking, keyword co-occurrence analysis identifying emerging research clusters, systematic review protocols, PRISMA, ensuring comprehensive coverage without selection bias. Thesis students employ systematic review for surgical robotics literature, analyzing 1,247 papers through PRISMA protocol, identifying 47 studies meeting inclusion criteria. Citation network revealed 3 dominant paradigms: teleoperation, shared control, autonomous subtasks, with critical gap in haptic feedback for soft tissue manipulation, directly informing thesis topic on tactile augmentation for robotic suturing. Research design addresses fundamental question: what evidence would convincingly demonstrate claimed contribution, distinguishing exploratory research, discovering patterns without pre-specified expectations, from confirmatory research, testing specific hypotheses with pre-registered analysis plans, specifying directional versus non-directional hypotheses where appropriate, ensuring hypotheses derive logically from problem analysis rather than post-hoc rationalization. Human-robot interaction thesis employs mixed methods design, quantitative experiment measuring task completion time and NASA TLX workload across 3 interaction modalities, qualitative interviews exploring user trust formation, triangulation revealing that quantitative metrics showed no difference but qualitative data revealed critical trust calibration failures invisible to metrics alone, demonstrating necessity of multi-method approaches for complex phenomena. Statistical analysis transforms raw data into credible evidence, power analysis determining minimum sample size to detect effects of interest with specified type 1-2 error rates, effect size reporting complementing p-values with practical significance, confidence intervals expressing precision around point estimates, multiple comparisons correction, Bonferroni, Benjamin Hochberg, controlling false discovery rates. Medical imaging thesis employs rigorous statistical validation, power analysis determined 85 subjects needed to detect 10% accuracy improvement with 80% power, effect sizes reported as Cohen's d with 95% confidence intervals. Benjamin Hochberg correction-controlled FDR at 5% across 12 diagnostic metrics. Results showed 8.7%, 6.2%, 11.1% improvement, d equals 0.63, statistically and clinically significant critical for FDA clearance pathway. Ethical research practice permeates entire methodology, not as compliance hurdle but as foundational principle. Data management plans ensuring integrity through version control and metadata documentation, authorship guidelines clarifying contribution expectations, conflict of interest disclosure protocols, dual-use awareness examining how beneficial technologies might enable harm. Thesis students receive IRB training, preparing protocols for human subject research, designing informed consent processes respecting participant autonomy, implementing data anonymization protecting privacy, conducting risk-benefit analyses justifying research procedures, ensuring ethical rigor matches technical excellence essential for responsible innovation. Scholarly communication transforms private insights into public knowledge, IMRAD structure, introduction, methods, results, discussion, enabling independent verification, argumentation moving beyond description to persuasion through evidence, figure design communicating complex information efficiently, citation practices acknowledging intellectual debt accurately. Thesis writing workshops employ iterative practice, structured outlines. Receiving feedback before drafting, peer review workshops teaching constructive critique skills, revision cycles emphasizing improvement over perfection, exposure to exemplary papers in target venues revealing field-specific conventions beyond generic templates, transforming writing from solitary struggle into collaborative scholarly practice essential for publication and professional credibility. Master Thesis, AI.760, Capstone Integration of Knowledge, Skills, and Original Contribution. Their master thesis constitutes integrative demonstration where students synthesize 3 semesters of learning into original contribution advancing AI and robotics knowledge while proving capacity for independent research, transforming students from guided learners executing prescribed assignments into autonomous investigators identifying unsolved problems, designing novel methodologies, implementing solutions, analyzing results with intellectual honesty, and communicating findings with scholarly precision. Thesis timeline deliberately spans semester 3 with structured milestones preventing procrastination while accommodating research unpredictability, weeks 1 to 2, topic selection with faculty advisor approval ensuring scope appropriate for master's level, neither trivial nor impossibly ambitious, weeks 3 to 6. Comprehensive literature review producing annotated bibliography of 30 to 50 seminal and recent papers establishing research gap with precise statement of how proposed work extends beyond existing solutions, weeks 7 to 10, research design developing detailed methodology with validation protocols including appropriate baselines, statistical power analysis for human subject studies, metrics alignment with claimed contributions, weeks 11 to 14, pilot implementation testing feasibility and identifying fatal flaws before full commitment, weeks 15 to 20, full implementation executing methodology at scale with systematic data collection or algorithm training, weeks 21 to 24, analysis completing. statistical evaluation, visualization, and interpretation with honest acknowledgement of limitations and unexpected findings, weeks 25 to 28, writing producing complete draft with IMRAD structure meeting academic publication standards, weeks 29 to 30, revision incorporating faculty feedback and preparing defense presentation, subsequent weeks, formal defense before committee of 3 faculty members including primary advisor and 2 readers from complementary domains. This timeline ensures thesis represents genuine contribution rather than hastily assembled project. Students experience full research lifecycle including inevitable challenges, pilot studies revealing methodological flaws requiring redesign, data collection encountering unexpected confounds necessitating protocol adjustments, algorithm implementations failing to replicate published results demanding meticulous debugging, computational resources constraining experiment scale requiring clever approximations preserving validity. Faculty mentorship guides adaptation without compromising rigor, weekly meetings during active research phases providing timely feedback, structured milestone reviews ensuring progress without micromanagement, access to computational resources, GPU clusters, robotics platforms, human subject participant pools, removing logistical barriers, connections to domain experts for specialized consultation when needed. Thesis topics span spectrum from theoretical to applied while maintaining research contribution requirement, algorithmic innovations developing novel architectures or training procedures with empirical validation against baselines, e.g., attention mechanisms for long-horizon reinforcement learning in sparse reward environments, systems integration demonstrating capabilities impossible with existing components through thoughtful orchestration, e.g., multimodal perception fusion for robust manipulation in cluttered environments, empirical studies characterizing performance boundaries under realistic conditions absent from benchmark datasets, e.g., degradation analysis of vision-based navigation under adverse weather conditions, human subject evaluations quantifying usability, trust, and collaboration quality in human AI teams, e.g., trust calibration in human robot teams through transparent failure communication, longitudinal deployments observing real-world adaptation. Revealing challenges invisible in laboratory settings, e.g., field deployment of agricultural robots, adaptation challenges across seasonal variability. All topics must satisfy contribution criteria, novelty extending beyond existing solutions rather than mere implementation of published methods, significance addressing genuine problem rather than artificial academic exercise, feasibility completable within resource constraints, time, computation, data access, rigor employing appropriate methodology with valid evaluation, ethics addressing societal implications and participant protections. Thesis evaluation employs academic peer review standards rather than simplistic grading, committee assesses originality, does work extend boundaries of existing knowledge, rigor, are claims supported by appropriate evidence with proper controls and statistical analysis, significance, does problem matter to field or society beyond academic exercise, communication, is contribution articulated with precision enabling independent verification, and integration, does work synthesize concepts from multiple courses demonstrating systems-level understanding. Defense presentation requires students to articulate contribution clearly under questioning, respond thoughtfully to critique distinguishing valid concerns from subjective preferences, demonstrate mastery not merely of narrow topic but of connections to broader AI and robotics principles, and acknowledge limitations without defensiveness while maintaining confidence in core contributions. Successful thesis completion signifies more than degree conferral, it demonstrates capacity to identify unsolved problems, design rigorous solutions, and contribute knowledge-advancing field with scholarly integrity. Graduates often publish thesis work in conferences, ICRA, IROS, RSS, NeurIPS workshops, or journals launching research careers in academia, industry research labs, or entrepreneurial ventures where original thinking drives innovation. Thesis also serves professional differentiation, unlike certificate programs or coursework-only master's degrees where credentials signal completion of prescribed curriculum. Thesis-based degree provides concrete evidence of research capacity through publicly accessible document demonstrating sustained intellectual engagement with unsolved problem. Employers value this evidence particularly for research engineer, algorithm developer, and technical leadership roles where capacity to navigate uncertainty and generate novel solutions proves essential. Thesis process also cultivates professional practices essential beyond academia, project Management through milestone adherence, technical communication through writing and presentation, collaborative skills through advisor interactions and peer feedback, resilience through navigating research setbacks, intellectual honesty through limitation acknowledgement. These practices transfer directly to industry R&D environments where engineers must propose projects, secure resources, execute with rigor, communicate progress, and adapt to challenges. Thesis provides authentic apprenticeship for these professional realities. Support infrastructure ensures equitable access to thesis success regardless of prior research experience. Research methodology course AI.720 provides explicit training in literature review techniques, research design principles, statistical analysis methods, academic writing standards, and ethics compliance. Writing Center offers discipline-specific feedback on drafts addressing argument structure, precision, and scholarly conventions, statistical consulting available for complex analysis. Designs, computational resources allocated equitably ensuring all students access necessary hardware without financial barriers, human subject research support navigating IRB protocols and participant recruitment, open office hours with multiple faculty beyond primary advisor providing diverse perspectives on research challenges. This infrastructure recognizes thesis represents significant challenge particularly for career changers or students from educational systems emphasizing examination over research. Support systems provide scaffolding enabling success without diluting rigor, ensuring thesis remains meaningful demonstration of mastery rather than gatekeeping barrier excluding capable students lacking prior research exposure. Thesis ultimately serves transformative purpose, converting students from consumers of knowledge who implement existing techniques into creators of knowledge who extend boundaries of what's possible through rigorous inquiry grounded in methodological discipline, ethical reflection, and genuine curiosity about unsolved problems. This transformation defines programs' distinctive value. Graduates enter workforce not merely as skilled engineers but as innovators capable of identifying capability gaps, designing investigations to address them, and contributing solutions advancing field while serving human needs. The thesis document itself becomes professional artifact, tangible evidence of sustained intellectual engagement with complex problem, publicly accessible demonstration of research capacity, foundation for future publications or patent applications, and concrete talking point during job interviews where candidates must articulate meaningful projects beyond coursework assignments. In competitive job markets where technical skills increasingly commoditized through online courses and bootcamps, thesis-based master's degree provides distinctive credential signaling not merely knowledge acquisition but capacity for original contribution, capacity increasingly valued as AI and robotics fields mature beyond initial hype cycles toward sustainable innovation grounded in rigorous research and thoughtful deployment. Elective integration with specialized courses and thesis work. Elective options enable personalization within structured progression. 6 specialized electives, AI.721, AI.726, allowing students to develop distinctive expertise aligned with career objectives while maintaining foundation in core AI and robotics principles. AI.721 Fuzzy Logic provides mathematical framework for approximate reasoning under uncertainty where binary true, false logic proves insufficient. Membership functions representing linguistic variables, warm, tall, fast, as continuous truth values between 0 and 1. Fuzzy inference systems mapping input membership degrees through rule bases to output membership degrees. Defuzzification strategies converting fuzzy outputs to crisp actions. Students implementing fuzzy controllers for robotic platforms, designing rule bases where linguistic variables, close, approaching fast, map to velocity adjustments, tuning membership functions through iterative testing rather than analytical derivation, comparing fuzzy control performance against PID controllers under model uncertainty. Analyzing stability properties through Lyapunov methods adapted for fuzzy systems. This elective proves valuable for students pursuing careers in industrial automation, consumer robotics, or any domain where precise mathematical models prove unavailable but reliable control remains essential. AI.722 Evolutionary computation explores nature-inspired optimization algorithms where gradient information proves unavailable or misleading. Genetic algorithms encoding candidate solutions as chromosomes undergoing selection, crossover, and mutation, evolutionary strategies employing real-valued vectors with self-adapting mutation parameters, genetic programming evolving executable programs through tree-structured representations. Students implement these algorithms solving problems where gradient descent fails, non-differentiable objective functions like neural architecture search where fitness evaluated through training rather than analytical gradient, multimodal landscapes with numerous local optima where gradient methods converge prematurely, black box optimization where function evaluations available but derivatives inaccessible. Comparative studies evaluate algorithm performance across problem classes, measuring convergence speed, solution quality, robustness to noise, scalability with problem dimensionality, developing intuition for when evolutionary approaches outperform gradient-based methods and when hybrid strategies combining both prove optimal. This elective proves valuable for students pursuing research careers, algorithm development roles, or any domain requiring optimization under uncertainty or non-differentiability. AI.723 Robotics Perception extends computer vision foundations into multimodal sensor fusion essential for robust autonomy under real-world constraints. Students explore heterogeneous sensor integration combining cameras, rich appearance but lighting dependent, LiDAR, precise geometry but sparse at distance, radar, weather penetrating but low resolution, ultrasonic, short-range proximity, and tactile sensors, contact forces, developing fusion architectures at multiple levels, raw data fusion. Aligning measurements in common coordinate frames, feature-level fusion combining extracted descriptors before classification, decision-level fusion combining classifier outputs through voting or Bayesian integration. Students implement perception pipelines for specific challenges, object detection under adverse weather where camera performance degrades but radar maintains functionality, semantic segmentation incorporating geometric constraints from LiDAR improving boundary accuracy, visual inertial odometry fusing camera and IMU data for robust localization when visual features scarce, tactile visual fusion where touch refines uncertain visual hypotheses during manipulation. Advanced topics include active perception, robots controlling sensors to reduce uncertainty through viewpoint planning, focus adjustment, or illumination control. Lifelong learning where perception systems adapt to environmental changes without catastrophic forgetting, uncertainty quantification providing calibrated confidence estimates essential for safety-critical decisions, domain adaptation transferring perception models trained in simulation to physical deployment without extensive relabeling. Students implement complete perception stacks for mobile manipulation platforms, detecting objects on cluttered tables under variable lighting, estimating 6D poses for grasping, segmenting scenes into manipulable versus fixed elements, predicting object dynamics under interaction forces. This elective proves essential for students pursuing careers in autonomous vehicles, field robotics, or any domain requiring robust perception under unstructured conditions where single-sensor approaches prove insufficient. AI.724 Multi-agent systems addresses coordination challenges where single-agent optimization proves inadequate for collective intelligence. Students explore distributed problem-solving where agents with partial information must collaborate toward shared goals. Game-theoretic frameworks modeling strategic interaction where agents pursue individual utilities potentially conflicting with collective welfare. Consensus algorithms enabling distributed agreement without central coordination. Swarm. Intelligence inspired by biological collectives achieving complex behaviors through simple local rules, communication protocols balancing information sharing against bandwidth constraints and privacy considerations. Students implement multi-agent scenarios, cooperative navigation where robots coordinate paths avoiding deadlock in constrained environments, distributed sensing where agents allocate coverage responsibilities maximizing information gain, adversarial settings where agents compete for resources requiring strategic reasoning about opponents' intentions, human agent teams where AI agents must understand human teammates' capabilities and intentions to provide effective support. Advanced topics include emergent communication, agents developing signaling protocols through reinforcement learning when pre-specified languages unavailable, credit assignment in cooperative settings where team rewards must be allocated to individual contributions, robustness to agent failures requiring graceful degradation without central coordinator, scalability challenges as agent count grows requiring hierarchical or modular architectures. Students develop systems where multiple robots collaboratively transport large objects requiring force coordination, where drone swarms perform area coverage with dynamic task allocation, where autonomous vehicles negotiate merges without centralized traffic control. This elective proves valuable for students pursuing careers in swarm robotics, distributed AI, autonomous vehicle coordination, or any domain where intelligence emerges from interaction rather than residing in individual agents. AI.725 Cognitive science bridges artificial and biological intelligence through interdisciplinary study of human cognition and its computational models. Students explore perception mechanisms revealing why biological vision outperforms artificial systems in certain contexts, robustness to occlusion, rapid scene understanding, attentional selection, memory systems distinguishing episodic, specific experiences, semantic, general knowledge, and procedural skills, forms informing artificial memory architectures, decision-making under uncertainty revealing biases and heuristics humans employ when optimal computation proves intractable, social cognition enabling theory of mind, inferring others' beliefs, desires, and intentions essential for human-robot collaboration. Students implement cognitive architectures inspired by neuroscience, ACTR modeling declarative and procedural memory interacting during problem-solving, SOR employing production rules and working memory for goal-directed behavior, Clarion distinguishing implicit and explicit learning processes, predictive coding. Frameworks unifying perception, action, and learning through hierarchical prediction error minimization. Applications span human-like AI where systems exhibit cognitive plausibility beyond behavioral mimicry, cognitive robotics where robots employ human-inspired strategies for exploration, tool use, and social learning, brain-computer interfaces translating neural activity into control signals informed by cognitive models, adaptive interfaces personalizing interaction based on cognitive load estimates from physiological signals. Students conduct comparative studies, implementing navigation strategies inspired by rodent hippocampal place cells versus conventional SLAM, developing manipulation policies incorporating human motor control principles like minimum jerk trajectories, designing language interfaces respecting human working memory constraints through incremental grounding. This elective proves valuable for students pursuing careers in human-robot interaction, cognitive architectures, neuro-inspired AI, or any domain where understanding biological intelligence informs artificial system design. AI.726 Big Data Analytics addresses scalable processing of massive datasets generated by intelligent systems. Students explore distributed computing frameworks, Apache Spark, Dask, enabling parallel processing across clusters, stream processing architectures, Apache Kafka, Flink, handling real-time data flows from sensor networks, data lake architectures organizing heterogeneous data types without rigid schema constraints, feature stores managing consistent feature computation across training, and inference pipelines, MLOps practices automating model deployment, monitoring, and retraining at scale. Students implement analytics pipelines processing terabytes of sensor data from fleets of autonomous vehicles, detecting rare edge cases requiring human review, identifying temporal patterns revealing component degradation before failure, correlating environmental conditions with perception performance to define operational design domains, generating synthetic data through simulation conditioned on real-world distributions to augment training sets. Advanced topics include privacy-preserving analytics, federated learning training models across decentralized devices without centralizing sensitive data, differential privacy adding calibrated noise to query results guaranteeing statistical indistinguishability, secure multi-party computation enabling joint analysis without revealing raw inputs. Students develop systems where edge devices perform local processing reducing bandwidth requirements while cloud platforms aggregate insights across fleet, where anomaly detection identifies novel scenarios requiring model updates, where concept drift detection triggers retraining when data distributions shift. This elective proves essential for students pursuing careers in AI infrastructure, MLOps engineering, fleet learning systems, or any domain where intelligence emerges from data at scale rather than individual algorithmic breakthroughs. Elective selection guidance ensures informed choices aligned with career objectives. Academic advisors conduct structured consultations mapping student interests to appropriate pathways. Students interested in industrial automation guided toward fuzzy logic and control systems integration, those pursuing research careers directed toward evolutionary computation and cognitive science for theoretical depth, autonomous vehicle aspirants steered toward robotics perception and multi-agent systems. Human-robot interaction specialists encouraged toward cognitive science and HRI core course integration, infrastructure engineers pointed toward big data analytics and IoT specialization. This guidance prevents random selection while preserving student agency. Advisors present options with concrete career mappings rather than prescribing single path, enabling informed decisions respecting individual goals and constraints. Electives also enable adaptation to emerging frontiers without curriculum overhaul. When foundation models emerged as field-shifting development, students combined deep learning core course with big data analytics elective to explore large-scale pre-training. When embodied AI gained prominence, students integrated robotics core courses with cognitive science elective to investigate physical grounding of representations. When neurosymbolic integration attracted attention, students combined machine learning foundations with cognitive science perspectives on symbolic reasoning. This flexibility ensures curriculum remains relevant amid rapid field evolution while maintaining stable core sequence, providing timeless foundations. Elective assessment emphasizes integration rather than isolation. Students cannot treat electives as disconnected modules but must demonstrate connections to core sequence through capstone projects or thesis work. Fuzzy logic students implement controllers complementing PID approaches from control systems course. Evolutionary computation students optimize hyperparameters for deep learning models developed in core courses. Robotics perception students enhance autonomous systems projects with multimodal fusion. Multi-agent systems students extend reinforcement learning implementations to cooperative settings. Cognitive science students design human-robot interaction interfaces informed by cognitive principles. Big data analytics students scale machine learning pipelines to fleet-level deployment. This integration requirement ensures electives deepen rather than fragment expertise. Students develop distinctive specialization while maintaining systems-level understanding of how specialized components function within complete intelligent systems. Elective options ultimately serve dual purpose, enabling personalization, accommodating diverse career aspirations and intellectual interests while maintaining cohort cohesion around shared core foundations, producing graduates who share common vocabulary and conceptual framework, enabling collaboration across specializations while possessing distinctive expertise, differentiating them in competitive job markets. This balance between standardization and personalization defines programs' distinctive value. Students graduate not as interchangeable generalists nor as isolated specialists but as T-shaped professionals with broad foundational competence and deep specialized expertise, positioned to lead innovation at integration boundaries where AI and robotics converge. Slide 21, AI.716, Pattern Recognition. Pattern recognition transforms raw sensor data into meaningful interpretations through statistical frameworks that quantify uncertainty, distinguish signal from noise, and generalize across variations, enabling machines to identify objects despite viewpoint changes, recognize speech amid background noise, and detect anomalies in sensor streams where human inspection proves impossible at scale. Unlike deterministic rule-based systems that fail when inputs deviate from expected patterns, probabilistic pattern recognition embraces uncertainty as fundamental reality, modeling observations as random variables drawn from underlying distributions where classification decisions balance error costs against confidence levels. Medical imaging exemplifies this necessity. Diabetic retinopathy detection requires distinguishing microaneurysms, tiny red dots indicating disease, from harmless retinal artifacts under variable lighting, focus, and patient eye conditions. Rule-based systems fail catastrophically when artifacts mimic pathology, while Bayesian classifiers compute posterior probabilities p, disease image, equals p, image disease, p, image, enabling calibrated confidence estimates that trigger human review when uncertainty exceeds thresholds. Google Health System reduced false negatives by 23% by flagging low confidence predictions for ophthalmologist verification, preventing blindness from misdiagnoses while maintaining 94% automation rate. This statistical foundation distinguishes pattern recognition from mere classification. It provides mathematical machinery for quantifying confidence, managing risk, and making optimal decisions under uncertainty, essential for safety-critical applications where binary yes/no outputs prove dangerously inadequate. Bayesian decision theory establishes optimal decision framework under uncertainty, minimizing expected risk through posterior probability computation and cost-sensitive action selection. Fundamental equation P, X, equals P, X, P, X, combines likelihood P, X, probability of observing X given class, prior P, class prevalence before observation, and evidence P, X, total probability of observation, to compute posterior P, X, updated belief after observation. Decision rule selects action alpha, minimizing conditional risk R, alpha X, equals lambda, alpha, P, X, where lambda, alpha, represents loss from choosing alpha when true state. Real-world medical diagnosis illustrates cost asymmetry. False negative, missing cancer, carries loss lambda equals 1000, patient death. False positive, unnecessary biopsy, carries loss lambda equals 10, patient anxiety. Procedure cost, optimal decision threshold shifts from 50% probability to 99% probability favoring sensitivity over specificity. Stanford's lung cancer detector employs cost-sensitive thresholds achieving 98.7% sensitivity, catching nearly all cancers, at 89% specificity, acceptable false positive rate, versus 92% sensitivity for equal error threshold, directly saving lives through mathematically optimal risk balancing. Minimum error rate classification emerges as special case where lambda equals 0 if I equals j else 1. Decision rule selects class maximizing posterior probability p, x. Autonomous vehicles employ minimum error classification for traffic sign recognition, computing p, stop_sign image, versus p, speed_limit image, through CNN softmax outputs. System achieves 99.97% accuracy on German TSRB benchmark by maximizing posterior under equal misclassification costs where confusing signs carry similar safety risk. Reject options handle high uncertainty cases, declaring don't know when max p, x, theta where theta rejection threshold. Amazon warehouse robots employ reject options for item identification, when confidence less than 95% on bin contents. Robot requests human verification rather than risking missorting. System reduced sorting errors 63% versus forced classification while maintaining 92% automation rate by strategically offloading ambiguous cases. These Bayesian principles transform pattern recognition from brittle pattern matching to risk-aware decision-making, essential for applications where uncertainty quantification determines safety margins, human oversight requirements, and fallback strategies under distributional shift. Parametric methods assume data distributions follow specific functional forms, typically Gaussian, normal, distributions characterized by mean vector mu and covariance matrix sigma enabling closed-form solutions for optimal classifiers. Gaussian discriminant analysis computes discriminant functions g, x, equals 1/2, x, to the power of 1, x, 1/2 ln plus ln p, where decision boundary g, x, equals g, x, defines optimal separation surface. Homoscedastic case, equals sigma, yields linear decision boundaries. Fisher's linear discriminant analysis, LDA, finds projection W maximizing between class variance, B within class variance ratio J, W, equals WSW, WSW where SB between class scatter, S within class scatter. Industrial quality control employs LDA for defect classification, measuring 20 spectral features from semiconductor wafers. LDA projects to 1D discriminant where defective, non-defective clusters separate with 99.3% accuracy. System inspects 200 parts minute on production line, reducing field failures 76% while eliminating human inspector fatigue-related errors. Heteroscedastic case, not equal to, yields quadratic boundaries. Quadratic discriminant analysis, QDA, maintains full covariance modeling enabling curved decision surfaces essential for overlapping distributions. Financial fraud detection employs QDA analyzing transaction features, amount, location entropy, velocity. Legitimate transactions form compact cluster, low variance, fraud forms diffuse cluster, high variance due to diverse attack patterns. QDA's quadratic boundaries achieve 92% fraud detection versus 84% for LDA by capturing distribution shape differences critical for distinguishing sophisticated attacks from normal outliers. Mixture models extend parametric flexibility. Gaussian mixture models, GMMs, represent complex distributions as weighted sums, X, where mixing coefficients. Expectation maximization, EM, algorithm iteratively estimates parameters. E-step computes posterior responsibilities gamma, Z, equals, X, X, M-step updates parameters equals, Z, X, Z, equals, Z, X, X, Z, equals, Z, N. Autonomous vehicles employ GMMs for road surface classification, modeling wet, dry, icy surfaces through spectral reflectance distributions from camera, LiDAR fusion. Three-component GMM achieves 94% accuracy distinguishing black ice, low reflectance, high smoothness, from wet asphalt, moderate reflectance, medium smoothness, critical for adaptive traction control where misclassification causes loss of vehicle control. Model selection determines optimal complexity. Bayesian Information Criterion, BIC, equals -2 ln L plus K ln N penalizes parameters K to prevent overfitting. Akaike Information Criterion, AIC, equals -2 ln L plus 2K favors predictive accuracy over true model recovery. Speech recognition systems employ BIC for phoneme modeling, selecting 8 to 16 Gaussian components per phoneme state balancing accuracy against computational cost. System achieves 95% word accuracy on noisy mobile recordings by avoiding underfitting, too few components, and overfitting, too many components capturing noise. These parametric methods provide interpretable, computationally efficient classifiers when distributional assumptions hold, enabling real-time operation on resource-constrained platforms while maintaining statistical optimality under model correctness. Non-parametric methods make minimal distributional assumptions, estimating densities and decision boundaries directly from data through local neighborhood analysis essential when parametric forms prove inadequate for complex real-world distributions. K-nearest neighbors, KNN, classifies query X by majority vote among K closest training examples, distance metric D, X, X, typically Euclidean XX or Mahalanobis, XX, to the power of 1, XX, accounting for feature correlations. Optimal K balances bias variance trade-off, small k, K equals 1, yields low bias but high variance, sensitive to noise, large K yields high bias but low variance, oversmoothing boundaries. Retail recommendation systems employ KNN with K equals 50, computing product similarity through cosine distance on purchase history vectors. System achieves 89% click-through rate by capturing nuanced preferences. Customers buying organic baby food also purchase eco-friendly diapers, without assuming distributional forms impossible to specify for complex human behavior. Cursive dimensionality challenges KNN in high-dimensional spaces. Distance concentration causes all pairwise distances to converge, making nearest neighbors meaningless. Solution employs dimensionality reduction, PCA, before KNN or distance metrics emphasizing relevant features. Genomic classification employs PCA plus KNN, reducing 20,000 gene expression features to 50 principal components capturing 85% variance. KNN with K equals 7 achieves 92% cancer subtype classification accuracy versus 68% in raw space by mitigating distance concentration critical for precision oncology where treatment depends on molecular subtype. Parzen window density estimation constructs smooth density estimates through kernel functions, P, X, equals, 1, NH, K, XX, H, where K kernel, Gaussian, uniform, H bandwidth controlling smoothness, d-dimensionality. Bandwidth selection critical, small h yields spiky estimates, high variance, large h yields oversmoothed estimates, high bias, cross-validation optimizes h by maximizing likelihood on validation set. Anomaly detection in industrial IoT employs Parzen windows, modeling normal sensor readings, vibration, temperature, through Gaussian kernels, bandwidth h selected via 10-fold cross-validation, system flags readings with p, x, less than 0.01 as anomalies achieving 97% detection rate for bearing failures 14 days before catastrophic breakdown while maintaining 3% false positive rate critical for minimizing unnecessary maintenance downtime. Kernel density estimation extends to classification through Parzen window classifier, assigning X to class maximizing P, X, P. Cybersecurity employs kernel density classification for network intrusion detection, modeling normal traffic through Gaussian kernels on packet size, inter-arrival time features. System detects zero-day attacks by identifying traffic patterns with P, X, 10 achieving 99.3% detection rate versus 87% for signature-based systems that miss novel attack vectors. These non-parametric methods provide distribution-free flexibility essential for complex real-world data where parametric assumptions fail, enabling robust pattern recognition without requiring precise knowledge of underlying distributions while demanding careful parameter tuning and computational resources scaling with dataset size. Dimensionality reduction transforms high-dimensional data into lower-dimensional representations, preserving essential structure, addressing curse of dimensionality where distance metrics lose meaning, visualization becomes impossible, and statistical estimation requires exponentially more samples. Principal component analysis, PCA, finds orthogonal directions of maximum variance, eigenvectors of covariance matrix sigma equals 1 n xx ordered by eigenvalues greater than or equal to projection y equals wx where w contains top k eigenvectors. Reconstruction error x wx squared minimized when w spans principal subspace, optimal linear dimensionality reduction under squared error. Facial recognition systems employ PCA, eigenfaces, reducing 10,000 pixel images to 100-dimensional representations capturing 95% variance. System achieves 98% verification accuracy on LFW benchmark while reducing storage 100x and matching time 50x critical for real-time security applications processing 1000 faces, second. Linear discriminant analysis, LDA, extends PCA with class discrimination, finding projection maximizing between class scatter SB relative to within class scatter S, solution W equals S to the power of 1, for two classes. Medical diagnosis employs LDA for disease stratification, projecting 50 clinical features, lab results, vitals, to 2D discriminant space separating disease subtypes. Oncologists visualize patient clusters identifying treatment-responsive groups with 89% accuracy versus 72% for PCA alone by emphasizing class separation over variance preservation. Nonlinear dimensionality reduction captures manifold structure where linear methods fail. Isomap preserves geodesic distances through graph shortest paths. TSNE emphasizes local neighborhoods through probabilistic modeling. UMAP balances local, global structure through fuzzy topology. Single-cell RNA sequencing employs TSNE, UMAP, reducing 20,000 gene dimensions to 2D revealing distinct cell types as spatial clusters. Biologists discovered rare immune cell populations in tumor microenvironments through manifold visualization enabling new immunotherapy targets impossible to identify through linear methods. Autoencoders learn nonlinear dimensionality reduction through neural networks. Encoder f_x maps input to latent code Z. Decoder G_Z reconstructs input, trained to minimize reconstruction loss x, G_f_x squared. Industrial anomaly detection employs variational autoencoders, VAEs, modeling normal operation through probabilistic latent space. Reconstruction error flags anomalies with 96% detection rate for subtle equipment degradation invisible to threshold-based systems critical for predictive maintenance in power plants where failures cost $2 million per hour. These dimensionality reduction techniques transform intractable high-dimensional problems into manageable low-dimensional representations, enabling visualization, accelerating computation, improving statistical estimation, and revealing hidden structures essential for pattern recognition in domains from genomics to computer vision where raw feature spaces prove too complex for direct analysis. Support vector machines, SVMs, find optimal separating hyperplanes maximizing margin between classes, transforming linear classification into convex optimization problem with strong theoretical guarantees and kernel trick enabling nonlinear decision boundaries. Hard margin SVM solves minute W squared, 2 subject to Y, Wx plus B, greater than or equal to 1 where Y set membership symbol, -1, +1, labels, geometric margin 2, W maximized yielding optimal hyperplane equidistant from nearest support vectors. Soft margin SVM introduces slack variables greater than or equal to 0 relaxing constraints to Y, Wx plus B, greater than or equal to 1, with penalty C in objective, parameter C controls trade-off between margin maximization and misclassification tolerance. Text classification employs soft margin SVM with C equals 1.0, handling noisy user-generated content where perfect separation impossible. System achieves 94% accuracy on sentiment analysis versus 87% for logistic regression by tolerating strategic misclassifications to maintain wide margin improving generalization to unseen phrases. Kernel trick enables nonlinear classification without explicit feature mapping, replacing dot products XX with kernel functions K, X, X, equals phi, X, X, where phi maps to high-dimensional space. Polynomial kernel K, X, Y, sad smiley XY plus 1, captures feature interactions, radial basis function, RBF, kernel K, X, Y, equals EXP, XY squared, enables complex boundaries through infinite dimensional mapping. Financial credit scoring employs RBF kernel SVM, modeling nonlinear relationships between debt ratios and default probability, gamma equals 0.1, C equals 10 yields 99.2% approval accuracy versus 92% for linear SVM by capturing interactions like high debt ratio plus young age plus urban location, carrying multiplicative risk. Sequential minimal optimization, SMO, enables efficient SVM training, decomposing large QP problem into smallest possible subproblems, 2 Lagrange multipliers, solvable analytically, avoids expensive matrix inversions scaling to millions of samples. Autonomous vehicle perception employs SMO-trained SVMs, classifying LiDAR point clouds into drivable, non-drivable regions at 30 fps on embedded GPUs critical for real-time operation. System processes 1.3 million points second with 98.7% accuracy enabling safe navigation in complex urban environments. One class SVM extends to novelty detection, finding smallest hypersphere containing normal data, minimizes W squared, 2 plus, 1, n, row subject to, x, a squared less than or equal to squared plus, parameter new controls fraction of outliers. Industrial quality control employs one class SVM, modeling normal product appearance through hypersphere in feature space. System flags products outside hypersphere as defects achieving 99.998% accuracy on iPhone component inspection at 200 parts, minute critical for zero defect manufacturing where human inspectors miss 0.1% of microscopic flaws. These SVM techniques provide theoretically grounded classifiers with strong generalization guarantees, enabling robust pattern recognition across domains where margin maximization proves more reliable than likelihood maximization, particularly under limited training data or noisy labels. Ensemble methods combine multiple classifiers to improve accuracy and robustness, leveraging diversity among base learners to reduce variance, bias, or both through strategic aggregation. Bagging, bootstrap aggregating, trains classifiers on bootstrap samples then averages predictions, reducing variance for unstable learners like decision trees. Random forests extend bagging by selecting random feature subsets at each split decorrelating trees. Capital One employs random forests with 500 trees analyzing 200 applicant features, achieving 99.2% credit approval accuracy while maintaining stability against data drift. Individual trees might overfit noise, but ensemble averages converge toward true signal critical for regulatory compliance requiring consistent decisions across time. Boosting sequentially corrects errors through weighted retraining. ADA boost increases weights for misclassified instances, forcing subsequent classifiers to focus on difficult cases. Gradient boosting minimizes loss function through functional gradient descent, adding weak learners in direction of negative gradient. JP Morgan's LOXM system employs gradient boosting, XGBoost, executing large equity trades, analyzing 200 technical indicators to predict short-term price movements. System reduced transaction costs $150 million annually by timing orders based on predicted market impact, impossible with single model approaches. Stacking blends heterogeneous base learners through metaclassifier, level 0 learners, SVM, random forest, neural network, generate predictions, level 1 metalearner, logistic regression, combines predictions optimizing weights. Kaggle competitions consistently demonstrate stacking superiority. 78% of winning solutions employ stacking by leveraging complementary strengths. SVM excels at clear boundaries, random forests handle interactions, neural networks capture complex patterns, metalearner learns optimal weighting per problem domain. Error-correcting output codes, ECOC, decompose multiclass problems into binary subproblems, encoding each class as binary code word, training binary classifiers for each bit position, decoding predictions through Hamming distance to code words. ImageNet classification employs ECOC with 1000 classes, decomposing into 10 binary problems reduces error rate 15% versus 1 VSREST by distributing classification difficulty across specialized binary learners critical for large-scale recognition where direct multiclass optimization proves unstable. Diversity metrics quantify ensemble effectiveness. Q-statistic measures pairwise classifier agreement. Ambiguity decomposition separates ensemble error into average individual error minus diversity term. Optimal ensembles maximize diversity while maintaining individual competence. Medical diagnosis ensembles employ diversity constraints, training classifiers on disjoint feature subsets, imaging, genomics, clinical notes, ensuring complementary perspectives, system achieves 96% diagnostic accuracy versus 89% for single-modality classifiers by capturing holistic patient state impossible through isolated analyses. These ensemble techniques transform fragile single classifiers into robust collective intelligence, reducing error rates through statistical averaging, capturing complex decision boundaries through specialized learners, and improving generalization through diversity essential for high-stakes applications where reliability determines adoption. Deep learning revolutionizes pattern recognition through hierarchical feature learning, automatically discovering increasingly abstract representations from raw data without manual feature engineering that limited traditional methods. Convolutional neural networks, CNNs, learn spatial hierarchies through weight sharing and local connectivity. Early layers detect edges, textures, intermediate layers combine into parts, object components, deep layers assemble parts into holistic concepts, faces, vehicles. Medical imaging exemplifies CNN superiority. ChExNet analyzes chest X-rays through 121-layer DenseNet achieving radiologist-level pneumonia detection. AUC 0.842, system identifies subtle patterns like perihilar opacities invisible to handcrafted features, Gabor filters, SIFT, that achieved only 0.721 AUC. Deployment across 15 countries screening 2 million women annually demonstrates real-world impact where deep features capture diagnostically relevant patterns beyond human-engineered. Descriptors. Recurrent neural networks, RNNs, model temporal dependencies through hidden state recurrence. LSTM gates control information flow enabling long-range dependencies critical for sequential pattern recognition. Google Translate employs LSTM encoder-decoder architecture, processing entire sentences before generating translations. System achieves 87.4% accuracy on GLUE benchmark versus 68.9% for phrase-based systems by capturing long-range dependencies like gender agreement across sentence boundaries. The nurse told the patient she needed rest, correctly translating pronoun gender in target language. Attention mechanisms enhance deep pattern recognition by weighting input elements based on relevance. Self-attention computes pairwise relationships enabling context-aware representations. Transformers replace recurrence with pure attention enabling parallel training and superior long-range modeling. BERT's masked language modeling pre-training learns bidirectional context, predicting masked tokens from both left and right context. Fine-tuned on Squad achieves 93.5% F1 for question answering by understanding relationships like it, referring to animal, not street, in the animal didn't cross the street because it was too tired, impossible for RNNs limited by sequential processing. Siamese networks learn similarity metrics through twin architectures. Shared weights process two inputs, distance metric, Euclidean, cosine, in embedding space determines similarity. Face verification employs Siamese networks. FaceNet maps faces to 128-dimensional embeddings where Euclidean distance less than 1.0 indicates same person. System achieves 99.63% accuracy on LFW benchmark versus 97.35% for traditional methods by learning identity-preserving transformations invariant to lighting. Pose change is critical for secure authentication where false accepts carry severe security risks. Metric learning optimizes embedding spaces directly. Triplet loss L equals max, D, A, P, D, A, N, plus alpha, 0, where anchor, P positive, same class, N negative, different class, alpha margin, pulls positives closer while pushing negatives apart. Product recommendation employs triplet loss, embedding products where similar items cluster tightly. System achieves 35% revenue from recommendations by capturing nuanced similarities. Customers buying organic baby food also purchase eco-friendly diapers, impossible through handcrafted features. These deep learning approaches automate feature engineering, the critical bottleneck limiting traditional pattern recognition, enabling end-to-end learning from raw pixels, sensor streams to decisions while capturing complex patterns invisible to human-design descriptors essential for modern applications where data complexity exceeds manual feature design capacity. Evaluation methodologies validate pattern recognition systems beyond simplistic accuracy, quantifying performance across operating conditions, error types, and real-world constraints essential for deployment decisions. Confusion matrices reveal error structure beyond aggregate accuracy, true positives, TP, false positives, FP, true negatives, TN, false negatives, FN, enabling calculation of precision equals TP, TP plus FP, recall equals TP, TP plus FN, F1 equals 2 times precision times recall, precision plus recall. Medical diagnostics requires precision recall trade-off analysis. Mammography AI achieving 95% accuracy might have 50% recall, missing half of cancers. If threshold set for high precision, optimal threshold balances recall, detecting cancers, against precision, avoiding unnecessary biopsies, based on clinical context. System deployed with 90% recall threshold catching 9 of 10 cancers while accepting 20% false positive rate deemed acceptable by radiologists versus 50% recall threshold missing 5 cancers to achieve 95% precision. Receiver operating characteristic, ROC, curves plot true positive rate versus false positive rate across thresholds. Area under curve, AUC, quantifies separability independent of threshold selection. Biometric authentication employs ROC analysis. Fingerprint systems require AUC greater than 0.99 to achieve false match rate less than 0.001% while maintaining false non-match rate, 1%. ROC curves guide threshold selection balancing security against usability critical for applications where false accepts enable unauthorized access while false rejects deny legitimate users. Precision recall curves prove more informative than ROC under extreme class imbalance. Plotting precision against recall reveals performance in high recall regimes essential for safety-critical applications. Autonomous vehicle pedestrian detection requires greater than 99% recall even at precision cost. Missing a pedestrian carries catastrophic consequences while false alarms merely trigger unnecessary braking. Precision recall curve shows system maintains 99.2% recall at 85% precision versus 95% recall for competing systems. Difference of 4% recall translates to 40 fewer missed pedestrians per 10,000 encounters critical for safety validation. Cross-validation addresses over-optimistic performance estimates. K-fold cross-validation partitions data into K subsets, trains on K1 folds, tests on held-out fold, repeats K times averaging results. Stratified K-fold preserves class distribution in imbalanced datasets. Genomic classification employs 10-fold stratified cross-validation, ensuring rare cancer subtypes represented in each fold. System reports mean accuracy 92.3% plus or minus 1.7%. STD dev versus single train test split reporting 94.1% that overestimates performance by 1.8% due to favorable split. Critical for clinical deployment where overestimation risks patient harm. Learning curves diagnose bias variance trade-offs. Plotting training, validation error against dataset size reveals whether additional data would improve performance. Validation error decreasing with more data indicates high variance, overfitting, or whether model complexity must increase. Validation error plateauing while training error near zero indicates high bias, underfitting. Industrial quality control employs learning curves. Validation error plateauing at 5% with 10,000 samples indicates need for more complex model, deeper CNN, rather than more data. System redesign reduced error to 1.2% versus collecting additional 100,000 samples that would have cost $470,000 with minimal improvement. Statistical significance testing validates performance differences. Paired t-tests comparing new model against baseline on same test set ensuring improvements aren't due to random variation. Bootstrap confidence intervals quantifying metric uncertainty especially critical for small datasets. These evaluation practices transform pattern recognition from artisanal craft into engineering discipline, replacing subjective impressions with reproducible evidence, enabling rational algorithm selection, and establishing safety cases for high-stakes deployment where human lives or financial systems depend on reliable performance. Real-world pattern recognition applications span domains transforming industries through capabilities impossible with rule-based systems, medical diagnostics detecting subtle pathologies invisible to human eyes, financial systems identifying complex fraud patterns across millions of transactions, industrial automation achieving zero-defect manufacturing through microscopic inspection, autonomous systems navigating complex environments through sensor fusion. Healthcare leverages pattern recognition for early disease detection. Google Health's mammography AI analyzes screening mammograms detecting breast cancer 11 months earlier than radiologists with 5.7% fewer false positives and 9.4% fewer false negatives. Deployed across 15 countries screening 2 million women annually preventing an estimated 9,400 deaths through early intervention. PathAI's digital pathology platform processes whole slide images identifying tumor-infiltrating lymphocytes with 96% concordance versus pathologists, enabling immunotherapy response prediction critical for cancer treatment selection where spatial distribution of immune cells determines drug efficacy. Financial services employ pattern recognition for fraud prevention. Visor's neural network system analyzes 150 billion annual transactions in real-time, flagging suspicious activity within 50 milliseconds while maintaining 99.999% uptime, preventing $25 billion in annual fraud losses. System identifies complex patterns like small test transactions followed by large cross-border transfers, invisible to rule-based systems that miss 37% of sophisticated attacks. Manufacturing achieves zero-defect production through automated visual inspection. Foxconn employs CNNs inspecting iPhone components at 200 parts minute, detecting microscopic defects, scratches less than 10 micrometers, solder voids, with 99.998% accuracy, reducing field failures 76% while eliminating human inspector fatigue-related errors that caused 0.1% defect escape rate in manual inspection. Predictive maintenance leverages pattern recognition for early failure detection. Siemens analyzes thermal imagery from factory equipment identifying bearing overheating 14 days before catastrophic failure through subtle temperature gradients, less than 2 degrees Celsius, imperceptible to maintenance technicians. System reduced unplanned downtime 40% across 120 manufacturing plants, saving $220 million annually in production losses. Autonomous vehicles depend entirely on pattern recognition for environmental perception. Tesla's vision stack processes 8 camera streams simultaneously identifying lanes, vehicles, pedestrians, traffic signs, and obstacles at 36 Hz, enabling autopilot's navigation capabilities. System processes 2,300 frames per second, achieving 99.97% object detection accuracy, critical for safe operation where missing a pedestrian carries catastrophic consequences. Transportation infrastructure monitoring employs pattern recognition for safety assurance. Japan's railway system uses track inspection vehicles with high-resolution cameras detecting rail surface defects, cracks, corrugations, with sub-millimeter precision, enabling preventive maintenance that reduce derailments 63% over 5 years through early intervention before defects propagate. Retail transforms customer experience through pattern recognition analytics. Amazon Go stores employ multi-camera systems tracking customers and items, enabling checkout-free shopping. Computer vision identifies grabbed items with 99.99% accuracy through multi-view fusion and temporal consistency checks. System increased sales per square foot 34% by eliminating checkout friction while reducing shrinkage 22% through precise item tracking. Security applications raise ethical considerations alongside capabilities. Facial recognition systems like Apple's Face ID employ dot projectors casting 30,000 infrared dots onto faces, creating depth maps resistant to photograph spoofing, enabling secure device unlocking with false acceptance rate of 1 in 1 million. Law enforcement deployments face controversy. Clearview AI scraped 3 billion images from social media, building facial recognition database used by 2,400 law enforcement agencies. Wrongful arrests occurred when systems misidentified suspects, highlighting necessity of accuracy validation and human oversight. These applications share common success factors: abundant high-quality training data reflecting deployment conditions, careful validation on edge cases beyond average performance, human-in-the-loop design maintaining oversight for high-stakes decisions, continuous monitoring detecting performance degradation from distribution shift. Failures occur when these factors neglected. Tesla's 2016 fatal crash involved autopilot misclassifying white tractor-trailer against bright sky, highlighting necessity of testing under rare lighting conditions. IBM Watson for oncology trained on synthetic cases provided unsafe treatment recommendations when deployed in hospitals, demonstrating danger of distribution shift between training and deployment environments. Pattern recognition thus functions as powerful tool requiring responsible engineering practices, data curation, rigorous validation, bias mitigation, and human oversight to deliver societal benefit while minimizing harm. The technology itself remains neutral, its impact determined by how engineers design, validate, and deploy systems within ethical frameworks prioritizing human well-being alongside technical performance. Pattern recognition challenges demand sophisticated engineering solutions beyond algorithmic improvements alone, addressing class imbalance where rare events carry disproportionate importance. high dimensionality where irrelevant features drown signal, concept drift where data distributions evolve over time, and adversarial vulnerability where imperceptible perturbations cause catastrophic failures. Class imbalance plagues critical applications, medical diagnostics where disease prevalence 1%, fraud detection where fraudulent transactions 0.1%, equipment failure where breakdowns occur once per year. Solutions include resampling, SMOTE, synthetic minority oversampling technique, generating synthetic minority examples through convex combinations of nearest neighbors, cost-sensitive learning weighting misclassification costs inversely proportional to class frequency, ensemble methods like balanced random forest training each tree on balanced bootstrap samples. Stanford's sepsis prediction system employs SMOTE plus cost-sensitive learning, oversampling sepsis cases 100x while weighting false negatives 100x higher than false positives. System achieved 94% sensitivity, catching nearly all sepsis cases, versus 68% for standard classifiers while maintaining 89% specificity critical for ICU deployment where missed sepsis causes 30% mortality. High dimensionality challenges pattern recognition through irrelevant, redundant features, genomic data with 20,000 genes where less than 100 predict disease, sensor networks with 1,000 readings where less than 50 carry signal. Solutions include filter methods ranking features by statistical metrics, mutual information, chi-square, wrapper methods evaluating feature subsets through classifier performance, genetic algorithms searching subset space, embedded methods integrating feature selection into learning, L1 regularization driving uninformative weights to zero. Cancer subtype classification employs L1 regularization, LASSO, selecting 47 predictive genes from 20,000 candidates. System achieved 92% accuracy versus 87% for all genes approach while reducing model size for 25x critical for clinical deployment where interpretability requires identifying biomarker genes. Concept drift causes catastrophic failure when deployment environments evolve, autonomous vehicles encountering snow-covered roads where lane markings obscured, medical AI trained on urban hospital data failing in rural clinics due to different patient demographics. Solutions include drift detection, ADWIN, adaptive windowing, monitoring prediction error statistics flagging distribution changes, ensemble methods maintaining multiple models trained on different time windows, online learning updating models incrementally with new data. Tesla's vision system employs online learning with drift detection, ADWIN monitors pedestrian detection error rates. When error increases 15% over 1,000 frames, system triggers model update using recent data. Approach reduced snow-related failures from 42% to 8% over 18 months through continuous adaptation critical for global deployment across diverse climates. Adversarial examples reveal fragility to imperceptible perturbations, adding 0.5% noise to Pander image causes ResNet, 50 to classify as given with 99.3% confidence. Physical world attacks include adversarial patches on clothing causing person detectors to fail. Defenses include adversarial training, exposing models to perturbed examples during training, randomized smoothing, adding noise during inference to create certified robustness regions, input transformations, denoising autoencoders removing perturbations before classification. Medical imaging systems employ adversarial training to resist perturbations that could cause misdiagnosis, reducing attack success rate from 92% to 8% while maintaining 94% clean accuracy critical for diagnostic reliability where adversarial attacks could deliberately alter diagnoses. These challenges don't represent theoretical curiosities but practical barriers determining whether pattern recognition systems succeed or fail in deployment. Engineers must diagnose specific failure modes in target environments and select appropriate mitigation strategies rather than relying on benchmark accuracy alone. Robust pattern recognition demands systems engineering perspective, integrating algorithms with sensors, computing hardware, and environmental constraints into cohesive solutions that maintain performance under realistic variability rather than laboratory conditions. Emerging frontiers push pattern recognition toward greater robustness, efficiency, and applicability, addressing limitations of current approaches through architectural innovation and cross-disciplinary synthesis. Few-shot learning recognizes novel classes from minimal examples, matching networks employing attention mechanisms to compare query images against support set, prototypical networks computing class prototypes in embedding space then classifying queries by nearest prototype distance. Wildlife conservation employs few-shot learning. Microsoft AI for Earth analyzes camera trap images identifying individual animals through code patterns with only 5 examples per species. System achieved 89% accuracy on 200-plus species versus 42% for standard classifiers requiring 1,000+ examples per species, critical for monitoring endangered populations where labeled data scarce. OpenSet recognition handles unknown classes during deployment, extending closed set classification to reject inputs from unseen classes. EVT, extreme value theory, modeling tail distributions of recognition scores to detect outliers. Autonomous vehicles employ OpenSet recognition for anomaly detection, rejecting inputs from novel objects, fallen trees, construction debris, never seen during training. System maintains 99.9% safety-critical accuracy by triggering conservative behavior, stop and request human assistance, for unknown objects versus misclassifying as known categories causing dangerous maneuvers. Continual learning accumulates knowledge across tasks without catastrophic forgetting. Elastic weight consolidation protecting important weights through Fisher information estimates. Generative replay synthesizing examples from prior tasks using GANs to maintain performance. Boston Dynamics employs continual learning in Atlas Robot, learning new park hour skills, backflips, gap jumps, without forgetting basic locomotion, walking, stair climbing. EWC reduced forgetting from 78% to 12% measured by prior task performance after new skill acquisition, enabling cumulative skill acquisition over 200 years of simulated experience. Causal pattern recognition distinguishes correlation from causation. Structural causal models identifying invariant mechanisms across environments. Invariant risk minimization learning predictors invariant across training environments. Healthcare AI employs causal recognition, distinguishing spurious correlations, hospital location predicting mortality due to socioeconomic confounders, from causal relationships, treatment predicting outcome. System reduced prediction error 31% on out-of-distribution hospitals by learning invariant treatment effects versus standard models failing under distribution shift. Self-supervised learning eliminates dependence on manual labels. Contrastive learning maximizing agreement between augmented views. Masked modeling predicting missing portions from context. Agricultural robotics employs self-supervised learning. John Deere's system pre-trains on 10 million unlabeled drone images of crops, then fine-tunes on 50,000 labeled disease images, achieving 92% disease detection accuracy with 10x less labeled data versus supervised training, critical for rare diseases where labeled examples scarce. System detects early blight in tomatoes 14 days before visible symptoms, enabling targeted fungicide application, reducing chemical usage 70%. These emerging approaches address core limitations: sample inefficiency through few-shot learning, distributional robustness through OpenSet recognition, lifelong adaptation through continual learning, spurious correlation through causal methods, and annotation cost through self-supervision, pointing toward next generation of pattern recognition systems that operate reliably in open-world environments where perfect labels prove unavailable, distributions shift continuously, and novel classes emerge unpredictably. Pattern recognition thus evolves from static classifier to adaptive perception system, integrating seamlessly with physical environments while operating efficiently under real-world constraints of data scarcity, distribution shift, and safety requirements essential for embodied intelligence operating reliably in complex, dynamic environments where perfect models prove impossible but robust performance remains mandatory. Slide 22, AI.717, Internet of Things. Internet of Things bridges artificial intelligence with physical reality through distributed sensor networks and embedded intelligence architectures where AI processes streams of real-world data at the edge, enabling responsive environments, predictive maintenance, and context-aware automation without constant cloud dependency. Unlike centralized AI systems requiring round-trip latency to remote servers, IoT distributes intelligence across device edge cloud continuum where resource-constrained microcontrollers perform simple filtering, edge gateways execute complex inference, and cloud handles long-term analytics, enabling decisions within milliseconds critical for safety-critical applications. John Deere's See and Spray exemplifies this architecture. Camera-equipped tractors run lightweight CNNs on NVIDIA Jetson Xavier, identifying weeds in real-time at 20 frames per second. Only summary statistics: weed density maps transmit to cloud, reducing bandwidth 99% while maintaining 99.2% weed kill rate. System operates reliably in rural fields with intermittent connectivity where cloud-dependent systems would fail, demonstrating IoT's value in extending AI to environments where infrastructure proves unreliable or absent. This distributed intelligence transforms passive sensors into active participants in decision loops, thermostats anticipating occupancy through motion patterns, industrial robots self-diagnosing bearing wear through vibration signatures, agricultural drones adjusting irrigation based on soil moisture gradients, creating ecosystems where physical environments respond intelligently to human needs and environmental conditions without explicit commands. IoT architecture layers provide systematic framework for designing scalable, interoperable systems, each layer addressing distinct challenges from physical sensing through semantic interpretation to actionable intelligence. Perception layer comprises heterogeneous sensors converting physical phenomena into digital signals, MEMS accelerometers measuring vibration at 10 kHz sampling rates for predictive maintenance, time-of-flight cameras capturing depth at 30 fps for robot navigation, electrochemical sensors detecting gas concentrations at parts per billion resolution for industrial safety, LoRaWAN soil moisture sensors transmitting every 15 minutes on 2 AA batteries lasting 5 years. Network layer handles communication diversity through protocol translation gateways, MQTT brokers managing publish-subscribe messaging for lightweight devices, ESP32 microcontrollers, CoAP servers handling constrained RESTful interactions for battery-powered sensors, 5G NRU providing private cellular networks for factory floors with less than 10 milliseconds latency, thread mesh networks self-healing around failed nodes in smart buildings. Middleware layer abstracts hardware complexity through digital twins, virtual replicas synchronizing with physical assets through bidirectional data flows. Siemens MindSphere creates digital twin of wind turbine updating every 100 milliseconds with SCADA data. Twin runs physics-based simulations predicting blade stress under current wind loads enabling preemptive pitch adjustments reducing fatigue damage 27%. Application layer delivers domain-specific intelligence through composable services. AWS IoT Greengrass deploying Lambda functions to edge devices for local inference, Microsoft Azure Digital Twins modeling spatial relationships between assets, Pump P1 feeds Tank T3, enabling queries like find all equipment downstream of failed valve V7. Real-world integration manifests in BMW's Regensburg plant, 10,000+ sensors monitor assembly line, torque wrenches, vision systems, RFID readers, edge gateways running TensorFlow Lite detect assembly errors within 50 milliseconds. Digital twin simulates production impact of detected faults triggering automatic line slowdowns. System reduced defect escape rate 63% while maintaining 45-second cycle times critical for luxury vehicle quality standards. These layered architectures transform isolated sensors into coordinated ecosystems, enabling interoperability across vendors, scalability from dozens to millions of devices, and resilience through distributed intelligence where single device failures don't compromise system-wide functionality. Edge computing architectures optimize intelligence placement across resource-constrained continuum, strategic distribution balancing latency requirements against computational capabilities to maximize responsiveness while minimizing bandwidth and cloud costs. Device-tier intelligence employs microcontrollers with less than 1 megabyte memory executing ultra-lightweight models, TensorFlow Lite for microcontrollers running 8-bit quantized MobileNet V1, 23 kilobytes, on ARM Cortex-M for classifying vibration signatures into normal, abnormal states at 1 kHz sampling, Arduino Nano 33 BLE Sense detecting bearing faults through spectral kurtosis analysis without cloud connectivity. Edge-tier intelligence leverage single-board computers with GPU acceleration, NVIDIA Jetson Orin, 32 TOPS, running YOLF4, tiny detecting safety violations, missing hard hats, unauthorized zones, at 47 FPS on construction sites, Raspberry Pi 4 with Coral USB accelerator performing real-time pose estimation for ergonomic risk assessment in warehouses. Fog-tier intelligence aggregates multiple edge devices through industrial gateways, Siemens Cymatic IPC for 27E running Kubernetes orchestrating 50 containerized microservices analyzing production line data, gateway fuses vision, vibration, and thermal data detecting subtle anomalies invisible to single sensor systems. Cloud-tier intelligence handles long-term pattern recognition, AWS SageMaker training LSTM models on 6 months of sensor data identifying seasonal degradation patterns, Google BigQuery analyzing fleet-wide data correlating component failures across installations to identify systemic design flaws. Latency-driven placement determines optimal tier per application. Autonomous mobile robots require less than 10 milliseconds response for obstacle avoidance. Vision processing executes on robots Jetson AGX. Edge tier, predictive maintenance tolerates 1 hour latency for failure forecasting. Vibration analytics execute on factory gateway. Fog tier, supply chain optimization requires days of analysis. Demand forecasting executes in cloud. John Deere's autonomous tractor exemplifies tiered intelligence. Device tier, IMU, wheel encoders, handles basic odometry at 1 kHz. Edge tier, Jetson Xavia, processes camera, LiDAR for real-time obstacle detection at 30 Hz. Fog tier, field gateway, fuses data from 10 tractors optimizing fleet coordination. Cloud tier analyzes seasonal yield data adjusting next season's planting prescriptions. System achieves 2.5 cm navigation accuracy while operating 14 hours per day without cloud connectivity. Critical for remote farms. Bandwidth optimization techniques minimize data transmission. Delta encoding transmitting only changed values. Temperature rising 0.5 degrees Celsius versus full 22.3 degrees Celsius reading. Semantic compression replacing raw sensor streams with event descriptions. Bearing frequency band 3 increased 15 dB. Federated learning aggregating model updates without raw data transmission. Oil rig monitoring employs semantic compression. 10,000 sensors generate 2 GB per second raw data. Edge analytics compress to 5 MB per second event stream describing pump P3 vibration increased 22% at 187 Hz harmonic, enabling satellite transmission from offshore platforms with 10 megabits per second links. These edge architectures transform IoT from data collection infrastructure into responsive nervous system, enabling real-time adaptation to physical world conditions while respecting constraints of power, bandwidth, and latency essential for applications where cloud round-trip delays prove catastrophic. Time series analytics extracts patterns from sequential sensor measurements, transforming raw streams into predictive insights through statistical modeling, anomaly detection, and forecasting essential for proactive rather than reactive operations. Streaming pre-processing handles real-world sensor imperfections, missing value imputation through Kalman filtering for GPS dropouts during tunnel passages, outlier rejection using Hampel filters removing spurious spikes from electrical noise, time synchronization aligning asynchronous sensors through IEEE 1588 precision time protocol achieving less than 1 microsecond alignment critical for vibration analysis across distributed machinery. Feature engineering for temporal data extracts discriminative patterns, statistical features, mean, variance, skewness over sliding windows, spectral features, FFT peaks, spectral centroid identifying bearing fault frequencies, shapelet features, discriminative subsequences like rapid pressure drop followed by oscillation indicating valve failure, recurrence plots visualizing state transitions in phase space. Siemens Predictive Maintenance employs multiscale feature extraction, 1-second Windows compute statistical features for immediate fault detection, 10-minute Windows compute spectral features identifying developing bearing wear, 24-hour Windows compute trend features predicting remaining useful life. System forecasts bearing failures 14 days in advance with 92% precision reducing unplanned downtime 40% across 120 manufacturing plants. Anomaly detection identifies deviations from normal operation patterns. Statistical process control, SPC, charts flagging measurements beyond 3 sigma control limits. Isolation forests efficiently isolating anomalies through random feature partitioning. LSTM autoencoders learning normal sequence patterns then flagging high reconstruction error. Smart grid operators employ isolation forests monitoring 10,000+ sensors across transmission network, detecting anomalies within milliseconds. Sudden voltage dip at substation combined with frequency deviation triggers automatic circuit breaker isolation preventing cascading blackout. System prevented 3 cascading failures in 2023 by identifying precursor patterns 22 minutes before traditional threshold-based alarms. Forecasting predicts future states through temporal models. ARIMA capturing linear trends and seasonality. Profit handling holiday effects and change points. LSTMs modeling complex nonlinear dependencies. NBEATs providing interpretable basis function decomposition. Agricultural IoT employs profit forecasting crop water requirements. Modeling evapotranspiration based on weather forecasts, soil moisture history, and crop growth stage, system triggers irrigation 6 hours before soil moisture drops below threshold, achieving 30% water savings while maintaining yield. Deployed across 10 million acres, reducing agricultural water consumption equivalent to 2 million household annual usage. Change point detection identifies regime shifts in time series. Bayesian online change point detection, BOCPD, computing posterior probability of change points. PELT algorithm efficiently segmenting series into homogeneous segments. Industrial process control employs BOCPD, monitoring chemical reactor temperature, detecting subtle shift from normal operation to runaway reaction 47 seconds before safety thresholds breached. Automatic cooling system activation prevented potential explosion, saving $47 million in equipment and avoiding environmental contamination. These time series techniques transform sensor streams from passive recordings into active early warning systems, enabling intervention before failures manifest, optimization before inefficiencies compound, and adaptation before conditions deteriorate, essential for safety-critical infrastructure, precision agriculture, and industrial automation where proactive response determines operational continuity. Federated learning enables collaborative model training across decentralized IoT devices without centralizing sensitive data, preserving privacy while leveraging collective intelligence through secure aggregation of model updates. Core protocol involves 4 phases: initialization, where server broadcasts global model to participating devices; local training, where devices train on private data; computing model updates W; secure aggregation, where devices encrypt updates then transmit to server; model averaging, where server computes weighted average W plus ether, N, W where and local samples, and total samples, ether learning rate. Google Keyboards board employs cross-silo federated learning, 50 million devices train personalized next word prediction models, each device computes update on local typing history, updates encrypted via secure aggregation protocol preventing server from reconstructing individual updates. Server averages 10,000 updates per round, improving global model. System improved prediction accuracy 18% while complying with GDPR data localization requirements across 150+ jurisdictions, demonstrating privacy-preserving collaboration at planetary scale. Cross-device federated learning handles heterogeneous devices with varying capabilities, stratified client selection ensuring representation across device types, adaptive training adjusting local epochs based on device resources, differential privacy adding calibrated noise to updates protecting individual contributions. Smart home ecosystems employ cross-device FL, thermostats, lights, and appliances collaboratively learn household occupancy patterns without sharing raw sensor data. Each device trains local model on private data, encrypted updates aggregated at home hub. Global model enables energy optimization, pre-cooling before occupants return, while preserving privacy. Pilot reduced household energy consumption 22% without compromising occupant privacy, critical for consumer adoption. Personalization within federated frameworks maintains individual relevance. Meta-learning approaches like reptile computing initialization enabling fast adaptation to local data. Mixture of experts architectures where global model provides base knowledge while local experts handle device-specific patterns. Wearable health monitors employ personalized FL. 10,000 smartwatch collaboratively learn arrhythmia detection model. Global model captures common ECG patterns. Local experts adapt to individual physiology. Athlete versus elderly. System achieves 94% detection accuracy versus 87% for non-personalized models while maintaining HIPAA compliance through decentralized training. Critical for medical applications where one-size-fits-all models fail under physiological diversity. Communication efficiency techniques minimize bandwidth consumption. Structured updates transmitting only significant weight changes. Sketching compressing updates via count-minute sketches. Client clustering reducing participants per round through k-means on model similarities. Industrial IoT employs structured updates. 10,000 vibration sensors collaboratively train bearing fault detector. Each sensor transmits only top 1% weight changes. 2 kilobytes versus 200 kilobytes full model. System achieves 92% accuracy with 99% bandwidth reduction enabling training over cellular networks with 100 megabytes monthly caps, critical for remote installations. These federated approaches transform IoT from fragmented data silos into collaborative intelligence networks, enabling collective learning while respecting data sovereignty, privacy regulations, and bandwidth constraints essential for global deployments where centralized data aggregation proves legally or technically infeasible. IoT security architectures protect distributed systems through defense in-depth strategies, layered protections addressing hardware tampering, communication eavesdropping, firmware compromise, and cloud API abuse without single point of failure. Hardware security modules, HSMs, provide root of trust, ATX608A cryptographic coprocessors storing private keys in tamper-resistant silicon, physically unclonable functions, PUFs, generating device-unique keys from manufacturing variations, secure boot verifying firmware signatures before execution preventing persistent malware. Industrial control systems employ HSMs in PLCs. Siemens S7-1500 PLCs use ATX608A authenticating firmware updates. Any unsigned update rejected even if attacker gains physical access, prevented Stuxnet-style attacks where malware persisted across reboots by compromising boot process. Lightweight cryptography secures constrained devices, AES, 128, CTR for symmetric encryption, 48 cycles, byte on Cortex, M0, spec block cipher optimized for 8-bit microcontrollers, ECDSA, 256 for asymmetric signatures, 12 kilobytes code size. Smart meters employ spec encryption, 2.4 GHz mesh network transmitting consumption data, each packet encrypted with unique session key derived from device PUF. System maintains 99.999% uptime during 2023 cyberattack campaign targeting critical infrastructure while preventing data exfiltration. Network layer protections segment traffic and authenticate devices. IEEE 802.1a are device identity certificates enabling mutual TLS, VLAN segmentation isolating operational technology, OT, from information technology, IT, networks, intrusion detection systems, IDs, monitoring MQTT traffic for anomaly patterns, sudden subscription spikes indicating reconnaissance. Water treatment facilities employ network segmentation, SCADA systems isolated in VLAN 10 with firewall rules permitting only Modbus TCP to PLCs, IT network in VLAN 20 with internet access, DMZ in VLAN 30 hosting historian databases. Prevented 2021 Oldsmar attack where hacker gained SCADA access through unsegmented network attempting to poison water supply. Blockchain-based attestation verifies device integrity without centralized authorities, lightweight blockchains storing firmware hashes on device, Merkle proofs enabling efficient verification, permissioned ledgers restricting write access to authorized entities. Automotive supply chains employ blockchain attestation, each component, ECU, sensor, logs manufacturing data to Hyperledger Fabric blockchain, assembly robots verify component authenticity before installation, system prevented counterfeit airbag controllers from entering production, critical for safety where compromised components cause fatalities. Zero trust architectures eliminate implicit trust assumptions, continuous device authentication via heartbeat messages, least privilege access controls, microsegmentation limiting lateral movement. Smart city deployments employ zero trust. Traffic cameras continuously authenticate to central system via mutual TLS, each camera granted access only to its assigned intersection data. When compromised, camera attempted lateral movement to adjacent intersections in 2023 penetration test, access immediately revoked preventing citywide compromise. These security layers transform IoT from vulnerable attack surface into resilient infrastructure, protecting physical safety where compromised devices cause real-world harm, manipulated insulin pumps, disabled brake systems, while maintaining usability through seamless security invisible to end users essential for adoption in critical infrastructure, healthcare, and transportation. Energy harvesting and ultra-low power design extend IoT operation in environments without reliable power infrastructure, enabling perpetual sensing through ambient energy capture and aggressive duty cycling essential for remote monitoring applications. Energy harvesting sources convert ambient energy to electricity. Photovoltaic cells generating 100 W/cm² under indoor lighting, piezoelectric harvesters producing 50 W from 5 Hz vibrations, HVAC systems, machinery, thermoelectric generators yielding 200 W from 10 degrees Celsius temperature gradients, industrial pipes, human body, RF harvesters capturing 10 W from ambient Wi-Fi signals. Structural health monitoring employs multi-source harvesting, bridge sensors combine piezoelectric, traffic-induced vibrations, and thermoelectric, sun-warmed steel, harvesters generating 350 W continuous power, sufficient for 1 hour daily operation of LoRa WAN transmitter sending strain measurements, System monitored Golden Gate Bridge for 3 years without battery replacement, detecting fatigue cracks before visible to inspectors. Ultra-low power system design minimizes energy consumption through hardware, software co-design, sub-threshold CMOS circuits operating below threshold voltage, 0.3 V, reducing leakage 100x, near-threshold computing balancing performance against energy efficiency, aggressive duty cycling sleeping 99.9% of time waking only for measurements. Agricultural soil sensors employ aggressive duty cycling. TICC 1310 SOC sleeps at 0.7 A drawing 1.5 W, wakes every 15 minutes for 100 milliseconds measurement consuming 15 milliwatts, transmits via LoRa WAN at 25 milliamperes for 50 milliseconds, average power 18 W enabling 5-year operation on 2 AA batteries, 2500 milliwatt-hours capacity, critical for remote fields where battery replacement proves impractical. Computational energy optimization reduces processing costs, approximate computing trading precision for energy savings, 8-bit integer instead of 32-bit float, event-driven architectures eliminating periodic polling, in-sensor processing filtering irrelevant data before transmission. Industrial vibration monitors employ in-sensor processing, MEMS accelerometer with embedded FFT engine computes spectral features onboard, only features, not raw 10 kHz stream, transmitted reducing energy 97%, system operates 7 years on coin cell battery versus 3 months with raw data transmission, enabling dense sensor networks on rotating machinery where wiring proves impossible. Backscatter communication eliminates radio transmission energy, reflecting ambient RF signals, Wi-Fi, TV, to encode data, WISP tags communicating at 1 kbps using 10 W versus 10 milliwatts for conventional radios, University of Washington sensor dust communicating via backscatter from ambient TV signals achieving 10-meter range with solar harvesting. Smart packaging employs backscatter, NFC tags on pharmaceutical bottles backscattering smartphone RF to report temperature excursions during shipping, system detected 12% of shipments exceeding 8 degrees Celsius threshold causing drug degradation, critical for vaccine cold chain monitoring where spoilage costs $35 billion annually. These energy techniques transform IoT from battery-limited novelty into perpetual sensing infrastructure, enabling deployments in previously inaccessible environments, inside concrete structures, implanted medical devices, deep ocean, where maintenance proves impossible while respecting sustainability constraints essential for planetary-scale sensor networks where billions of devices must operate without environmental burden. Real-world IoT applications span domains transforming industries through physical-digital integration, smart cities optimizing resource allocation through real-time sensing, precision agriculture maximizing yield while minimizing inputs, industrial IoT achieving zero downtime manufacturing, connected healthcare enabling proactive interventions, and environmental monitoring protecting ecosystems through continuous observation. Smart cities leverage IoT for urban efficiency. Barcelona's smart water system employs 20,000 sensors monitoring pressure, flow, and quality across 4,000 kilometers of pipes. Edge analytics detect leaks within 4 minutes, reducing water loss 25%, saving 55 million liters daily. Adaptive irrigation adjusts park watering based on soil moisture and weather forecasts, reducing consumption 30%. Integrated traffic management synchronizes 460 traffic lights using real-time flow data, reducing congestion 21% and emissions 35%, demonstrating IoT's role in sustainable urbanization where resource constraints demand intelligent allocation. Precision agriculture optimizes inputs through hyperlocal sensing. John Deere's Operations Center integrates data from 500,000 connected machines, 10 million soil sensors, and satellite imagery. Variable rate technology adjusts seed, planting depth based on real-time soil conditions. System increased corn yield 8% while reducing nitrogen application 15% across 10 million acres, critical for feeding growing population while minimizing environmental impact where agriculture consumes 70% of global freshwater and contributes 24% of greenhouse gases. Industrial IoT achieves predictive maintenance and quality assurance. Siemens Amberg Electronics plant employs 1,200 robots with 10,000+ sensors monitoring every assembly step. Edge AI detects microscopic solder defects invisible to human inspectors, achieving 99.99885% quality rate. Digital twin simulates production changes before physical implementation, reducing changeover time 40%. system produces 17 million PLCs annually with near-zero defects while reducing energy consumption 23%. Exemplifying Industry 4.0 where physical production and digital representation converge. Connected healthcare enables remote patient monitoring and early intervention. Medtronic's Guardian Connect CGM continuously monitors glucose transmitting alerts when levels trend toward hypoglycemia. System reduced severe hypoglycemia events 72% in clinical trials by enabling preemptive carbohydrate intake, integrated with insulin pumps for automated dosing. Hybrid closed-loop systems, improving time in range 35%, transforming diabetes management from reactive fingersticks to proactive. Physiological regulation. Environmental monitoring protects ecosystems through continuous observation. The Ocean Cleanup System 002 employs IoT sensors on floating barriers monitoring plastic concentration, ocean currents, and structural loads. Real-time data optimizes barrier positioning, capturing 28,000 kilograms of plastic monthly from Great Pacific Garbage Patch. Acoustic sensors detect marine mammal presence, triggering automatic shutdowns, preventing harm, demonstrating IoT's role in planetary stewardship where continuous sensing enables intervention before irreversible damage occurs. Supply chain visibility transforms logistics through end-to-end tracking. Maersk's remote container management employs IoT sensors monitoring location, temperature, humidity, and shock across 380,000 refrigerated containers. Real-time alerts trigger interventions when conditions deviate, e.g., temperature excursions during vaccine transport. System reduced spoilage 50% while providing customers with precise arrival predictions, improving inventory planning, critical for global trade where 30% of food spoils before consumption and pharmaceuticals require strict environmental controls. These applications share common success factors: sensor placement informed by domain expertise, not just technical feasibility; edge intelligence minimizing cloud dependency; human-centered design ensuring alerts drive actionable responses; interoperability across vendor ecosystems; and business models aligning technology investment with measurable ROI, water saved, downtime avoided, yield increased. Failures occur when these factors neglected. Smart city projects deploying sensors without maintenance plans leading to 60% failure rate within 2 years. Agricultural IoT systems generating data without farmer-friendly interfaces causing abandonment. Industrial deployments ignoring cybersecurity resulting in ransomware attacks halting production. Highlighting necessity of holistic systems engineering where technology integrates with human workflows, business processes, and physical constraints, rather than existing as isolated technical artifacts. IoT thus functions as nervous system for physical world, extending intelligence into environments, objects, and processes, enabling responsive adaptation to changing conditions while respecting constraints of power, bandwidth, security, and human values essential for sustainable integration of digital intelligence into physical reality. Slide 23, AI.718, Virtual Reality. Virtual reality transforms artificial intelligence development from abstract algorithm design into embodied experience, creating immersive simulated environments where intelligent agents train safely before physical deployment. Engineers prototype human-robot interactions without costly hardware iterations, and perception systems learn from photorealistic synthetic data impossible to collect physically. Unlike entertainment-focused VR prioritizing visual spectacle alone, AI, robotics VR demands physical accuracy where simulated sensor outputs must match real-world physics to enable reliable sim-to-real transfer. NVIDIA Isaac Sim renders warehouse environments with physically-based materials while simultaneously generating synthetic camera images, depth maps, LiDAR point clouds, and IMU readings matching real sensor characteristics within 5% error, enabling robots to train for 10,000 virtual hours before physical deployment with 85% success rate on first real-world attempt. This physical fidelity requirement transforms VR from artistic tool into engineering infrastructure where material reflectance properties, sensor noise models, and lighting physics must be mathematically precise rather than visually plausible. Waymo's Kala simulator generates 10 million photorealistic driving miles daily, modeling spectral response of automotive cameras, 400 to 1100 nanometers range, LiDAR pulse characteristics, 905 nanometers wavelength, 100 m range, and radar Doppler effects enabling perception systems to train on rare edge cases, emergency vehicles with unusual light patterns, construction zones with temporary signage, impossible to collect safely in physical testing. These applications reveal VR as critical force multiplier, accelerating AI development cycles by orders of magnitude, enabling safe exploration of failure modes, and reducing physical testing costs while maintaining fidelity sufficient for real-world transfer essential for safety-critical autonomy where rare edge cases determine system reliability. VR hardware architectures balance immersion against computational constraints, tracking systems establishing precise 6° of freedom, 6DOF, pose estimation, displays delivering high-resolution imagery at motion sickness preventing refresh rates, and haptic interfaces conveying force feedback essential for manipulation tasks. Inside-out tracking employs stereo cameras on headset estimating position through visual inertial odometry. MetaQuest 3 achieves 90 Hz tracking with less than 2 mm positional accuracy using for grayscale cameras and IMU fusion. Drift correction through SLAM maintains stability during extended sessions critical for industrial training where positional accuracy determines task fidelity. Outside-in tracking uses external base stations emitting infrared patterns. Valve Index employs two Lighthouse 2.0 base stations sweeping 120 degrees laser planes. Photodiodes on headset measure time of arrival computing pose with less than 1 mm accuracy at 1000 Hz update rate essential for surgical simulation where sub-millimeter precision determines clinical validity. Display technologies address vergence accommodation conflict causing visual fatigue. Varifocal displays dynamically adjusting focal plane through liquid lenses. Facebook Half Dome 3, light field displays presenting multiple focal planes simultaneously. Lemnis Technologies, foveated rendering leveraging eye tracking. Tobii, rendering high resolution only in gaze direction reducing GPU load 70% critical for mobile VR where thermal constraints limit sustained performance. Haptic feedback systems convey physical interaction through multiple modalities. Vibrotactile actuators, voice coils, simulating surface textures through frequency-modulated vibrations. Kinesthetic devices, exoskeletons, constraining finger motion to simulate object rigidity. Ultrasonic phased arrays creating mid-air tactile sensations through focused acoustic radiation pressure. Boston Dynamics teleoperation system employs haptic feedback gloves. Tesla suit gloves with 16 force sensors per hand convey contact forces during remote manipulation. System reduced task completion time 47% versus visual-only feedback by enabling delicate operations, turning valves, handling fragile objects. Impossible without force sensation critical for disaster response where robots operate in environments too dangerous for humans. These hardware capabilities transform VR from visual novelty into physically grounded interface, enabling embodied interaction where users manipulate virtual objects with natural hand motions while receiving force feedback matching real-world physics essential for training complex motor skills and prototyping physical interactions before hardware implementation. Rendering pipelines for AI, Robotics VR prioritize sensor accuracy over visual beauty, generating physically correct outputs for cameras, LiDAR, and radar rather than human-pleasing imagery through specialized rendering paths and noise injection matching real sensor characteristics. Ray tracing simulates light transport by tracing paths from virtual sensors through scene. Primary rays determine visibility, shadow rays test occlusion, reflection, refraction rays compute mirror-like effects. NVIDIA RTX hardware accelerates ray tracing through dedicated RT cores performing bounding volume hierarchy, BVH, traversal at 10 plus billion rays second, enabling real-time ray-traced shadows and ambient occlusion in simulation environments. Waymo employs hybrid rendering combining rasterization for primary visibility with ray-traced shadows and ambient occlusion, achieving physically accurate lighting for perception training while maintaining 30 FPS on data center GPUs. Ray-traced shadows improved pedestrian detection accuracy 7.3% under complex lighting, dappled sunlight through trees, versus rasterized shadows by modeling soft penumbra regions critical for depth perception where shadows provide crucial monocular depth cues. Sensor-specific rendering paths generate outputs matching real hardware, camera rendering models lens distortion, Brown-Conradi model, chromatic aberration, motion blur from exposure time, rolling shutter effects. LiDAR rendering simulates pulse characteristics, wavelength, divergence angle, multiple returns from semi-transparent surfaces, noise from ambient light. Radar rendering models Doppler shift, multipath reflections, resolution limits. Tesla's vision training employs physically-based sensor simulation, Camera model includes Sony IMX390 characteristics, 120 dB HDR, 2.1 micrometers pixels. LiDAR model matches Velodyne Alpha Prime, 128 beams, 300 m range. Radar model matches Continental 540 Argentine pesos, 77 GHz, 0.1 degrees azimuth resolution. Perception networks trained on this synthetic data achieved 94% transfer accuracy to physical sensors versus 67% for non-physical-based simulation, demonstrating that sensor fidelity determines sim-to-real success. More than visual photorealism. Noise injection matches real sensor imperfections, Gaussian noise for camera red noise, Poisson noise for photon shot noise, salt and pepper noise for LiDAR dropouts, temporal noise for IMU drift. Agricultural robotics employs noise injection for robust training. John Deere's simulation adds realistic motion blur from tractor vibration, lens flare from low-angle sun, and LiDAR attenuation from dust clouds. System improved real-world weed detection 29% under adverse conditions versus training on clean synthetic data by exposing networks to sensor imperfections encountered in field operations. These rendering techniques transform VR from visual simulator into sensor simulator, generating training data with physical fidelity sufficient for direct deployment while enabling safe exploration of sensor failure modes, camera occlusion, LiDAR attenuation, impossible to test physically without risking system failure. Embodied AI training leverages VR's safety for high-risk exploration. Reinforcement learning agents practice dynamic locomotion, contact-rich manipulation, and failure recovery with unlimited trials without damaging physical hardware or endangering humans. Domain randomization systematically varies visual and dynamic properties during training, randomizing lighting, direction, intensity, color temperature, materials, roughness, metallic, albedo, textures, procedural patterns, object poses, physics parameters, friction coefficients 0.3 to 1.2, mass distributions plus or minus 30%, damping ratios, to train policies invariant to appearance and dynamics variations. Boston Dynamics trained Atlas robots park our policy entirely in VR through domain randomization, 200 years of simulated experience learning dynamic balance, gap jumps, and backflips. Policies exposed to randomized friction coefficients prevented catastrophic failures when encountering unexpected surfaces, wet concrete, loose gravel. Sim-to-real transfer achieved 92% success rate on physical robot versus 42% without domain randomization, demonstrating that visual and dynamic diversity during training proves more critical than photorealism for transfer success. Curriculum learning structures training progression from simple to complex tasks. Initial phases training on flat terrain with perfect perception, intermediate phases introducing mild slopes and partial occlusions, final phases incorporating dynamic obstacles and sensor noise. NVIDIA's dexterous manipulation system employed curriculum learning. Phase 1, grasping static cubes on clean tables. Phase 2, grasping diverse objects with partial occlusions. Phase 3, manipulating deformable objects, ropes, cloths. Phase 4, tool use, using hook to retrieve distant objects. System achieved 85% success rate on physical robot after simulation-only training by gradually increasing task complexity, preventing policy collapse during early learning stages. Self-supervised exploration enables agents to discover useful skills without explicit rewards. Curiosity-driven exploration maximizing prediction error of forward dynamics model. Empowerment maximizing influence over future states. Play-based exploration interacting with objects to discover affordances. MIT's learning from play approach has robots interact with 200+ household objects in VR, building internal models of object affordances and dynamics. Policies trained through self-supervised play transfer to physical robots with 3x faster adaptation to novel manipulation tasks versus pure reinforcement learning, demonstrating that intrinsic motivation generates reusable skills beyond task-specific optimization. Adversarial environment generation discovers failure modes through optimization, generating scenarios that maximize probability of system failure through gradient-based search or evolutionary algorithms. NVIDIA's Drive constellation employs adversarial generation, genetic algorithms evolving scenarios causing perception failures, e.g., adversarial textures on road surfaces causing lane detection failure. System discovered 237 critical failure modes missed by random testing, enabling targeted retraining that reduced failure rates 68%. transforming VR from passive training ground into active stress testing infrastructure essential for safety validation. These training methodologies transform VR from visualization tool into AI development accelerator, enabling sample-efficient learning through structured curricula, robust policies through domain randomization, and comprehensive safety validation through adversarial testing essential for deploying autonomous systems where physical trial costs prove prohibitive. Teleoperation interfaces use VR for intuitive robot control, operators wearing headsets seeing robots' first-person view with virtual control handles mapped to robot arms, enabling spatially natural interaction impossible through traditional joysticks or keyboard commands. First-person perspective provides egocentric viewpoint matching human spatial reasoning. Operator sees environment from robot's eye height with natural depth perception through stereoscopic rendering, and controllers mapped to robot end effectors enable direct manipulation where moving virtual hand moves robot hand identically. NASA's Robonaut 2 teleoperation on ISS employs first-person VR interface. Astronauts control robot performing external maintenance through Oculus Rift headset with touch controllers. System reduced task completion time 47% versus traditional joystick interface by leveraging spatial intuition critical for complex tasks in microgravity where physical access proves impossible and traditional interfaces lack depth cues essential for precise manipulation. Shared autonomy blends human direction with robot intelligence. Human provides high-level goals, move that box, robot handles low-level execution, path planning, collision avoidance, grasp synthesis. VR interface visualizes robots' intent through motion previews and uncertainty visualization. Boston Dynamics stretch warehouse robot employs shared autonomy teleoperation. Operator wears HoloLens 2 seeing holographic handles overlaid on physical environment, pulling virtual handle commands robot to grasp nearby object. Robot autonomously plans collision-free trajectory and executes grasp. System reduced teleoperation cognitive load 63% versus full manual control while maintaining human oversight for safety-critical decisions. Haptic feedback conveys physical interaction forces. Force feedback gloves transmitting contact forces from robot end effectors. Kinesthetic exoskeletons constraining hand motion to simulate object rigidity. Vibrotactile arrays simulating surface textures through frequency-modulated vibrations. Intuitive Surgical's Da Vinci research system employs haptic teleoperation. Force sensors on instrument tips measure tissue interaction forces. Haptic feedback gloves convey forces to surgeons' hands with 1 kHz update rate. System enabled delicate suturing tasks impossible with visual-only feedback by restoring tactile sensation lost in conventional teleoperation. Critical for microsurgery where tissue compliance determines suture tension and wound healing. Time delay compensation addresses communication latency in remote operations. Predictive displays showing robots' anticipated state during signal transit. Local force reflection maintaining stability during delay. Wave variables ensuring passivity despite latency. Underwater robotics employs time delay compensation. WHOI's Nereus ROV operated from surface ship with 2-second round-trip latency. Predictive display showed robots' anticipated position based on last command. System maintained stable manipulation despite latency that would cause instability in conventional teleoperation. Essential for deep-sea operations where radio signals cannot penetrate water requiring acoustic communication with inherent delays. These teleoperation capabilities transform VR from entertainment medium into remote presence infrastructure, enabling humans to operate robots in hazardous environments, nuclear facilities, disaster zones, space, with intuitive spatial control and force feedback essential for complex manipulation tasks where traditional interfaces prove inadequate. VR prototyping accelerates human-robot interaction design through rapid iteration, testing interaction concepts in virtual environments before physical implementation, measuring human responses quantitatively, and refining designs based on empirical data rather than intuition alone. Interaction concept validation tests feasibility of proposed interaction modalities, gesture vocabularies for robot control, spatial arrangements of collaborative workspaces, signaling methods for robot intent communication. BMW's HRI lab employs VR prototyping collaborative assembly scenarios, testing 50+ interaction variants, handover distances, motion speeds, signaling methods, in 2 weeks versus 6 months for physical prototyping. VR testing identified optimal handover distance, 60 centimeters, reducing errors 37% versus intuitive guesses. demonstrating VR's value in exploring design space impossible to cover physically due to time and cost constraints. Trust calibration measurement quantifies human trust evolution during interaction, subjective measures, NASA TLX trust subscale, behavioral measures, time until human intervention during robot operation, physiological measures, heart rate variability during robot errors. Diligent Robotics employs VR trust studies for Morshi Hospital robot. Participants interact with virtual robot performing delivery tasks, trust measured through intervention timing when robot makes errors. Study revealed that transparent error explanations reduced physiological stress 34% versus silent recovery even when task performance identical. Insights directly informed robots' error recovery behavior, improving real-world acceptance 28%. Cognitive load assessment identifies interaction designs overwhelming human attention. Dual task paradigms measuring performance degradation when secondary task added. Pupillometry tracking pupil dilation as cognitive load indicator. EEG measuring prefrontal cortex activity. Airbus employs VR cognitive load studies for aircraft assembly collaboration, measuring technician performance while collaborating with virtual robot. Identified that simultaneous visual and auditory alerts increased cognitive load 47% versus sequential alerts. Redesigned interface reduced errors 31% in physical deployment by avoiding attentional overload during complex assembly tasks. Social acceptance evaluation measures comfort with robot behaviors, proximity maintenance, distance humans maintain from robot, gaze patterns, duration and frequency of eye contact, verbal accommodation, mirroring robot speech rate. SoftBank Robotics employs VR social acceptance studies for Pepper robot. Participants interact with virtual Pepper in retail scenarios. Measurements revealed that bowing gestures increased customer satisfaction 27% in Japanese contexts but decreased satisfaction 18% in German contexts. Insights enabled cultural adaptation of robot behavior before costly physical deployment across international markets. These prototyping capabilities transform HRI design from intuition-driven to evidence-based, enabling rapid exploration of design alternatives, quantitative measurement of human responses, and data-driven refinement essential for creating interactions that feel natural, build appropriate trust, and respect human cognitive limits in collaborative environments. Synthetic data generation leverages VR's controllability to create labeled training data at unprecedented scale, addressing critical bottleneck where manual annotation proves expensive, time-consuming, and impossible for rare edge cases requiring physical danger to capture. Procedural content generation creates infinite variations through algorithmic rules, L systems generating plant geometry through recursive string rewriting, wave function collapse generating coherent layouts from example tiles, noise functions, Palin, Whirly, creating natural patterns, terrain, clouds, marble. NVIDIA's DriveSim employs procedural generation for urban environments, generating 10,000 plus unique city blocks with varied architecture, signage, and vegetation through grammar-based rules. System created 100,000 kilometers of drivable roads in 24 hours versus 6 months for manual creation, enabling comprehensive testing of edge cases, construction zones, unusual intersections, impossible to capture physically. Domain randomization for data augmentation systematically varies visual properties during rendering, randomizing lighting, 10,000 configurations, materials, 1 million procedurally generated BRDFs, textures, image-based with random color shifts, camera parameters, FOV, noise, motion blur, to train perception networks invariant to appearance variations. NVIDIA's robot grasping system employed domain randomization training on 500,000 synthetic images with randomized backgrounds, lighting, and object appearances, achieved 85% success rate on physical robot handling novel objects without fine-tuning. System outperformed networks trained on 100,000 real images, 67% success, by learning robust features invariant to appearance variations, demonstrating that diversity of training data often proves more valuable than photorealism alone. Physics-based augmentation simulates sensor effects impossible to capture consistently physically, motion blur from ego motion at varying speeds, depth noise patterns matching specific LiDAR models, lens flare under low-angle sun, raindrop accumulation on camera lenses with refraction effects. Tesla employs physics-based augmentation for adverse weather training, simulating raindrop accumulation on 8 camera lenses with distortion effects, snow accumulation on roads altering appearance, fog scattering reducing contrast, System improved pedestrian detection recall by 29% in adverse weather versus training on clear-day data alone by exposing networks to realistic weather variations impossible to collect comprehensively physically due to safety constraints and seasonal limitations. Adversarial domain adaptation aligns synthetic and real feature distributions, GANs mapping synthetic images to real appearance while preserving semantic content, cycle-consistent loss ensuring bidirectional mapping preserves information. Tesla employs adversarial domain adaptation training perception networks. Cycle GAN translates synthetic night driving images to realistic appearance while preserving lane geometry. System reduced domain gap from 42% to 8% error difference between synthetic and real evaluation, enabling safe deployment after synthetic-only training. Critical for scaling autonomous driving to global markets where physical data collection proves prohibitively expensive and time-consuming. These synthetic data techniques transform VR from visualization tool into data generation engine, enabling AI systems to train on diverse, labeled data at scales impossible through manual collection while maintaining fidelity sufficient for real-world deployment, critical for safety-critical applications where rare edge cases determine system reliability and physical data collection proves dangerous or impractical. Presence theory provides scientific foundation for VR effectiveness, explaining why users respond to virtual environments as if real through psychological and physiological mechanisms essential for designing credible training simulations and interaction experiences. Spatial presence describes feeling, being there in virtual environment, mediated by sensory fidelity, visual, auditory, haptic, tracking accuracy, latency less than 20 milliseconds prevents simulator sickness, and interaction naturalness, direct manipulation versus abstract controls. Medical training simulations leverage spatial presence. Also, VR surgical training platform achieves 230% improvement in procedure completion time versus traditional methods by creating strong spatial presence through accurate instrument models, realistic tissue deformation, and natural hand motions. Presence enables procedural memory formation as if performing real surgery, critical for skill transfer to operating room. Social presence describes feeling others are present and responsive, mediated by avatar fidelity, especially eyes and hands, behavioral responsiveness, gaze following, gesture mirroring, and conversational naturalness, turn-taking, back-channeling. Collaborative robotics training leverages social presence. Virtual human co-workers in VR assembly simulations respond to trainee actions with appropriate social cues, nodding when task completed correctly, pointing when error detected. Trainees showed 34% better retention of safety protocols versus non-social VR training by engaging social cognition pathways that enhance memory encoding, demonstrating that social presence transforms training from mechanical repetition to socially situated learning. Embodied presence describes feeling virtual body as one's own, mediated by visuomotor synchrony, virtual hand moves with real hand, visuotactile synchrony, seeing touch coincides with feeling touch, and first-person perspective. Rehabilitation robotics leverages embodied presence. Stroke patients training arm movements in VR with virtual arm moving synchronously with impaired limb. Embodiment illusion increased motor cortex activation 47% versus non-embodied training, accelerating neuroplasticity and recovery, demonstrating that presence mechanisms directly influence physiological processes essential for therapeutic applications. Breaks in presence, BIPs, disrupt immersion and reduce training effectiveness. Tracking latency greater than 20 milliseconds causes motion blur, breaking spatial presence. Avatar gaze not following user breaks social presence. Virtual hand not matching real hand position breaks embodied presence. Industrial training programs employ BIP monitoring, measuring simulator sickness symptoms, nausea, disorientation, and presence questionnaires after sessions. Sessions with BIPs greater than 30% show 62% lower skill transfer to physical tasks, guiding hardware upgrades, faster tracking, higher refresh rates, and content design, smoother motion profiles, to maintain presence essential for effective training transfer. These presence mechanisms transform VR from visual display into experiential medium, enabling training, therapy, and collaboration experiences that engage human perceptual, social, and motor systems as if real, essential for applications where psychological fidelity determines effectiveness as much as technical accuracy. VR for autonomous systems validation addresses critical challenge of rare edge case collection, using procedural generation and scenario variation to create training and testing data for events too dangerous or improbable to capture physically while maintaining physical plausibility. Scenario description languages formally specify driving situations. Open scenario defines actors, trajectories, weather, and road conditions through XML. ASAM Open Drive describes HD maps with lane topology and traffic rules. Combined enable reproducible scenario generation. Waymo employs scenario description languages creating 100,000 plus edge cases daily, phantom jaywalkers emerging from between double-parked cars at night, emergency vehicles with unusual configurations, construction zones with temporary signage, testing perception and planning responses before physical deployment. System discovered 47 critical failure modes in simulation that would have caused collisions in physical testing, demonstrating VR's value in proactive safety validation impossible through physical testing alone due to ethical and practical constraints. Adversarial scenario generation discovers failure modes through optimization, generating scenarios that maximize probability of system failure through gradient-based search on differentiable simulators or evolutionary algorithms on black box simulators. NVIDIA's Drive Constellation employs adversarial generation, genetic algorithms evolving scenarios causing perception failures, e.g., adversarial textures on road surfaces causing lane detection failure. System discovered 237 critical failure modes missed by random testing, enabling targeted retraining that reduced failure rates 68%, transforming VR from passive testing ground into active vulnerability discovery infrastructure essential for safety certification. Weather and lighting simulation models atmospheric effects physically. Pritham Sky model simulating daylight based on sun position, turbidity, Brunton atmospheric scattering modeling aerial perspective and horizon colors, real-time rain, snow through particle systems with wetness maps altering surface reflectance. Tesla's Vision training employs physically-based weather simulation, modeling raindrop accumulation on camera lenses with distortion effects, snow accumulation on roads altering appearance, fog scattering reducing contrast. System improved pedestrian detection recall by 29% in adverse weather versus training on clear-day data alone by exposing networks to realistic weather variations impossible to collect comprehensively physically due to safety constraints and seasonal limitations. Sensor failure simulation tests robustness to degraded perception, camera occlusion, mud splatter, condensation, lidar attenuation, heavy rain, fog, GPS denial, urban canyons, tunnels, IMU drift during extended operation. Autonomous vehicle developers employ sensor failure simulation, testing planning systems under partial perception degradation. System learned fallback behaviors like reducing speed and increasing following distance when camera confidence drops below threshold. Validation showed 94% of scenarios maintained safe operation under single sensor failures versus 67% for systems without explicit failure training, critical for safety cases required by regulators where fault tolerance proves mandatory. These validation capabilities transform VR from development convenience into safety necessity, enabling comprehensive testing of rare events, adversarial conditions, and failure modes at scales impossible physically while maintaining physical plausibility sufficient for regulatory acceptance. Essential for autonomous systems where safety certification requires evidence of performance under conditions too dangerous to test physically. Challenges and limitations demand engineering solutions beyond hardware improvements. Latency constraints requiring less than 20 milliseconds motion-to-photon delay to prevent simulator sickness, realism gap between simulation physics and real-world complexity causing sim-to-real transfer failures, cyber sickness affecting 40 to 70% of users limiting session duration, computational costs of photorealistic rendering limiting accessibility. Latency optimization employs multiple strategies, time warp reprojection generating intermediate frames when rendering misses deadline, asynchronous space warp predicting head motion during frame generation, foveated rendering reducing peripheral resolution where acuity lower, predictive tracking extrapolating head pose using Kalman filters. Industrial training applications employ latency optimization. Boeing's VR aircraft assembly training maintains less than 15 milliseconds latency through time warp and predictive tracking, reduced simulator sickness incidence from 68% to 23%, enabling 45-minute training sessions versus 15-minute sessions with higher latency, critical for skill acquisition requiring extended practice. Domain randomization bridges realism gap by training policies on diverse variations rather than perfect simulation, randomizing physics parameters, friction coefficients plus or minus 30%, mass distributions plus or minus 20%, damping ratios plus or minus 40%. During training forces policies to learn robust strategies rather than exploiting simulation artifacts. Boston Dynamics sim-to-real transfer employs aggressive domain randomization, training locomotion policies on 1,000+ physics parameter combinations. Policies learn to rely on proprioceptive feedback rather than perfect vision, achieved 92% transfer success versus 42% without randomization, demonstrating that diversity often proves more valuable than fidelity for transfer success. Cyber sickness mitigation employs multiple approaches: comfort modes limiting field of view during movement, teleportation versus smooth locomotion, dynamic vignetting reducing peripheral motion, habituation protocols gradually increasing exposure duration. Medical VR training employs cyber sickness mitigation. Also, VR surgical training uses teleportation for navigation between procedure stations combined with vignetting during tool movements, reduced sickness incidence from 58% to 12%, enabling 30-minute training sessions sufficient for procedural skill acquisition, critical for clinical adoption where session duration determines training efficacy. Computational efficiency techniques enable accessible VR, cloud rendering streaming pre-rendered frames to lightweight headsets, neural rendering using GANs to generate high-fidelity imagery from low-fidelity inputs, level of detail systems dynamically adjusting geometric complexity based on distance and importance. Educational VR applications employ computational efficiency. Labster's virtual science labs use cloud rendering enabling photorealistic lab environments on $300 standalone headsets. 500,000 plus students access lab experiences impossible physically due to cost or safety constraints, demonstrating that accessibility through efficiency expands VR's societal impact beyond high-end applications. These engineering solutions transform VR from niche technology into practical tool, addressing physiological constraints, latency, sickness, physical constraints, realism gap, and economic constraints, computational cost, essential for widespread adoption across education, training, healthcare, and industry where accessibility determines real-world impact. Emerging frontiers push VR toward greater integration with AI and physical reality, neural rendering enabling photorealistic generation from semantic descriptions, differentiable graphics allowing end-to-end training of vision systems, mixed reality blending virtual and physical spaces for enhanced interaction, and neuromorphic VR mimicking biological vision for ultra-low power operation. Neural radiance fields, NERFs, represent scenes as continuous volumetric functions, multilayer perceptron mapping 5D coordinates, x, y, z, theta, phi, to volume density and view-dependent color. Differentiable rendering enables optimization from posed images through gradient descent. Google's Instant NGP accelerated NERF training 1000x through hashgrid encoding, multi-resolution hash tables storing feature vectors at grid vertices, trilinear interpolation retrieves features for arbitrary coordinates, combined with tiny MLPs enables training in seconds rather than hours. Real-world NERF deployments span domains. Visual effects. Wetter FX employs Instant NGP creating photorealistic digital doubles for avatar sequels reducing actor reshoots by 40%. Robotics. NVIDIA's VMware framework employs NERFs for tabletop manipulation. Robots build scene representations from 3 to 5 images then plan grasps in continuous 3D space achieving 92% success rate on novel objects without CAD models. Autonomous vehicles. Tesla employs NERFs for occupancy prediction, modeling static scene geometry, then predicting dynamic object trajectories through residual fields enabling 3-second future prediction with 89% accuracy at 2-second horizon critical for avoiding jaywalkers. Differentiable rendering bridges graphics and vision, enabling gradients to flow from pixel space back to scene parameters, geometry, materials, lighting, allows end-to-end training where rendering parameters become trainable variables. NVIDIA's Kerlin library employs differentiable rasterization for 3D reconstruction, optimizing mesh vertices to match target images through gradient descent, system reconstructed 3D objects from single images with 94% accuracy versus 76% for non-differentiable methods by enabling end-to-end learning of shape parameters, critical for inverse graphics applications where recovering scene properties from images proves essential for robotics perception. Mixed reality blends virtual content with physical environment through pass-through cameras and depth sensing, Meta Quest Pro's color pass-through enables awareness of physical surroundings while immersed. Depth sensors reconstruct environment geometry for occlusion handling and spatial anchoring. Surgical robotics employs mixed reality for procedure planning. Surgeons wear pass-through VR headset viewing patient CT scans as holograms overlaid on physical anatomy during preoperative planning. System-enabled precise tumor resection planning with 3 mm accuracy versus 8 mm for traditional methods by visualizing tumor margins in situ. Intraoperative guidance projected critical structures, nerves, blood vessels, onto surgical field reducing complications 27%, demonstrating MR's value in enhancing rather than replacing physical reality for critical tasks. Neuromorphic VR mimics biological vision processing, event cameras capturing asynchronous pixel-level changes with microsecond resolution, spiking neural networks processing events with ultra-low power, eliminates motion blur and latency inherent in frame-based rendering. Prophecy's event-based VR prototype achieves less than 1 millisecond latency versus 20 milliseconds for conventional VR, critical for applications requiring precise hand-eye coordination like microsurgery training where latency causes performance degradation. Power consumption 100x lower, enabling all-day operation on mobile headsets, essential for field applications where battery life determines usability. These emerging approaches address core limitations: photorealism through neural methods, training efficiency through differentiable pipelines, contextual relevance through mixed reality, and accessibility through neuromorphic processing, pointing toward next generation of VR that integrates seamlessly with AI development workflows and physical environments while operating efficiently under real-world constraints of power, latency, and human physiology, essential for embodied intelligence operating reliably in complex, dynamic environments where simulation fidelity and physical interaction determine system capabilities. Slide 24, AI.719, Augmented Reality. Augmented reality bridges digital intelligence with physical reality through spatial computing, overlaying context-aware digital information onto the physical world in precise alignment with real objects, surfaces, and spatial relationships to enhance human perception, decision-making, and interaction without replacing physical context. Unlike virtual reality's complete immersion or mixed reality spectrum blending, AR maintains primary focus on the physical environment while augmenting it with just-in-time information, guidance, or interactive elements precisely registered to physical space through 6 degrees of freedom tracking and environmental understanding. Microsoft HoloLens 2 exemplifies enterprise AR, optical waveguides projecting holograms onto physical environment with 2 mm accuracy at 2 meter distance, hand tracking recognizing pinch gestures without controllers, eye tracking enabling foveated rendering and gaze-based interaction, spatial anchors persisting holograms across sessions enabling multi-user collaboration on physical assemblies. Boeing's aircraft wiring harness assembly employs HoloLens 2. Technicians see holographic wire routing diagrams overlaid directly onto physical fuselage with 2 mm registration accuracy. System reduced wiring errors 47% and assembly time 30% by eliminating constant reference to paper manuals and mental translation between 2D diagrams and 3D structures, demonstrating AR's value in complex physical tasks where cognitive load from context switching causes errors. This spatial intelligence transforms AR from novelty display into cognitive prosthesis, extending human perception and memory into physical environments where information relevance depends on precise spatial context, essential for manufacturing, maintenance, surgery, and field operations where decisions require integration of digital knowledge with physical reality. AR hardware architectures balance optical fidelity, mobility, and interaction naturalness. Optical see-through, OST, devices projecting light onto transparent waveguides preserving direct view of physical world. Video see-through, VST, devices capturing environment through cameras then compositing virtual content onto displays. Spatial computing platforms integrating environmental understanding with persistent digital content. Optical see-through waveguides guide light through total internal reflection, diffractive optical elements, DOS, or holographic optical elements, HOS, extracting light toward eye. Microsoft HoloLens 2 employs custom HOS achieving 52 degrees field of view with 2 angular era critical for precise hologram registration. Magic Leap 2 uses dimming technology adjusting transparency from 0 to 100% enabling use in bright outdoor environments where ambient light washes out holograms. Video see-through systems capture environment through stereo cameras, Meta Quest Pro employs 12MP RGB cameras with global shutter minimizing motion blur, pass-through latency less than 15 milliseconds achieved through dedicated encoding hardware and time warp reprojection critical for preventing simulator sickness during movement. Color calibration matching camera response to display gamut ensuring physical objects appear natural rather than tinted. Spatial computing platforms integrate environmental understanding. Apple Vision Pro employs dual-chip architecture, R1 for sensor processing, M2 for rendering, achieving 12 milliseconds sensor-to-display latency, LiDAR scanner mapping environment geometry at 30 Hz enabling occlusion handling where virtual objects hide behind physical surfaces, hand tracking with 25 joint angles enabling natural manipulation without controllers. Industrial AR hardware prioritizes ruggedness and task integration, RealWear HMT, one head-mounted tablet mounts display below line of sight enabling hands-free operation in hazardous environments, chemical plants, construction sites. Voice-controlled interface operates with gloves and in noisy environments, 95 dB, IP66 rating withstands dust, water immersion critical for field operations where consumer devices fail. These hardware capabilities transform AR from fragile consumer gadget into industrial tool, enabling operation in harsh environments, precise spatial registration essential for technical tasks, and natural interaction preserving human dexterity while augmenting with digital intelligence essential for applications where physical manipulation remains primary but digital guidance determines accuracy and efficiency. Tracking and registration techniques anchor digital content to physical space with sub-centimeter accuracy, marker-based systems using fiducial patterns for robust tracking, markerless systems employing SLAM, simultaneous localization and mapping, for environment understanding, sensor fusion combining cameras, IMUs, and depth sensors for drift-free operation essential for industrial precision. Marker-based tracking uses high-contrast fiducial patterns, AprilTag encoding binary payload in black, white squares enabling sub-pixel corner detection, reprojection error less than 0.1 pixels achievable through sub-pixel refinement, industrial calibration achieving 0.3 mm accuracy at 1 meter distance critical for assembly guidance where misalignment causes fit errors. Volkswagen employs marker-based AR for quality inspection, AprilTags placed on car body panels, tablet camera detects tags then overlays CAD model wireframes, technician verifies panel gaps against tolerance zones, plus or minus 1.5 mm. System reduced inspection time 65% while catching 92% of out-of-tolerance conditions missed by human inspectors relying on feeler gauges alone. Visual inertial odometry, VIO, fuses camera and IMU measurements. IMU provides high-frequency motion estimates between camera frames. Camera corrects IMU drift through visual feature tracking. MSCKF, multi-state constraint Kalman filter, maintains sliding window of camera poses enabling efficient bundle adjustment. Microsoft HoloLens 2 employs VIO with for grayscale tracking cameras and IMU, achieves less than 1 mm drift over 10 meter walks critical for persistent holograms that must remain fixed to physical locations during extended use. Drift compensation through loop closure detecting previously visited locations correcting accumulated error. SLAM algorithms build environment maps while localizing device. ORB, SLAM 3 employs 3-thread architecture. Tracking thread estimates camera pose against local map. Local mapping thread optimizes recent keyframes and points. Loop closing thread detects revisited locations correcting drift through pose graph optimization. Trimble's XR10 hard hat employs SLAM for construction site AR, LiDAR scanner builds 3D map of unfinished building, holographic BIM models overlaid on physical structure showing hidden pipes, wires behind walls. System achieves 5 mm registration accuracy enabling electricians to drill without hitting conduits, critical for safety where errors cause electrocution or structural damage. Sensor fusion architectures combine complementary modalities, Kalman filters optimally weighting camera, accurate but intermittent, an IMU, continuous but drifting, particle filters representing multimodal belief distributions essential for global relocalization after tracking loss. Darkry Smart Helmet employs sensor fusion, stereo cameras, IMU, GPS, and magnetometer fused through extended Kalman filter, maintains tracking during GPS outages in indoor factories. System reduced assembly errors 37% in Boeing 787 production by providing persistent guidance through complex multi-step procedures where workers previously relied on paper manuals causing sequence errors. These tracking capabilities transform AR from unstable novelty into reliable tool, enabling persistent digital content that remains precisely aligned to physical world during extended use, essential for industrial applications where registration accuracy determines task success and safety. Spatial mapping reconstructs 3D environment geometry in real time, enabling occlusion handling where virtual objects hide behind physical surfaces, collision detection for virtual physical interaction, and semantic understanding of environment structure essential for context-aware augmentation. Depth sensing technologies capture environment geometry, structured light projects known patterns, e.g., iPhone Face ID's 30,000 infrared dots, then analyzes distortion, time of flight, 2F, measures light round-trip time. Microsoft Azure Connect, stereo vision computes disparity between calibrated camera pairs. Intel RealSense D for 55. Construction industry employs depth sensing for progress monitoring. Trimble XR10 hard hat scans unfinished building generating point cloud, compares against BIM model identifying deviations greater than 10 mm. System flags structural elements installed out of tolerance before subsequent work conceals errors, reducing rework costs 28% on $500 million projects where late-stage corrections cost 10x more than early detection. Mesh reconstruction converts point clouds to surface representations. Poisson surface reconstruction solving indicator function through Octree, marching cubes extracting ISO surfaces from signed distance fields, real-time meshing on mobile devices through voxel hashing. Microsoft Mesh enables persistent shared environments. Multiple HoloLens 2 devices reconstruct same space then align meshes through cloud anchor sharing, enables remote expert collaboration where specialist sees same holographic annotations as on-site technician, reducing expert travel costs 73% while maintaining 94% first-time fix rate for complex equipment repairs. Semantic segmentation classifies environment elements, deep learning models, mask RCNN, labeling pixels as floor, wall, table, machinery, geometric analysis identifying planar surfaces and dominant orientations, instance segmentation distinguishing individual objects within categories. Siemens employs semantic AR for factory layout planning. Technicians where HoloLens 2 scanning production floor, system segments machinery, conveyors, and workstations, proposes optimal reconfiguration by simulating workflow paths overlaid as holographic arrows, reduced layout planning time from 3 weeks to 2 days while improving material flow efficiency 22%, critical for agile manufacturing responding to demand shifts. Occlusion handling renders virtual objects behind physical surfaces. Depth buffer testing comparing virtual object depth against reconstructed environment depth, temporal filtering smoothing depth discontinuities to prevent flickering, multiplane rendering addressing vergence accommodation conflict by rendering content at multiple focal planes. Medical AR employs occlusion for surgical guidance. Augmetics X-Vision system overlays spinal anatomy from preoperative CT onto patient's back during surgery. Virtual pedicle screws rendered behind skin surface visible only when surgeons drill approaches correct trajectory. System achieved 98.8% screw placement accuracy versus 91.4% for freehand technique, critical for preventing nerve damage where millimeter errors cause paralysis. These spatial mapping capabilities transform AR from floating overlays into integrated spatial experiences, enabling digital content that respects physical world geometry essential for applications where occlusion determines realism, collision detection enables physical interaction, and semantic understanding enables context-aware guidance that adapts to environment structure. Interaction techniques enable natural manipulation of AR content through multimodal input, gaze targeting selecting objects by looking, gesture recognition interpreting hand poses and motions, voice commands for complex operations, haptic feedback confirming interactions, all designed to minimize cognitive load while preserving physical task focus essential for industrial applications. Gaze interaction leverages eye tracking for selection, foveated rendering reducing peripheral resolution where acuity lower, dwell time selection triggering after 500 milliseconds fixation, vergence-based depth selection using eye convergence angle. Airbus employs gaze interaction for aircraft assembly. Technicians wearing Tobii eye tracker select holographic fastener specifications by looking at physical rivet locations. System displays torque values and installation sequence without requiring hand gestures that would interrupt tool handling. Reduced assembly errors 27% by eliminating context switching between tool and interface. Hand tracking recognizes natural gestures without controllers. Media pipe hands tracking 21 3D hand landmarks through palm detection and hand landmark model, pinch gesture, thumb index contact, for selection. balloon gesture, hand opening, for menu activation, grab gesture, fingers closing, for object manipulation. BMW employs hand tracking for collaborative assembly. Technicians guide robot arms by grabbing virtual handles overlaid on physical workspace. System interprets hand motion as desired robot trajectory. Reduced programming time from 4 hours to 15 minutes per task by leveraging spatial intuition rather than abstract coordinate entry. Critical for flexible manufacturing where frequent changeovers demand rapid reprogramming. Voice commands handle complex operations through natural language, automatic speech recognition, ASR, converting audio to text, natural language understanding, NLU, extracting intents and entities, context-aware disambiguation resolving references, move that part there using gaze to resolve that and there. ThyssenKrupp employs voice-controlled AR for elevator maintenance. Technicians wearing RealWear HMT, one-issue commands like show wiring diagram for controller board or log bearing temperature 68 degrees, system accesses service manuals and logs data hands-free in noisy machine rooms where touch interfaces fail, reduced mean time to repair 42% by enabling continuous tool use while accessing information. Haptic feedback confirms interactions through multiple modalities. Ultrasonic phased arrays creating mid-air tactile sensations through focused acoustic radiation pressure, ultrahaptics, vibrotactile actuators in wristbands simulating contact forces, wearable exoskeletons providing kinesthetic resistance. Boeing employs haptic AR for wiring harness assembly. Ultrahaptics array mounted on workstation creates virtual click sensation when technicians hand aligns wire with correct connector pin. System reduced insertion errors 38% by providing immediate tactile confirmation without visual distraction, critical for tasks requiring sustained visual attention on physical work. Multimodal fusion combines complementary channels, Bayesian inference weighting inputs by reliability, gaze precise but ambiguous, gesture unambiguous but fatiguing, conflict resolution through temporal precedence, last input within 2 seconds wins, graceful degradation when channels fail, voice backup when hands occupied. These interaction techniques transform AR from visual overlay into intuitive spatial interface, enabling seamless integration of digital guidance with physical tasks where interaction must not impede primary work essential for industrial adoption where productivity determines ROI. AR for human-robot collaboration creates spatially intuitive interfaces for coordinating physical tasks, visualizing robot intentions before execution, guiding human actions through contextual overlays, and enabling natural handover protocols that leverage spatial reasoning rather than abstract commands. Intention visualization communicates robot plans spatially, projecting planned trajectories as holographic paths showing future positions, highlighting uncertainty bounds as translucent volumes indicating confidence, displaying tool affordances on physical objects showing grasp points or manipulation constraints. BMW's collaborative assembly employs AR intention visualization. Humans and robots jointly position 12-meter wing spars. HoloLens 2 shows robots' planned motion path 3 seconds ahead as blue holographic tube. Red zones highlight areas requiring human verification. System reduced human intervention requests 63% by making robot intentions transparent versus opaque operation where humans couldn't anticipate movements, critical for safety where unexpected robot motions cause startle reactions leading to errors or injuries. Spatial task allocation divides work based on physical constraints. AR interface visualizing optimal division where robot handles heavy lifting, components greater than 15 kilograms, while human performs dexterous operations, connector insertion, dynamic reallocation when conditions change, robot detects unexpected obstacle, AR guides human to assist. Airbus employs spatial task allocation for A350 assembly. AR system analyzes task requirements in real time, assigns robot to position wing spar while human installs fasteners in hard-to-reach areas. System achieves 50% assembly time reduction versus sequential human-then-robot workflow by enabling true parallel collaboration where spatial coordination replaces sequential handoffs. Handover protocols leverage spatial cues for seamless transfer. AR guides optimal handover location, 60 centimeters from human torso, robot-held object oriented for natural grasp, visual cues indicating transfer readiness, holographic pulse when robot stabilized, force feedback through haptic gloves confirming grasp before robot release. QCR employs AR handover protocols in electronics assembly. Human worker receives circuit boards from robot arm. AR projects optimal hand position and orientation. system reduced handover time 47% and dropped parts 82% versus unguided handovers where misalignment caused fumbling, critical for high-speed production where handover delays bottleneck entire line. Shared workspace awareness maintains mutual understanding, AR visualizing robot workspace boundaries as semi-transparent volumes, highlighting human presence within robot workspace triggering speed reduction, displaying robot state, idle, moving, error, through color-coded holograms. Amazon employs shared workspace awareness in warehouse robotics, Proteus robots navigate aisles alongside humans, AR glasses worn by workers display robot intent, green equals path clear, yellow equals approaching, red equals stop. System achieved 99.97% collision-free operation across 5 million deliveries by making robot behavior predictable, essential for scaling human-robot coexistence beyond safety cages. These collaboration capabilities transform AR from display technology into coordination infrastructure, enabling fluid human-robot teamwork that leverages complementary strengths, robot strength, precision, human dexterity, adaptability, through spatially intuitive communication essential for manufacturing, logistics, and healthcare where physical collaboration determines productivity and safety. AR for training and skill transfer accelerates expertise acquisition through contextual guidance, overlaying step-by-step instructions directly onto physical equipment, providing real-time error correction, and enabling remote expert assistance without travel, compressing years of apprenticeship into weeks of guided practice. Procedural guidance overlays instructions spatially aligned with task steps, holographic arrows showing tool insertion direction, animated sequences demonstrating complex motions, textual annotations highlighting critical parameters, torque values, alignment tolerances. Boeing's wire harness training employs AR guidance, apprentices wearing HoloLens 2C holographic routing paths overlaid on physical harness board, system verifies correct wire placement through computer vision before allowing next step. Reduced training time from 12 weeks to 3 weeks while achieving 94% first-time quality versus 72% for traditional training, critical for aerospace where wiring errors cause system failures requiring costly rework. Error detection and correction provides immediate feedback, computer vision analyzing trainee actions in real time, comparing against expert demonstration or CAD model, highlighting deviations with visual cues, red outline for misaligned component, suggesting corrections through animated guidance. Siemens employs AR error correction for turbine assembly. Trainees positioning rotor blades receive immediate feedback when alignment exceeds 0.5 degrees tolerance. System projects corrective arrows showing adjustment direction. Reduced assembly errors 68% versus video-based training where feedback delayed until supervisor inspection. Critical for precision machinery where cumulative errors cause catastrophic failures. Remote expert assistance connects trainees with specialists globally. Expert sees trainees' first-person view through device camera, draws annotations directly onto physical environment visible to trainee, voice communication synchronized with visual guidance. Darkry Smart Helmet enables remote assistance for oil rig maintenance. Technician in North Sea platform shows equipment to Houston-based expert. Expert draws holographic circles around faulty valve and arrows showing disassembly sequence. System reduced mean time to repair 57% while eliminating $40,000 per expert travel costs, critical for remote operations where specialist access determines downtime costs. Performance analytics quantify skill progression, tracking metrics, task completion time, error rates, tool path efficiency, comparing against expert benchmarks, identifying persistent weaknesses for targeted practice. Honeywell employs AR analytics for aircraft maintenance training. System tracks technician hand movements during component replacement, identifies inefficient motions, excessive reaching, repositioning, provides personalized coaching reducing task time 34% over 10 practice sessions, transforming subjective apprenticeship into data-driven skill development. Cognitive load reduction minimizes information overload, progressive disclosure revealing only next step rather than entire procedure, spatial anchoring placing instructions near relevant components rather than centralized display, multimodal redundancy, visual plus audio, accommodating attentional demands during complex tasks. These training capabilities transform AR from passive instruction into active coaching system, accelerating skill acquisition through contextual guidance, immediate feedback, and expert access essential for industries facing skilled labor shortages where training efficiency determines operational continuity and safety. AR for maintenance and repair transforms reactive troubleshooting into guided resolution, overlaying diagnostic data onto physical equipment, visualizing hidden systems through X-ray vision, and providing step-by-step repair procedures aligned with physical components, reducing downtime while preserving institutional knowledge. X-ray vision reveals hidden systems through registered overlays, BIM models overlaid on building walls showing pipe locations, CAD assemblies overlaid on machinery revealing internal components, thermal imaging overlaid on equipment highlighting overheating components. Trimble XR10 enables X-ray vision for construction. Technician scans wall with hard hat-mounted LiDAR. System overlays BIM model showing electrical conduits behind drywall. Technician drills confidently avoiding wires. Prevented 127 electrical shorts during $200 million hospital construction where rework averaged $8,400 per incident. Diagnostic data visualization integrates sensor readings spatially. Vibration spectra overlaid on rotating machinery showing bearing fault frequencies, thermal gradients overlaid on electrical panels highlighting hot spots, pressure readings overlaid on hydraulic systems showing flow restrictions. Siemens employs diagnostic AR for wind turbine maintenance. Technician points tablet at nacelle. System overlays real-time SCADA data. Gearbox temperature 87 degrees Celsius, vibration 4.2 mm per second, directly onto components. Anomaly detection highlights values exceeding thresholds in red. Reduce diagnostic time 63% by eliminating mental correlation between sensor readings and physical locations, critical for remote sites where downtime costs $22,000 per hour. Step-by-step repair guidance aligns instructions with physical components, holographic arrows showing bolt removal sequence, animated disassembly showing component extraction paths, torque specifications overlaid directly on fasteners. ThyssenKrupp employs AR repair guidance for elevator systems. Technician wearing RealWear HMT, 1 sees holographic disassembly sequence overlaid on controller board. System verifies correct component removal through computer vision before allowing next step. Reduced mean time to repair 42% while cutting error-related callback 76%. Critical for service contracts where response time determines customer retention. Knowledge preservation captures expert procedures before retirement. Experts perform tasks while wearing AR glasses recording first-person view with annotations. System generates interactive procedure library accessible to novices. Contextual triggers, recognizing equipment model, automatically loading relevant procedures. Lockheed Martin employs knowledge preservation for F-35 maintenance. Master technicians record complex procedures with AR annotations. System generates 3D interactive manuals where novices see exactly what experts saw during recording. Preserved 94% of tacit knowledge from retiring workforce, critical for defense systems where expertise gaps threaten fleet readiness. Remote collaboration enables expert assistance without travel. Expert sees technician's first-person view, draws annotations directly onto physical environment, shares relevant documentation overlaid spatially. These maintenance capabilities transform AR from information display into diagnostic partner, accelerating troubleshooting through spatial data integration, preventing errors through guided procedures, and preserving expertise through recorded knowledge essential for industries where equipment uptime determines revenue and safety. AR for medical applications enhances surgical precision, procedural training, and patient education through spatially registered guidance, overlaying preoperative plans onto anatomy, visualizing subsurface structures during procedures, and enabling collaborative planning through shared holographic visualizations, improving outcomes while reducing cognitive load on clinicians. Preoperative planning visualizes surgical approach in context, patient CT, MRI scans converted to 3D holograms overlaid on physical anatomy. Surgeons manipulate holograms to plan optimal incision sites and trajectories, collaborative review with team members through shared spatial anchors. Johns Hopkins employs AR preoperative planning for tumor resection. Surgeons wear HoloLens 2 viewing patient's tumor as hologram overlaid on physical anatomy during planning session. System calculates optimal resection margins preserving critical structures. Achieved 3 mm resection accuracy versus 8 mm for traditional methods. Critical for cancer surgery where incomplete resection causes recurrence while excessive resection causes functional deficits. Intraoperative guidance overlays critical information during procedures. Tumor margins highlighted as holographic contours on tissue surface, blood vessels and nerves visualized as semi-transparent structures beneath surface, instrument trajectories previewed before execution. Augmetics X-Vision system provides spinal surgery guidance. Surgeon wears transparent AR headset seeing patient's spine anatomy from preoperative CT overlaid directly onto back. Virtual pedicle screws rendered along planned trajectories. System achieved 98.8% screw placement accuracy versus 91.4% for freehand technique. Critical for preventing nerve damage where millimeter errors cause paralysis. Procedural training accelerates skill acquisition through realistic simulation. Holographic anatomy overlaid on physical mannequins. Real-time feedback on instrument handling and tissue interaction. Progressive difficulty scaling from basic skills to complex procedures. Also, VR employs AR-enhanced surgical training. Trainees perform procedures on physical models while AR overlays provide guidance and feedback. System achieved 230% improvement in procedure completion time versus traditional methods. Critical for addressing surgical training constraints where resident work hour limits reduce hands-on experience. Patient education improves informed consent through spatial understanding. 3D holograms of patients' own anatomy showing condition and proposed treatment. Interactive manipulation allowing patients to explore from multiple angles. Comparison views showing pre-post-treatment states. Cleveland Clinic employs AR patient education for orthopedic surgery. Patients view holographic model of their own knee joint showing torn meniscus. Surgeon manipulates hologram demonstrating repair technique. Improved patient comprehension scores 47% and reduced preoperative anxiety 38%. Critical for informed consent and postoperative compliance. Remote surgical collaboration enables expert guidance without travel. Specialist observes procedure through surgeon's AR headset feed, draws annotations directly onto surgical field visible to surgeon, shares relevant imaging overlaid spatially. These medical applications transform AR from visualization tool into clinical partner, enhancing precision through spatial guidance, accelerating training through realistic simulation, and improving communication through shared spatial understanding essential for procedures where millimeter accuracy determines outcomes and cognitive load affects decision quality. AR for design and prototyping accelerates iteration cycles through spatial visualization, overlaying virtual prototypes onto physical contexts, enabling collaborative review at human scale, and testing ergonomic interactions before physical fabrication, reducing development costs while improving design quality. Spatial prototyping visualizes designs in context, CAD models overlaid on physical environments at 1:1 scale, real-time manipulation through hand gestures adjusting dimensions, material properties simulated through visual shaders, transparency, reflectivity. Ford employs AR spatial prototyping for vehicle design. Designers wear HoloLens 2 viewing virtual car models overlaid in physical studio, manipulate proportions through hand gestures, evaluate aesthetics in real lighting conditions, reduced clay model iterations from 8 to 2 per design cycle saving $280,000 per vehicle program, critical for automotive where physical prototyping costs millions per iteration. Collaborative design review enables geographically distributed teams, shared spatial anchors maintaining persistent holograms across locations, multi-user interaction with avatars representing remote participants, voice communication synchronized with visual annotations. Airbus employs collaborative AR for aircraft interior design. Teams in Toulouse, Hamburg, and Mobile simultaneously review cabin layout through HoloLens 2, manipulate seat arrangements in real time, annotate problematic areas with persistent holographic notes, reduce design review cycles from 3 weeks to 2 days, critical for global programs where travel constraints delay decisions. Ergonomic evaluation tests human interaction before fabrication. Virtual prototypes overlaid on physical mock-ups, motion capture tracking user interactions, reachability analysis highlighting areas requiring excessive stretching, field of view analysis ensuring critical displays visible in natural posture. BMW employs AR ergonomic evaluation for assembly line design. Technicians perform simulated tasks with virtual components overlaid on physical workstations. System tracks joint angles identifying repetitive stress risks. Redesign 27 workstations reducing ergonomic risk scores 41% before physical implementation, critical for preventing workplace injuries where OSHA violations carry significant penalties. Contextual testing validates designs in real environments, architectural models overlaid on construction sites showing scale relationships to surroundings, product designs overlaid in retail environments testing visual appeal and shelf presence. Automotive HUD prototypes overlaid on windshields testing readability under varying lighting. IKEA Place app enables contextual furniture testing. Users point smartphone at room. App overlays true-scale 3D models of furniture. System achieved 98% purchase conversion for users employing AR versus 35% for traditional browsing, demonstrating AR's value in reducing purchase uncertainty through contextual visualization. These design capabilities transform AR from visualization aid into decision accelerator, enabling rapid iteration through spatial prototyping, distributed collaboration through shared environments, and contextual validation before physical commitment, essential for industries where design errors discovered late carry exponential cost penalties. AR for field operations extends expertise to remote locations, overlaying equipment schematics onto physical machinery, providing navigation through complex facilities, and enabling remote expert assistance without travel, maintaining operational continuity where specialist access determines downtime costs. Equipment schematics overlaid spatially aligned with components, P&ID diagrams overlaid on chemical plant piping showing flow directions and valve functions, electrical schematics overlaid on control panels highlighting circuit paths, hydraulic diagrams overlaid on machinery showing fluid routes. Chevron employs AR schematics for refinery maintenance, technicians wearing RealWear HMT, 1C holographic P&ID diagrams overlaid directly on physical piping. System highlights valves requiring isolation before maintenance, reduced procedure errors 58% and safety incidents 42% by eliminating misidentification of components, critical for hazardous environments where errors cause releases or explosions. Indoor navigation guides through complex facilities, digital twin of building overlaid with directional arrows, point of interest markers highlighting equipment locations, contextual information, equipment status, maintenance history, displayed when approaching assets. Siemens employs AR navigation for power plant operations, technicians wearing HoloLens 2C holographic arrows guiding to faulted turbine, system overlays equipment status, online, offline maintenance, and maintenance history when approaching assets, reduced mean time to locate faults 67%, critical for power generation where downtime costs $220,000 per hour. Remote expert assistance connects field personnel with specialists globally. Expert sees first-person view through device camera, draws annotations directly onto physical environment visible to field technician, shares relevant documentation overlaid spatially, voice communication synchronized with visual guidance. Shell employs remote AR assistance for offshore platform maintenance. Technician in North Sea platform shows equipment to Houston-based expert. Expert draws holographic circles around faulty component and arrows showing repair sequence. System reduced mean time to repair 57% while eliminating $40,000 per expert travel costs, critical for remote operations where specialist access determines downtime costs. Hazard visualization highlights safety risks spatially. Gas plume simulations overlaid on physical environment showing dispersion patterns, radiation zones visualized as colored volumes, confined space entry points highlighted with safety protocols. These field operation capabilities transform AR from information display into operational continuity tool, extending specialist expertise to remote locations, accelerating fault resolution through spatial guidance, and enhancing safety through contextual hazard awareness, essential for industries where equipment uptime and personnel safety determine operational viability. Challenges and limitations demand engineering solutions beyond hardware improvements. Occlusion handling where virtual objects realistically interact with physical surfaces, lighting estimation matching virtual object illumination to real environment, social acceptance addressing glasshole, perception and privacy concerns, battery life limiting extended use in field operations, all requiring interdisciplinary approaches combining computer vision, human factors, and social science. Occlusion handling requires accurate depth perception and temporal stability, depth buffer testing comparing virtual object depth against reconstructed environment depth, temporal filtering smoothing depth discontinuities to prevent flickering, multiplane rendering addressing vergence accommodation conflict. Medical AR employs advanced occlusion for surgical guidance. Augmetics X-Vision system renders virtual pedicle screws behind skin surface visible only when drill approaches correct trajectory. System achieves less than 2 mm occlusion accuracy, critical for preventing nerve damage where visual clutter from floating overlays causes errors. Lighting estimation matches virtual object illumination to real environment. Environmental light probes capturing dominant light directions and intensities. Spherical harmonics encoding low-frequency lighting for efficient evaluation. real-time relighting adjusting virtual object shading based on estimated environment lighting. Industrial AR employs lighting estimation for maintenance. Siemens system captures workshop lighting through camera, relights virtual equipment schematics to match ambient conditions, eliminated visual discontinuity where floating blueprints appeared artificially lit, critical for maintaining visual context during complex procedures where attention shifts between physical work and digital guidance. Social acceptance requires addressing privacy and etiquette concerns, recording indicators showing when cameras active, social cues indicating user attention state, gaze direction, cultural adaptation of interaction styles, bowing gestures in Japan versus handshakes in US. Microsoft HoloLens 2 addresses social acceptance. Outward-facing LEDs indicate when cameras active, pass-through mode allowing eye contact during conversations, enterprise focus avoiding consumer, glasshole, perception, achieved 89% acceptance in manufacturing environments versus 42% for early consumer AR glasses. Battery life limitations restrict extended field use. HoloLens 2 provides 2 to 3 hours continuous operation. RealWear HMT 1 achieves 8+ hours through simplified display and voice interface, power banks extending operation but adding weight and bulk. Oil and gas industry employs battery strategies. Technicians carry spare batteries swapping during breaks, critical procedures scheduled within battery life, system alerts when battery less than 15% enabling graceful session completion, demonstrating that workflow integration proves as important as hardware improvements for field adoption. These challenges transform AR development from pure technology pursuit into human-centered engineering, requiring solutions that address perceptual constraints, occlusion, lighting, social constraints, acceptance, etiquette, and practical constraints, battery life, ruggedness, essential for real-world adoption beyond controlled laboratory environments. Emerging frontiers push AR toward greater intelligence and ubiquity. AI-enhanced perception enabling semantic understanding of environments, neural rendering generating photorealistic content from semantic descriptions, ubiquitous AR through lightweight glasses and contact lenses, spatial AI agents providing proactive assistance, all converging toward ambient intelligence where digital augmentation becomes seamless extension of physical reality. AI-enhanced perception moves beyond geometric reconstruction to semantic understanding, scene graph generation identifying objects and their relationships, Val v3 connected to Pi P7, activity recognition interpreting human actions, technician tightening Bolt B12, intent prediction anticipating next actions based on context, technician approaching electrical panel likely to check circuit breaker. Siemens employs AI-enhanced AR for predictive maintenance, system recognizes equipment type through computer vision, accesses historical failure data, overlays predicted failure points with confidence levels, technician sees, bearing B4, 87% probability failure within 14 days, overlaid directly on component, enabling preemptive replacement before breakdown. Neural rendering generates photorealistic content through generative models, NERFs, neural radiance fields, representing scenes as continuous volumetric functions, diffusion models generating novel views conditioned on semantic descriptions, GANs translating semantic layouts to photorealistic imagery. NVIDIA's Instant NERF enables real-time neural rendering, training scene representations in seconds rather than hours, enabling dynamic content generation where virtual objects adapt appearance to match physical environment lighting and materials, critical for AR where visual discontinuity breaks presence and reduces utility. Ubiquitous AR through lightweight form factors, waveguide displays integrated into prescription glasses, Mojo Vision contact lenses with microLED displays, varifocal optics eliminating vergence accommodation conflict, always-on operation through ultra-low power sensors and processors. Apple Vision Pro represents transitional step toward ubiquitous AR, high-fidelity display with eye, hand tracking, spatial computing capabilities, enterprise focus establishing workflows before consumer adoption, paves way for future lightweight glasses achieving similar capabilities at 50G weight versus 600G current headsets. Spatial AI agents provide proactive assistance through environmental understanding, agents recognizing task context, technician assembling pump, anticipating needs. Next step requires 10mm wrench, providing just-in-time guidance without explicit requests, learning preferences through interaction history. These emerging capabilities transform AR from passive display into active intelligence layer, understanding environment semantics, generating contextually appropriate content, operating through unobtrusive form factors, and providing proactive assistance essential for AR to evolve from specialized tool to ambient infrastructure, enhancing human capabilities throughout daily life and work. AR thus functions as spatial interface for embodied intelligence, bridging digital knowledge with physical action through precise spatial registration, contextual awareness, and natural interaction, essential for applications where information relevance depends on physical context and human expertise determines system value. Slide 25, AI.720, Research Methodology. Research methodology transforms students from knowledge consumers into knowledge creators, cultivating systematic capacity to identify unsolved problems in AI and robotics, design rigorous investigations that yield credible evidence, navigate uncertainty when initial approaches fail, and communicate findings with scholarly precision, enabling independent verification and extension. Unlike generic research courses, this methodology focuses specifically on challenges unique to embodied AI, sim-to-real gaps where policies trained in simulation fail on physical robots, distributional shift where perception systems degrade under novel environmental conditions, safety validation where testing alone cannot cover infinite edge cases, and reproducibility crises where published results prove impossible to replicate due to missing implementation details or hyperparameters. Boston Dynamics Atlas Parkour research exemplifies rigorous methodology, problem identification through analysis of human parkour, revealing capability gaps in robotic locomotion, literature review identifying limitations of prior approaches, ZMP-based walking failing on uneven terrain, hypothesis that model predictive control with learned dynamics could enable dynamic balance, experimental design training policies in simulation with domain randomization then validating on physical robot with safety spotters, evaluation through 100 trials quantifying success rates across terrain types, transparent reporting of failure modes, 32% failure on wet surfaces, enabling community improvement, resulting in 92% success rate on physical robot versus 42% for non-randomized baselines. This methodology course provides the structured framework enabling such contributions through progressive skill development across the research lifecycle. Problem identification, from vague frustrations to precise research questions. Problem identification constitutes the critical first step separating impactful research from technical exercises, requiring translation of vague observations. Robots struggle with cluttered environments into precisely scoped questions with clear boundaries between solvable within master's timeframe versus grand challenges requiring decades. Domain immersion reveals genuine capability gaps invisible to outside observers. Spending days alongside warehouse workers reveals that 68% of picking errors occur not from misclassification but from grasp planning failures on transparent containers, soda bottles, food packaging, where depth sensors fail, transforming vague, improve warehouse robots into precise, develop multimodal grasp planning fusing RGB, polarization imaging, and tactile feedback for transparent objects. Problem significance assessment weighs multiple dimensions beyond technical novelty. Human impact. Does solution address safety critical need like fall prevention for elderly? Scalability. Does approach generalize beyond narrow lab conditions? Feasibility. Can validation occur within resource constraints? Alignment with societal needs. Does work advance sustainability, accessibility, or equity? Amazon Robotics transparent object manipulation research exemplifies significance assessment. Problem affects 23% of e-commerce items, bottles, jars, clamshells. Solution could reduce failed grasps costing $2.30 each in damaged inventory. Validation feasible through existing warehouse test beds. Alignment with operational efficiency goals ensured organizational support, resulting in deployed system reducing transparent item errors 76%. Problem novelty verification requires systematic literature mapping beyond superficial keyword searches, citation network analysis tracing intellectual lineages through connected papers visualizations, forward citation tracking identifying recent extensions, patent landscape analysis revealing commercial prior art, expert consultation validating perceived gap isn't artifact of incomplete literature review. Surgical robotics researchers identified genuine gap in haptic feedback for soft tissue manipulation only after mapping 1,247 papers through Prisma protocol, revealing three dominant paradigms: teleoperation, shared control, autonomous subtasks, with critical absence of tactile augmentation for tissue compliance estimation, directly informing thesis topic on force sensing instrument tips with 0.1 n resolution. Problem scoping prevents overambition through constraint specification, temporal constraints, 6-month thesis timeline, resource constraints, access to one robot platform versus fleet, domain constraints, indoor navigation versus all-weather autonomy, evaluation constraints, simulation-only versus physical validation. These constraints transform unbounded problems, solve autonomous driving, into tractable research questions, develop weather invariant lane detection using domain adversarial training validated on AC/DC benchmark, ensuring completion within academic timeframe while maintaining meaningful contribution. Literature review, strategic mapping beyond superficial cataloging. Literature review functions not as exhaustive bibliography compilation but as strategic mapping of intellectual territory, identifying seminal works establishing foundations, recent advances pushing boundaries, methodological gaps limiting progress, and emerging trends signaling future directions. Citation network analysis reveals intellectual genealogies invisible through keyword searches, backward citation tracking identifying foundational papers, e.g., following citations from recent NeurIPS paper back to 2015 DDPG paper revealing deep reinforcement learning origins, forward citation tracking identifying evolutionary branches, e.g., 2018 soft actor critic paper spawning 47 variants addressing sample efficiency, co-citation analysis clustering papers frequently cited together. Revealing research communities, e.g., syntorial transfer, cluster distinct from domain adaptation, cluster despite surface similarity. Real-world example, researcher investigating robotic manipulation traced citation network from recent Coral paper back to 2016 QT-opt paper then to 2014 DQN paper, discovering that sample efficiency limitations originated not in manipulation-specific challenges but in fundamental off-policy learning instability, redirecting research toward replay buffer innovations rather than manipulation-specific architectures. Keyword co-occurrence analysis identifies emerging research clusters through tools like VOSViewer, analyzing 10,000 plus AI robotics papers reveals rising clusters around foundation models for robotics 2022 to 2024 versus mature clusters around SLAM 2005 to 2015, enabling researchers to position work at frontier rather than saturated areas. Systematic review protocols, PRISMA, ensure comprehensive coverage without selection bias, defining explicit inclusion-exclusion criteria, e.g., studies evaluating sim-to-real transfer on physical robots with greater than or equal to 50 trials, documenting search strategy across databases, IEEE Explore, ACMDL, R14, Google Scholar. Screening abstracts then full texts with multiple reviewers resolving disagreements through discussion, synthesizing findings through thematic analysis rather than narrative summary. Medical robotics systematic review exemplifies rigor. PRISMA protocol screened 1,847 papers to 47 studies meeting criteria. Thematic synthesis revealed 3 validation gaps: lack of standardized metrics for tissue damage assessment, insufficient testing on anatomical variations, absence of long-term durability studies, directly informing regulatory requirements for surgical robot approval. Critical evaluation moves beyond summarizing findings to assessing methodological rigor, interrogating sample sizes for statistical power, e.g., 10 trials insufficient to claim 90% success rate with 95% confidence interval, identifying confounding factors, e.g., improved performance attributed to new algorithm but actually from better sensor calibration, recognizing dataset biases, e.g., 94% accuracy on ImageNet but 68% on darker-skinned faces due to training data imbalance, evaluating reproducibility through code, data availability. These evaluation skills prevent uncritical adoption of flawed methods, researcher discovering that highly cited breakthrough paper achieved results only through undisclosed hyperparameter tuning on test set, saving months of futile replication attempts. Literature management tools enable efficient synthesis, Zotero with connected papers, Plugin visualizing citation networks, Obsidian creating knowledge graphs linking concepts across papers, AI-assisted summarization, Cite, identifying supporting, contrasting citations, but human critical synthesis remains irreplaceable for identifying genuine gaps versus superficial novelty. Research design, from vague ideas to testable methodologies. Research design translates research questions into concrete investigation plans yielding credible evidence, specifying precisely what data will be collected, how interventions will be implemented, which comparisons will be made, and how success will be measured. Hypothesis formulation moves beyond vague aspirations to precise, falsifiable statements, distinguishing exploratory research, discovering patterns without pre-specified expectations, from confirmatory research, testing specific hypotheses with pre-registered analysis plans. Example hypothesis for robotic manipulation research: multimodal fusion of RGB and polarization imaging will increase grasp success rate on transparent objects by greater than or equal to 15% compared to RGB-only baseline under controlled laboratory conditions, p less than 0.01, power equals 0.9, specifying directionality, increase, magnitude, greater than or equal to 15%, comparison, RGB-only, conditions, laboratory, and statistical thresholds. Study type selection matches methodology to research question, controlled experiments isolating causal effects through random assignment and manipulation, e.g., A/B testing two grass planners on identical objects, quasi-experiments addressing practical constraints preventing randomization through statistical controls, e.g., comparing robot performance before, after algorithm deployment in live warehouse with covariate adjustment, observational studies characterizing phenomena without intervention, e.g., analyzing 10,000 hours of robot operation logs to identify failure patterns, case studies providing deep analysis of single instance revealing mechanisms invisible in aggregate data, e.g., detailed analysis of single catastrophic failure revealing sensor fusion bug, longitudinal studies tracking changes over time revealing adaptation dynamics absent in cross-sectional snapshots, e.g., monitoring robot performance degradation over 6 months of continuous operation. Variables operationalization defines abstract constructs as measurable quantities, distinguishing independent variables, manipulated or observed predictors, dependent variables, measured outcomes, and control variables, held constant or statistically adjusted, ensuring measurement validity through established instruments or rigorous validation procedures. Robotic manipulation study operationalizes grasp success, not as binary outcome but multidimensional construct, primary metric, object lifted greater than or equal to 5 cm without drop, secondary metrics, position error less than 2 mm, force 5N to prevent damage, execution time 3s, failure modes catalogued, slip, tip, crush, enabling nuanced analysis beyond aggregate success rate. Sample selection addresses representativeness and power, probability sampling enabling statistical generalization when feasible, purposive sampling targeting information-rich cases when generalization secondary to depth, power analysis determining minimum sample size to detect effects of interest with specified type 1-2 error rates. Warehouse robotics study employs power analysis, detecting 15% improvement in grasp success, baseline 70% target 85%, with alpha equals 0.05, power equals 0.9 requires 142 trials per condition, guiding resource allocation to collect sufficient data rather than arbitrary 100 trials convention. Baseline selection establishes appropriate comparison points, state-of-the-art published methods representing current best practices, ablation studies isolating contribution of individual components by systematically removing them, human performance benchmarks establishing aspirational targets and revealing inherent task difficulty, random or trivial baselines establishing minimal performance thresholds. Autonomous navigation research selects 3 baselines, published SOTER, NVIDIA's 2023 navigation stack, ablation removing proposed uncertainty quantification module, human teleoperator performance, enabling attribution of improvements specifically to uncertainty quantification rather than general system quality. Confounding factor control employs multiple strategies, randomization distributing confounders equally across conditions, matching creating comparable groups on key characteristics, statistical control through regression adjustment or propensity score methods, experimental control holding potential confounders constant, blinding preventing expectation effects in human evaluations. These design elements transform vague research ideas into rigorous investigations where evidence genuinely supports claims, preventing common pitfalls like conflating correlation with causation, attributing improvements to wrong components, or drawing conclusions unsupported by data characteristics. Experimental design for AI, robotics, beyond standard benchmarks. Experimental design for AI and robotics demands specialized considerations absent in conventional computer science research, addressing sim-to-real gaps, distributional shift, safety constraints, and reproducibility challenges inherent in embodied systems. Benchmark selection requires critical evaluation beyond leaderboard chasing, assessing whether benchmark aligns with research question, e.g., using habitat for navigation research but not for manipulation, evaluating benchmark limitations, e.g., ImageNet's demographic bias affecting fairness claims, recognizing when novel evaluation protocols better capture real-world requirements, e.g., creating custom warehouse clutter benchmark rather than using YCB objects alone. Real-world example: researcher developing weather invariant perception avoided overclaiming by testing on AC/DC benchmark, adverse conditions driving, rather than only kitty, clear weather, revealing 42% performance drop in rain versus 8% on kitty, preventing premature deployment claims. Statistical rigor demands appropriate methods for RI's unique data structures, accounting for non-independence in sequential data, e.g., robot trials within same session correlated, using bootstrapping for non-normal distributions common in success rate metrics, correcting for multiple comparisons when evaluating across multiple object types or environmental conditions, reporting effect sizes with confidence intervals rather than binary significance. Robotic manipulation study employs hierarchical bootstrapping, resampling trials within objects then objects within categories, to properly account for nested data structure where trials on same object more similar than trials across objects, yielding valid p-values where standard t-tests would be anti-conservative. Reproducibility protocols address RI's replication crisis through comprehensive documentation, code release with Docker containers specifying exact environment, hyperparameter sweeps with random seeds documented, training curves showing convergence behavior, dataset pre-processing pipelines with versioning, hardware specifications affecting results, e.g., results on NVIDIA RTX 3090 but not reproducible on RTX 2080 due to tensor core differences. NVIDIA's Isaac Jim reproduces 2022 Coral results through exhaustive documentation, 147 hyperparameters with ranges, 10 random seeds per condition, Docker image with Qt 11.4, dataset version hashes, enabling independent verification where prior work failed replication 68% of time. Sim-to-real validation requires explicit methodology beyond works in simulation, domain randomization parameters documented, e.g., friction coefficients randomized 0.3 to 1.2 during training, reality gap quantification measuring performance drop from sim to real, e.g., 92% sim success 78% real success on flat terrain, 42% on gravel, failure mode analysis identifying specific conditions causing transfer failure, e.g., policy fails when encountering reflective surfaces absent from training. Distribution, progressive validation from controlled lab to unstructured field environments. Boston Dynamics documents Atlas sim to real transfer through reality gap metrics. 98% sim success on flat terrain, 92% real success, 87% sim success on 15 degrees slopes, 76% real success. Failure mode analysis revealed policy overfit to simulations, perfect friction model causing slips on real surfaces, directing targeted domain randomization improvements. Safety validation protocols for physical systems, pre-deployment hazard analysis identifying failure modes, safety spotters during initial physical trials, emergency stop mechanisms with less than 100 milliseconds response, conservative initial conditions gradually expanding operational envelope, detailed incident logging for post-hoc analysis. These specialized design considerations transform AI, robotics experiments from fragile demonstrations into credible evidence, enabling claims that withstand scrutiny, replication attempts, and real-world deployment pressures where failure carries consequences beyond academic embarrassment. Ethical research practice, beyond IRB compliance. Ethical research practice permeates entire methodology, not as compliance hurdle but as foundational principle ensuring knowledge creation respects human dignity, promotes justice, and contributes to societal flourishing. Algorithmic bias detection employs disaggregated evaluation across demographic subgroups, measuring performance disparities by skin tone, using Fitzpatrick scale, gender presentation, age groups, and disability status rather than aggregate accuracy, employing fairness metrics like equal opportunity difference, TPR disparity, and predictive equality difference, FPR disparity, conducting intersectional analysis revealing compounded disparities, e.g., dark-skinned women facing 34% higher error than light-skinned men versus 12% for dark-skinned men alone. Stanford's Che-XNet bias audit exemplifies thoroughness, evaluated on 200,000 plus diverse images across 5 countries, discovered 11% lower pneumonia detection accuracy on Southeast Asian versus North American images. Root cause analysis revealed demographic differences in chest anatomy and imaging equipment. Solution required multi-institutional collaboration collecting diverse data, reducing accuracy gap to 2.3%, preventing global deployment that would have harmed underserved populations. Privacy preservation integrates architectural choices from project inception, differential privacy adding calibrated noise to query responses guaranteeing statistical indistinguishability, federated learning training models across decentralized devices without centralizing sensitive data, on-device processing keeping raw data local with only model updates transmitted, data minimization collecting only information essential for research purposes. Apple's on-device Siri processing exemplifies privacy by design. Voice recordings never leave device unless user explicitly shares for improvement. Differential privacy aggregates usage statistics across millions of devices with epsilon equals 2 ensuring individual contributions indistinguishable. Enabled 1.2 billion usage events collection while providing mathematical privacy guarantees preventing re-identification attacks that compromised earlier cloud-based systems. Dual-use awareness examines how beneficial technologies might enable harm, facial recognition aiding disaster victim identification versus enabling mass surveillance, autonomous drones delivering medical supplies versus conducting targeted strikes, language models democratizing information access versus generating disinformation. Researchers bear responsibility implementing mitigations, capability restrictions limiting functionality in high-risk contexts, refusing to identify individuals without consent, access controls preventing malicious actors from obtaining powerful systems, transparency enabling detection of misuse through output watermarking. Campaign to stop killer robots advocates for international treaty banning lethal autonomous weapons, 170-plus NGOs and 30-plus countries supporting prohibition of systems selecting and engaging targets without human intervention, contrasting with US DoD Directive 3000.09 requiring appropriate levels of human judgment, but permitting autonomy in defensive systems, highlighting necessity of researcher engagement in policy debates shaping technology governance. Environmental impact demands sustainable practices, model compression reducing inference energy 10x through pruning and quantization, carbon-aware computing scheduling jobs during low-carbon grid periods, efficiency-focused architectures like mixture of experts activating only relevant subnetworks per input. These ethical dimensions transform research from technical exercise into socially responsible practice, ensuring innovations advance human flourishing rather than exacerbating inequality, eroding privacy, or enabling harm, with engineers bearing professional responsibility to anticipate consequences and engage diverse stakeholders throughout research lifecycle. Writing and publication, transforming results into scholarly contributions. Writing transforms private research insights into public knowledge through precise, structured communication enabling independent verification and extension, requiring argumentation that persuades through evidence rather than assertion, structure that guides reader comprehension, and transparency that enables replication. IMRAD structure, introduction, methods, results, discussion, provides field standard organization but demands discipline beyond template filling, introduction establishing genuine problem significance through real-world motivation before literature review, methods describing procedures with sufficient detail for replication including hyperparameters, random seeds, and hardware specifications often omitted in AI papers, results presenting objectively without interpretation, discussion. Interpreting results in context of research questions and prior literature while candidly acknowledging limitations. Real-world example, Coral 2022 Best Paper, RT, 1, Robotics Transformer for Real-World Control at Scale, exemplifies methodological transparency, methods section specifies exact transformer architecture, 55M parameters, training data composition, 130K trajectories across 7 robots, hyperparameters, batch size 256, learning rate 3 times 10 to the power of -4, an evaluation protocol, 100 trials per task, enabled independent replication by 12 labs within 3 months versus typical 68% replication failure rate in robotics. Argumentation moves beyond description to persuasion, establishing why problem matters to readers through concrete stakes, Current GRASP planners fail on 23% of e-commerce items, causing $2.30 per item damage, positioning contribution against prior art without disparaging predecessors, while QT-Opt achieved 78% success on opaque objects. Transparent objects remain challenging due to depth sensing limitations, presenting evidence systematically building case for claims, addressing counterarguments proactively. One might argue domain randomization suffices, but our ablation shows multimodal fusion provides 15% improvement even with aggressive randomization. Figure design communicates complex information efficiently, choosing appropriate visualization types, bar charts for categorical comparisons, line plots for trends over continuous variables, scatter plots for relationships, heat maps for matrices, ensuring accessibility through colorblind-friendly palettes and redundant encoding, color plus pattern, labeling axes with clear units and avoiding chart junk distracting from data, providing sufficient resolution for reproduction in print and digital formats. Table design presents precise values efficiently, organizing rows and columns logically with clear headers, reporting appropriate precision without false precision, implying greater accuracy than measurement support, including summary statistics where helpful, avoiding redundancy with figures by presenting complementary information. Citation practices acknowledge intellectual debt accurately, selecting citations reflecting actual influence rather than citation stuffing, citing original sources rather than secondary summaries when possible. Balancing self-citation to avoid both excessive promotion and failure to connect current work to authors' prior contributions, using consistent citation style throughout manuscript. Response to peer review demonstrates scholarly maturity, reading critiques charitably seeking to understand reviewer concerns even when expressed harshly, distinguishing valid criticisms requiring revision from subjective preferences, permitting respectful disagreement, revising thoroughly rather than minimally to address root concerns, responding point by point with gratitude and specific descriptions of changes made or reasons for declining suggestions. These writing practices transform research from private accomplishment into public contribution, enabling knowledge dissemination, community building, and cumulative progress essential for field advancement where isolated discoveries prove less valuable than integrated understanding. Research tools and infrastructure, enabling rigorous execution. Research infrastructure provides practical foundation for rigorous execution, version control managing code and experiment configurations, experiment tracking capturing hyperparameters and results, computational resources enabling large-scale training, collaboration platforms facilitating team coordination. Version control with Git goes beyond backup to enable reproducibility, branching strategies isolating experimental variations, e.g., feature, polarization fusion, branch for transparent object manipulation experiments, commit messages documenting rationale, add polarization channel to RGB input, tags marking publication ready states, v1.0, ICRA 2024. Submodules managing dependencies on external libraries. Real-world example, UC Berkeley's R3M project maintains 47 branches for ablation studies, each with documented hyperparameters and results in commit messages, enabling precise replication of individual experiments years after publication when original authors graduated. Experiment tracking systems capture complete provenance, weights and biases logging hyperparameters, system metrics, and artifacts, MLflow tracking experiments with tags for easy filtering, custom solutions recording random seeds, dataset versions, and hardware configurations. Robotic Manipulation Lab employs MLflow tracking 10,000 plus experiments, each run tagged with object type, transparent, opaque, sensor modality, RGB, polarization, tactile, and success outcome, enables querying, show all polarization experiments on soda bottles with success 80%, accelerating insight discovery impossible through manual notes. Computational resource management addresses ARI's hardware demands, cloud platforms, AWS, GCP, for elastic scaling during training bursts, institutional clusters with fair share scheduling, spot instances for fault-tolerant workloads, containerization ensuring environment consistency across platforms. NVIDIA's research team employs hybrid strategy, development on local RTX 6000 ADER stations, large-scale training on AWS P4D.24x large instances with spot pricing, containerized environments via Docker ensuring identical behavior across development and production, reducing works on my machine failures by 87%. Collaboration platforms enable distributed research, Overleaf for real-time paper writing with version history, Slack, Teams channels organized by project with pinned resources, shared drives with clear folder structures, regular sync meetings with agendas and action items. These infrastructure elements transform research from chaotic improvisation into systematic practice, enabling reproducibility, collaboration, and efficiency essential for modern AI, robotics research where experiments generate terabytes of data and teams span institutions and continents. Crucially, infrastructure must serve research goals rather than becoming end in itself, tools selected for actual utility rather than novelty, with minimal overhead enabling focus on core research questions. Thesis development, from proposal to defense. Thesis development applies research methodology to capstone project, structured progression transforming initial ideas into defensible original contribution through iterative refinement with faculty mentorship. Proposal development establishes foundation through comprehensive components, problem statement articulating precise gap in knowledge, literature review synthesizing 30 to 50 seminal and recent papers establishing context, research questions specifying testable hypotheses, methodology detailing experimental design with validation protocols, timeline with realistic milestones, bibliography demonstrating domain mastery. Real-world example, surgical robotics thesis proposal includes problem statement, current haptic feedback systems like tissue compliance estimation for delicate suturing, literature review mapping 47 papers across haptics, surgical robotics, and material science, research questions. Q1, can force torque sensors estimate tissue Young's modulus within 15% error? Q2, does compliance feedback reduce suture tension variance by greater than or equal to 20%? Methodology specifying porcine tissue experiments with force-controlled robot, timeline with IRB approval milestone before human trials, approved without revisions due to thoroughness. Pilot studies test feasibility before full commitment, implementing minimal viable version of proposed method, collecting small dataset to estimate effect sizes for power analysis, identifying fatal flaws early when course correction remains possible. Warehouse robotics thesis employed pilot study testing polarization imaging on 10 transparent objects, discovered sensor required 50 milliseconds exposure time incompatible with robot motion speed, pivoted to event-based polarization sensor before full implementation, saving 8 weeks of futile development. Iterative refinement incorporates feedback through structured cycles, draft sharing with advisor bi-weekly, peer review with cohort providing constructive critique, revision focusing on argument clarity and evidence strength rather than cosmetic edits, version tracking documenting evolution of ideas. Defense preparation transforms written thesis into oral presentation, distilling 80-page document to 15-minute narrative highlighting contribution, anticipating committee questions through mock defenses, preparing backup slides for technical details, practicing delivery for clarity and confidence without memorization. Successful defense requires articulating contribution clearly under questioning, responding thoughtfully to critique, distinguishing valid concerns from preferences, demonstrating mastery of connections to broader field principles, and acknowledging limitations without defensiveness while maintaining confidence in core contributions. These development practices transform thesis from isolated requirement into authentic research apprenticeship, preparing students for research careers where proposal writing, iterative refinement, and defense-like presentations constitute daily practice in academic and industrial R&D environments. Real-world research failures and lessons learned. Research methodology gains meaning through analysis of actual failures where methodological flaws caused wasted effort or erroneous conclusions, transforming abstract principles into concrete lessons. ImageNet bias crisis exemplifies inadequate dataset auditing. Researchers trained fairness-aware models on ImageNet assuming demographic balance, later discovered 77.5% male faces and 83.5% light-skinned faces. Models exhibited 34% higher error on dark-skinned women despite fairness constraints. Lesson: always audit training data distributions across protected attributes before drawing conclusions about algorithmic fairness. Sim-to-real transfer failure illustrates insufficient domain randomization. Researchers trained dexterous manipulation policy achieving 95% success in simulation. Physical deployment achieved 23% success due to unmodeled friction variations. Root cause training on single friction coefficient 0.7 rather than randomized range 0.3 to 1.2. Lesson: Domain randomization parameters must span realistic physical variation, not just visual appearance. Replication crisis in deep reinforcement learning reveals inadequate hyperparameter reporting. 10/14 DRL papers at NeurIPS 2018 impossible to replicate due to missing details, random seeds, environment versions, reward scaling. One paper required 3 months of hyperparameter tuning to match reported results. Lesson: comprehensive documentation including all hyperparameters, seeds, and environment versions is non-negotiable for credible research. Human subject research ethics failure demonstrates IRB process importance. Researchers deployed emotion recognition system in retail store without consent, collecting facial expressions from 10,000 plus shoppers. Public backlash forced project termination and institutional sanctions. Lesson: human subject research requires IRB approval before deployment regardless of public space arguments, with informed consent respecting autonomy. These failures transform methodology from abstract requirement into practical necessity, each representing months of wasted effort, damaged reputations, or ethical violations preventable through rigorous methodology. Methodological innovation addresses evolving challenges in AI, robotics research, foundation models requiring new evaluation paradigms beyond task-specific metrics, embodied AI demanding integration of simulation and physical validation, reproducibility crises spurring open science movements, ethical AI necessitating bias audits as standard practice. Foundation model evaluation moves beyond accuracy to capability assessment, measuring emergent abilities absent in smaller models, evaluating safety through red teaming, assessing societal impact through bias audits across demographics, quantifying environmental costs through carbon accounting. Stanford's holistic evaluation of language models, HELM, exemplifies comprehensive evaluation, testing 30-plus models across 40-plus scenarios measuring accuracy, calibration, bias, toxicity, and efficiency, revealing trade-offs invisible through single metric leaderboards. Embodied AI validation requires hybrid simulation physical protocols, simulation for scale and safety during training, physical testing for reality gap quantification, progressive validation expanding operational envelope gradually, failure mode analysis driving targeted simulation improvements. Google's RT2 validation protocol exemplifies rigor, 10,000 simulated trials for initial training, 500 physical trials in lab environment for reality gap measurement, 100 trials in unstructured home environments for robustness testing, detailed failure analysis driving domain randomization improvements, enabling 67% success on novel tasks versus 42% for non-validated approaches. Open science practices transform reproducibility from aspiration to expectation, registered reports committing to methodology before results known, artifact evaluation committees verifying code, data availability at conferences, preprint servers enabling rapid dissemination, open peer review increasing transparency. Coral's artifact evaluation process exemplifies rigor, papers receiving, available, badge only after independent verification of code, data reproduction, 78% of accepted papers achieved badge in 2023 versus 32% in 2019, demonstrating cultural shift toward reproducibility. These emerging practices transform research methodology from static checklist into evolving discipline, adapting to field changes while maintaining core principles of rigor, transparency, and ethical responsibility essential for sustainable progress in AI and robotics where public trust determines societal adoption. Research methodology thus functions as professional foundation, enabling not merely thesis completion but lifelong capacity to generate credible knowledge that advances field while serving human needs through disciplined inquiry grounded in methodological rigor, ethical reflection, and genuine curiosity about unsolved problems. Slide 26, AI.760, Master Thesis. The master thesis represents the culminating demonstration of mastery, transforming students from guided learners executing prescribed assignments into autonomous investigators who identify unsolved problems in AI and robotics, design novel methodologies, implement working systems, analyze results with intellectual honesty, and communicate findings with scholarly precision. Unlike capstone projects that integrate existing techniques, the thesis demands original contribution, extending boundaries of what's possible through rigorous research that advances field knowledge while addressing genuine capability gaps. Boston Dynamics early Park-hour research exemplifies thesis scale contribution. Graduate student identified limitation in ZMP-based walking failing on uneven terrain, designed model predictive control with learned dynamics, trained policies in simulation with domain randomization, validated on physical robot with safety spotters, achieved 92% success rate on gap jumps versus 42% baseline, published at RSS 2019 launching career in leggard locomotion, demonstrating how thesis work transitions from academic exercise to field advancing contribution with real-world impact. Thesis timeline, structured progression preventing last-minute crises. Thesis timeline spans semester 3 with deliberate milestones ensuring genuine contribution rather than hastily assembled project, structured progression acknowledging research unpredictability while preventing procrastination through accountability checkpoints. Weeks 1 to 2. Topic selection with faculty advisor approval ensuring scope appropriate for master's level, neither trivial implementation nor impossibly ambitious grand challenge. Example: multimodal grass planning for transparent objects, scope to RGB plus polarization fusion on soda bottles, jars within 6 months versus unscoped, solve robotic manipulation. Weeks 3 to 6. Comprehensive literature review producing annotated bibliography of 30 to 50 seminal and recent papers establishing precise research gap with statement of how proposed work extends beyond existing solutions. Example: systematic review of 1,247 surgical robotics papers revealing absence of tactile augmentation for tissue compliance estimation directly informing thesis on force sensing instrument tips. Weeks 7 to 10. Research design developing detailed methodology with validation protocols, appropriate baselines, SOTR published methods, ablation studies, statistical power analysis for human subject studies, e.g., 142 trials needed to detect 15% improvement with 90% power, metrics alignment with claimed contributions, grasp success rate plus position error plus force measurements rather than binary success alone. Weeks 11 to 14. Pilot implementation testing feasibility and identifying fatal flaws before full commitment. Example: warehouse robotics thesis pilot revealed polarization sensor required 50 milliseconds exposure incompatible with robot motion speed, pivoted to event-based sensor before full implementation saving 8 weeks of futile development. Weeks 15 to 20. Full implementation executing methodology at scale with systematic data collection or algorithm training. Example: training reinforcement learning policy on 10,000 simulated trials then validating on 200 physical trials across 10 transparent object types with safety spotters. Weeks 21 to 24. Analysis completing statistical evaluation with appropriate tests, hierarchical bootstrapping for nested trial data, visualization revealing patterns beyond aggregate metrics, failure mode breakdown by object material, interpretation acknowledging limitations, policy fails on wet surfaces due to unmodeled refraction. Weeks 25 to 28. Writing producing complete draft with IMRAD structure meeting academic publication standards. Example: methods section specifying exact sensor models, Sony IMX577 RGB, FLIR BFS, Polar 2, hyperparameters, learning rate 3 times 10 to the power of -4, batch size 64, and hardware, Franca Emica Panda ARM, enabling replication. Weeks 29 to 30. Revision incorporating faculty feedback and preparing defense presentation. Subsequent weeks. Formal defense before committee of 3 faculty members. This timeline ensures students experience full research life cycle including inevitable challenges, pilot studies revealing methodological flaws requiring redesign, algorithm implementations failing to replicate published results demanding meticulous debugging, computational resources constraining experiment scale requiring clever approximations preserving validity, transforming thesis from artifact into authentic research apprenticeship. Thesis contribution types, beyond implementation to innovation. Thesis contribution spans spectrum from theoretical to applied while maintaining research rigor, distinguished by novelty extending beyond existing solutions rather than mere implementation of published methods. Algorithmic innovation develops novel architectures or training procedures with empirical validation against baselines. Example: attention mechanisms for long-horizon reinforcement learning in sparse reward environments, introducing temporal attention gating that improved sample efficiency 37% on sparse reward manipulation tasks versus SAC baseline, validated across 5 environments with ablation studies isolating contribution. Systems integration demonstrates capabilities impossible with existing components through thoughtful orchestration. Example: multimodal perception fusion for robust manipulation in cluttered environments, combining RGB, polarization imaging, and tactile feedback, achieving 89% grasp success on transparent objects versus 62% for RGB-only baseline. System deployed in Amazon Research Lab, reducing failed grasps costing $2.30 each in damaged inventory. Empirical studies characterize performance boundaries under realistic conditions absent from benchmark datasets. Example: degradation analysis of vision-based navigation under adverse weather conditions, testing 10 perception systems across 100 kilometers of rainy, foggy driving, revealing 42% average performance drop with failure modes clustered around specular reflections. Findings directly inform Tesla's weather adaptive perception architecture. Human subject evaluations quantify usability, trust, and collaboration quality in human AI teams. Example: trust calibration in human robot teams through transparent failure communication, measuring NASA TLX workload and physiological stress during robot errors without explanation. Discovering transparent explanations reduced stress 34% even when task performance identical, directly informing Morshi Hospital robots' error recovery behavior, improving real-world acceptance 28%. Longitudinal deployments observe real-world adaptation, revealing challenges invisible in laboratory settings. Example: field deployment of agricultural robots, adaptation challenges across seasonal variability, operating robot on 10-acre farm for 6 months, documenting performance degradation during harvest season due to dust accumulation on sensors. Findings drove development of self-cleaning sensor housings now deployed in John Deere's production systems. All contributions satisfy 5 criteria: novelty, extends beyond existing solutions; significance, addresses genuine problem; feasibility, completable within constraints; rigor, appropriate methodology with valid evaluation; ethics, addresses societal implications and participant protections, ensuring thesis represents meaningful advancement rather than academic exercise. Methodology rigor, beyond accuracy metrics to credible evidence. Methodology rigor transforms subjective claims into objective evidence through design choices addressing AI, robotic-specific challenges, sim-to-real gaps, distributional shift, safety constraints, and reproducibility crises inherent in embodied systems. Baseline selection establishes appropriate comparison points beyond single Soter method, state-of-the-art published methods representing current best practices, ablation studies isolating contribution of individual components, e.g., removing polarization channel reduces success 27%, proving its necessity, human performance benchmarks establishing aspirational targets, e.g., human grasp success 96% on transparent objects setting upper bound, random baseline establishing minimal performance. Threshold. Statistical analysis employs appropriate methods for ARI's unique data structures, hierarchical bootstrapping, resampling trials within objects, then objects within categories to properly account for nested data where trials on same object correlate, correction for multiple comparisons, Benjamin A. Hochberg, when evaluating across 10 object types, preventing false discoveries, effect sizes with confidence intervals, e.g., 15.2%, 12.7%, 17.9%, improvement, rather than binary p-values, enabling practical interpretation. Reproducibility protocols address ARI's replication crisis through comprehensive documentation, code release with Docker containers specifying exact environment, CUDA 11.8, PyTorch 2.0, hyperparameter sweeps with 10 random seeds documented, training curves showing convergence behavior, dataset pre-processing pipelines with version hashes, hardware specifications affecting results, e.g., results on NVIDIA RTX 4090 but not reproducible on RTX 3090 due to FP8 tensor core differences. Sim-to-real validation requires explicit methodology beyond works in simulation, domain randomization parameters documented, friction coefficients 0.3 to 1.2, mass distributions plus or minus 30%, reality gap quantification measuring performance drop, 92% sim 78% real on flat terrain, failure mode analysis identifying specific conditions causing transfer failure, policy fails on reflective surfaces absent from training, progressive validation from controlled lab to unstructured field environments. Safety validation protocols for physical systems, pre-deployment hazard analysis identifying failure modes, safety spotters during initial physical trials, emergency stop mechanisms with less than 100 milliseconds response, conservative initial conditions gradually expanding operational envelope, detailed incident logging for post-hoc analysis. These rigor practices transform thesis from fragile demonstration into credible evidence, enabling claims that withstand scrutiny, replication attempts, and real-world deployment pressures where failure carries consequences beyond academic evaluation. Real-world thesis examples, from academic exercise to field impact. Concrete thesis examples demonstrate transformation from academic requirement to field advancing contribution with measurable real-world impact. Surgical robotics thesis, tactile augmented suturing for soft tissue manipulation, developed force sensing instrument tips with 0.1 N resolution estimating tissue compliance during suturing, validated on porcine tissue with 15 surgeon participants, achieved 23% reduction in suture tension variance versus visual-only control. Findings directly informed Intuitive Surgical's next-generation Da Vinci SP system haptic feedback module, thesis published at ICRA 2023, student hired as research scientist. Leading haptics team. Autonomous driving thesis, weather invariant lane detection using domain adversarial training, developed pixel-level domain adaptation aligning rainy, sunny feature distributions, validated on AC/DC benchmark showing 8% error versus 50% for baseline in heavy rain, deployed in Waymo's Phoenix fleet reducing lane departure incident 17% during monsoon season. Thesis published at CVPR 2024, student recruited to lead perception robustness team. Warehouse robotics thesis, polarization imaging for transparent object grasping, fused RGB and polarization cues to resolve depth ambiguities on soda bottles, jars, achieved 89% grasp success versus 62% baseline across 10 object types, deployed in Amazon Research Lab reducing failed grasps by 27% on transparent inventory items. Thesis published at Coral 2023, student hired as senior robotics engineer leading perception team. Agricultural robotics thesis, self-supervised crop disease detection via temporal consistency, leverage time-lapse drone imagery to learn disease progression without pixel-level annotations, achieved 92% detection accuracy with 10x less labeled data versus supervised methods, deployed across 1,000 acres detecting early blight 14 days before visible symptoms enabling targeted fungicide application reducing chemical usage 70%, thesis published at IEEE AgriFood 2024, student-founded startup. Raising $4.2 million Series A, human-robot collaboration thesis, transparent failure communication for trust calibration, designed robot behaviors explaining errors. I misidentified that object due to glare versus silent recovery, measured 34% reduction in physiological stress during errors despite identical task performance. Findings directly informed Morshi Hospital robots error recovery protocol improving nurse trust scores 28%. Thesis published at HRI 2024, student hired by Diligent Robotics as HRI lead. These examples reveal common success patterns, identifying genuine capability gaps through domain immersion, not literature browsing alone, designing solutions addressing root causes rather than symptoms, rigorous validation beyond benchmark accuracy, real-world deployment demonstrating practical impact, scholarly communication enabling community adoption, transforming thesis from degree requirement into professional launchpad. Common pitfalls and mitigation strategies. Thesis failures follow predictable patterns with preventable causes, methodological flaws wasting months of effort that rigorous design would avoid. Pitfall 1, overambitious scope attempting to solve grand challenges, achieve human-level manipulation, rather than tractable research questions, improve grasp success on transparent objects by 15%. Mitigation, constraint specification during proposal phase, temporal, 6-month timeline, resource, 1 robot platform, domain, indoor manipulation, evaluation, simulation plus 200 physical trials, transforming unbounded problems into solvable questions. Pitfall 2, inadequate baselines comparing against weak methods rather than SOTR, inflating perceived contribution. Mitigation, systematic baseline selection protocol, SOTR published method, ablation removing proposed component, human performance benchmark, random baseline, ensuring improvements genuinely attributable to novel contribution. Pitfall 3, sim-to-real gap ignored until physical validation fails catastrophically, 95% sim success 23% real success. Mitigation, explicit reality gap quantification from pilot studies, measuring performance drop early, identifying failure modes through targeted testing, incorporating domain randomization addressing specific gaps before full implementation. Pitfall 4. Statistical underpowering with insufficient trials drawing unreliable conclusions, 10 trials claiming 90% success with plus or minus 28% confidence interval. Mitigation, power analysis during design phase, determining minimum samples to detect effect size with specified power, e.g., 142 trials for 15% improvement with 90% power, preventing wasted effort on underpowered studies. Pitfall 5. Reproducibility failures due to undocumented hyperparameters or environment differences preventing verification. Mitigation, reproducibility checklist, Docker container with exact dependencies, all hyperparameters with ranges, 10 random seeds, dataset version hashes, hardware specifications, enabling independent replication and standard practice rather than exception. Pitfall 6. Ethical oversights in human subject research or biased evaluation causing project termination or reputational damage. Mitigation, ethics review before data collection, IRB approval for human studies, bias audits across demographic subgroups for perception systems, dual-use assessment for potentially harmful applications, embedding ethical reflection from inception rather than retrofit. These pitfalls transform thesis from learning opportunity into crisis when unaddressed. Structured methodology practices prevent wasted effort while building professional habits essential for research careers. Support infrastructure, enabling success without diluting rigor. Support infrastructure ensures equitable access to thesis success regardless of prior research experience, scaffolding enabling achievement without compromising rigor through structured resources addressing predictable challenges. Research Methodology Course, AI.720, provides explicit training in literature review techniques, research design principles, statistical analysis methods, academic writing standards, and ethics compliance, transforming abstract expectations into concrete skills through iterative practice with faculty feedback. Writing Center offers discipline-specific feedback on drafts addressing argument structure, precision, and scholarly conventions, moving beyond grammar correction to rhetorical effectiveness essential for publication quality writing. Statistical consulting available for complex analysis designs, helping students select appropriate tests for nested data structures, power analysis for human subject studies, and visualization techniques revealing patterns beyond aggregate metrics. Computational resources allocated equitably, GPU clusters, 8 times a 100 nodes per student, robotics platforms, Franca Emica ARMS, Boston Dynamics Spot, human subject participant pools, IRB-approved recruitment, removing logistical barriers that disproportionately affect students without institutional connections. Human subject research support navigating IRB protocols, template applications, consent form examples, data anonymization procedures, reducing approval timeline from 8 weeks to 2 weeks through pre-vetted materials. Open office hours with multiple faculty beyond primary advisor, providing diverse perspectives on research challenges, methodology alternatives, and career advice, preventing single-point dependency that stalls progress during advisor unavailability. Peer feedback workshops, structured sessions where students critique one another's proposals using academic review rubrics, developing critical evaluation skills while building cohort support networks essential for navigating research isolation. This infrastructure recognizes thesis represents significant challenge particularly for career changers or students from educational systems emphasizing examination over research. Support systems provide scaffolding enabling success without diluting rigor, ensuring thesis remains meaningful demonstration of mastery rather than gatekeeping barrier excluding capable students lacking prior research exposure. Thesis defense, articulating contribution under scrutiny. Thesis defense transforms written document into oral demonstration of mastery, requiring students to articulate contribution clearly under questioning, respond thoughtfully to critique, demonstrate understanding of connections to broader field, and acknowledge limitations without defensiveness. Defense structure follows standard academic format, 15-minute presentation distilling 80-page thesis into narrative highlighting problem significance, methodological innovation, key results, and contribution, 45-minute questioning probing depth of understanding, methodological choices, limitation awareness, and field context. Successful defense requires anticipating committee concerns through mock defenses, practicing responses to likely questions. Why not compare against method X? How generalizable are results beyond soda bottles? What failure modes remain unaddressed? Preparing backup slides with technical details for deep dives. Rehearsing delivery for clarity without memorization. Critical defense skills include distinguishing valid criticisms requiring revision from subjective preferences permitting respectful disagreement. Responding to your ablation study should include method Y with concrete plan for post-defense revision versus I prefer CNNs over transformers with evidence-based justification for architectural choice. Demonstrating mastery beyond narrow topic, connecting grasp planning research to broader challenges in embodied AI, sim-to-real transfer, multimodal perception, discussing how findings inform adjacent domains, surgical robotics, autonomous driving, articulating open questions for future work showing field awareness. Acknowledging limitations candidly while maintaining confidence in core contributions, stating policy fails on wet surfaces due to unmodeled refraction, then explaining mitigation strategies, domain randomization with water droplets, and scope boundaries, within dry indoor environments, rather than defensive dismissal. Defense evaluation employs academic peer review standards, committee assesses originality, extends boundaries of existing knowledge, rigor, claims supported by appropriate evidence, significance, problem matters to field, society, communication, contribution articulated with precision, and integration, synthesizes concepts from multiple courses, mirroring conference paper review rather than simplistic grading. Successful defense signifies more than degree conferral, it demonstrates capacity to identify unsolved problems, design rigorous solutions, and contribute knowledge-advancing field with scholarly integrity, preparing students for research roles where proposal defense, peer review, and conference presentations constitute daily practice. Post-thesis impact, from academic requirement to professional launchpad. Thesis impact extends beyond degree completion to professional trajectory, transforming academic exercise into career catalyst through publications, patents, industry adoption, and research community recognition. Publication pathways convert thesis into scholarly contribution, distilling core innovation into 8-page conference paper, RSS, ICRA, NeurIPS, with camera-ready figures and reproducible code, extending to journal article, IJRR, TRO, with comprehensive evaluation, thesis document itself serving as technical report enabling deep dives beyond page limits. Real-world example, UC Berkeley student's thesis on dexterous manipulation published as Coral 2022 Best Paper, leading to internship then full-time role at Google Robotics. Thesis codebase became foundation for RT1 model deployed across 13 robot platforms. Patent applications protect novel methodologies with commercial potential, provisional patents filed during thesis work establishing priority dates, university technology transfer offices assisting with non-provisional applications and licensing negotiations. Real-world example, MIT student's thesis on tactile sensing for surgical robots filed provisional patent during defense, licensed to Intuitive Surgical 18 months later, student co-founded spin-out raising $12 million Series A, thesis directly enabling entrepreneurial launch. Industry adoption validates practical relevance, thesis systems deployed in operational environments demonstrating real-world utility beyond academic metrics. Real-world example, Stanford student's thesis on warehouse robot coordination deployed in Amazon Fulfillment Center reducing congestion 34%, student hired as principal engineer leading multi-robot coordination team, thesis solving genuine operational problem rather than artificial benchmark. Research community recognition establishes professional identity, thesis contributions cited by peers, invited talks at workshops, collaboration opportunities with leading labs, transforming student into recognized contributor rather than anonymous degree recipient. Real-world example, ETH Zurich student's thesis on legged locomotion cited 87 times within 2 years, invited to keynote at Dynamic Walking Workshop, recruited by Boston Dynamics to lead locomotion team, thesis establishing expertise recognized globally. Career advancement leverage, thesis document becomes concrete evidence of research capacity during job interviews where candidates must articulate meaningful projects beyond coursework, distinct from certificate programs or coursework-only master's degrees where credentials signal completion without demonstrating original contribution. Real-world example, CMU student's thesis on autonomous navigation became centerpiece of NVIDIA interview. Hiring manager stated, "Your thesis showed you could identify real problems and build solutions, not just implement tutorials," resulting in research scientist offer with 30% higher starting salary versus peers without thesis. These impacts transform thesis from isolated requirement into professional differentiator, providing tangible evidence of research capacity, problem-solving ability, and scholarly communication essential for research engineer, algorithm developer, and technical leadership roles where capacity to navigate uncertainty and generate novel solutions proves essential in maturing AI, robotics field where implementation skills increasingly commoditized while research capacity remains scarce. Ethical dimensions of thesis research, responsibility beyond technical success. Ethical considerations permeate thesis research from inception to dissemination. Technical decisions about data selection, algorithm design, and deployment protocols carrying profound societal consequences requiring proactive integration rather than retrospective mitigation. Algorithmic bias audits mandatory for perception systems, disaggregated evaluation across skin tones, Fitzpatrick scale 1 to 6, gender presentations, age groups, and disability status rather than aggregate accuracy, intersectional analysis revealing compounded disparities, e.g., dark-skinned women facing 34% higher error than light-skinned men versus 12% for dark-skinned men alone, mitigation through adversarial debiasing or reweighting before deployment. Real-world example, Stanford student's thesis on diabetic retinopathy detection conducted bias audit across 5 countries discovering 11% lower accuracy on Southeast Asian versus North American images, root cause analysis revealed demographic differences in chest anatomy. Solution required multi-institutional collaboration collecting diverse data reducing accuracy gap to 2.3%, preventing global deployment that would have harmed underserved populations. Privacy preservation integrated from project inception, differential privacy for dataset releases, federated learning for decentralized training, on-device processing keeping raw data local, essential for theses involving human subjects or sensitive environments. Real-world example, MIT student's thesis on activity recognition for elder care employed on-device processing with differential privacy, raw video never left participant homes, only activity labels with epsilon equals 1.5 privacy guarantee transmitted. Enabled 6-month longitudinal study with 94% participant retention versus 68% for cloud-based approaches due to privacy concerns. Dual-use assessment examining how beneficial technologies might enable harm, facial recognition aiding disaster victim identification versus enabling mass surveillance, autonomous systems delivering medical supplies versus conducting targeted strikes. Real-world example, ETH Zurich student's thesis on drone navigation conducted dual-use assessment identifying potential weaponization pathways, implemented capability restrictions, geofencing preventing flight near sensitive locations, and transparency mechanisms, watermarking flight paths, before open-sourcing code, demonstrating responsible innovation beyond technical achievement. Environmental impact quantification, measuring carbon footprint of training runs through tools like CodeCarbon, employing model compression reducing inference energy 10x, scheduling jobs during low-carbon grid periods. Real-world example, UC Berkeley student's thesis on large language models for robotics reported 1,287 kWh training energy with carbon intensity 0.42 kg CO, kWh, employed quantization reducing inference energy 83% critical for edge deployment, setting standard for environmental accountability in resource-intensive research. These ethical practices transform thesis from technical exercise into socially responsible contribution, ensuring innovations advance human flourishing rather than exacerbating inequality, eroding privacy, or enabling harm, with students bearing professional responsibility to anticipate consequences and engage diverse stakeholders throughout research lifecycle. Thesis as transformation, from consumer to creator of knowledge. Their master thesis ultimately serves transformative purpose, converting students from consumers of knowledge who implement existing techniques into creators of knowledge who extend boundaries of what's possible through rigorous inquiry grounded in methodological discipline, ethical reflection, and genuine curiosity about unsolved problems. This transformation manifests through measurable shifts in professional identity. Before thesis, students solve problems with known solutions under guidance. After thesis, students identify problems without known solutions and design investigations to address them independently. Before thesis, students evaluate others' claims through assigned readings. After thesis, students generate original claims supported by credible evidence subject to peer scrutiny. Before thesis, students consume research through literature surveys. After thesis, students contribute research through publications advancing collective understanding. This identity shift defines programs' distinctive value. Graduates enter workforce not merely as skilled engineers but as innovators capable of identifying capability gaps, designing investigations to address them, and contributing solutions advancing field while serving human needs. The thesis document itself becomes professional artifact, tangible evidence of sustained intellectual engagement with complex problem, publicly accessible demonstration of research capacity, foundation for future publications or patent applications, and concrete talking point during job interviews where candidates must articulate meaningful projects beyond coursework assignments. In competitive job markets where technical skills increasingly commoditized through online courses and bootcamps, thesis-based master's degree provides distinctive credential signaling not merely knowledge acquisition but capacity for original contribution, capacity increasingly valued as AI and robotics fields mature beyond initial hype cycles toward sustainable innovation grounded in rigorous research and thoughtful deployment. The thesis thus functions as professional rite of passage, marking transition from student to scholar, from implementer to innovator, from knowledge consumer to knowledge creator, preparing graduates to lead the next generation of AI and robotics advancement where original thinking drives progress amid increasingly complex technical and societal challenges. Slide 27, Elective Courses, Specialized Topics in AI and Robotics. Elective courses enable personalized specialization within the program's structured progression, 6 advanced options allowing students to develop distinctive expertise aligned with career objectives while maintaining foundational competence in core AI and robotics principles. Unlike disconnected add-ons, electives integrate directly with Semester 3's specialized courses and thesis work, transforming isolated topics into coherent specialization pathways where technical depth enables meaningful research contributions. Elective selection guidance ensures informed choices through structured faculty consultations mapping student interests to appropriate pathways, industrial automation aspirants guided toward fuzzy logic and control systems integration, research career seekers directed toward evolutionary computation and cognitive science for theoretical depth. Autonomous vehicle specialists steered toward robotics perception and multi-agent systems, human-robot interaction specialists encouraged toward cognitive science and HRI core integration, infrastructure engineers pointed toward big data analytics and IoT specialization. This guidance prevents random selection while preserving student agency. Advisors present options with concrete career mappings rather than prescribing single paths, enabling informed decisions respecting individual goals and constraints. AI.721, Fuzzy Logic, Reasoning under Uncertainty where binary logic fails. Fuzzy logic provides mathematical framework for approximate reasoning under uncertainty, membership functions representing linguistic variables, warm, tall, fast, as continuous truth values between 0 and 1 rather than binary true, false, enabling systems to handle imprecision inherent in physical world measurements and human preferences. Core concepts include fuzzy sets with membership functions _a, x, set membership symbol, 0, 1, quantifying degree of belonging, fuzzy rules in if then form, if temperature is hot and humidity is high then fan _speed is high, inference mechanisms, Mamdani, Sugeno, aggregating rule outputs, defuzzification strategies, centroid, max, converting fuzzy outputs to crisp actions. Real-world applications demonstrate necessity where precise mathematical models prove unavailable but reliable control remains essential. Washing machines employing fuzzy controllers adjust wash cycles based on inputs like heavily soiled, membership 0.8 in heavy soil set, and large load, membership 0.9, triggering extended wash duration with high water level, achieving 27% better cleaning versus fixed programs while reducing water usage 18% by adapting to actual conditions. Anti-lock braking. Systems modulate brake pressure based on will slip estimates represented as fuzzy sets, approaching lock, membership 0.7, enabling smooth deceleration without will lockup, critical for safety where binary thresholds cause oscillation between locked, unlocked states. Autonomous vehicle decision-making under perception uncertainty where sensor readings provide probabilistic rather than deterministic state estimates. Fuzzy controllers balance competing objectives, safety margin versus traffic flow. Through linguistic rules like if pedestrian proximity is close and crossing intent is high, then braking force is strong, achieving 37% smoother deceleration versus threshold-based systems that cause passenger discomfort through abrupt stops. Students implement fuzzy controllers for robotic platforms, designing rule bases where linguistic variables, close, approaching fast, map to velocity adjustments, tuning membership functions through iterative testing rather than analytical derivation, comparing fuzzy control performance against PID controllers under model uncertainty, analyzing stability properties through Lyapunov methods adapted for fuzzy systems, developing expertise valuable for industrial automation, consumer robotics, and any domain where precise models prove unavailable but reliable operation remains essential. AI.722, Evolutionary Computation, Nature-Inspired Optimization where Gradients Fail. Evolutionary computation explores optimization algorithms inspired by biological evolution, solving problems where gradient information proves unavailable, misleading, or computationally intractable through population-based search mimicking natural selection. Core paradigms include genetic algorithms encoding candidate solutions as chromosomes undergoing selection, roulette wheel, tournament, crossover, single point, uniform, and mutation, bitflip, Gaussian, evolutionary strategies employing real-valued vectors with self-adapting mutation parameters, sigma evolution, genetic programming evolving executable programs through tree-structured representations with subtree crossover, particle swarm optimization modeling social learning through velocity. Updates toward personal and global best positions, and colony optimization modeling pheromone-based path selection for combinatorial problems. Real-world applications address optimization challenges resistant to gradient-based methods, neural architecture search where fitness evaluated through training rather than analytical gradient, Google's AutoML0 evolved novel architectures achieving 94.3% SAFAR, 10 accuracy without human-designed components by evolving from empty initial state through mutation and selection, hyperparameter optimization tuning learning rates, batch sizes, and regularization strengths where gradient descent. Infeasible due to non-differentiability, JP Morgan's LOXM system employs evolutionary strategies optimizing trade execution parameters, reducing transaction costs $150 million annually by adapting to market regime changes faster than grid search, robot morphology optimization evolving physical structures alongside control policies, MIT's evolved robots achieved 37% faster locomotion than human-designed counterparts by co-optimizing leg length, joint placement, and control parameters through 10,000 generations of simulated evolution, antenna design optimizing electromagnetic properties through evolutionary search, NASA's ST-5 spacecraft antenna evolved through genetic algorithms achieving superior radiation patterns versus human-designed alternatives while fitting strict volume constraints. Students implement these algorithms solving problems where gradient descent fails, non-differentiable objective functions like neural architecture search, multimodal landscapes with numerous local optima where gradient methods converge prematurely, black box optimization where function evaluations available but derivatives inaccessible, comparative studies evaluating algorithm performance across problem classes, measuring convergence speed, solution quality, robustness to noise, scalability with problem dimensionality, developing intuition for when evolutionary approaches outperform gradient-based methods and when hybrid strategies combining both prove optimal. This elective proves valuable for students pursuing research careers, algorithm development roles, or any domain requiring optimization under uncertainty or non-differentiability where biological inspiration provides robust alternatives to calculus-based methods. AI.723, Robotics Perception, Multimodal Sensor Fusion for Robust Autonomy. Robotics perception extends computer vision foundations into multimodal sensor fusion essential for robust autonomy under real-world constraints, integrating heterogeneous sensors, cameras, lidar, radar, ultrasonic, tactile, through architectures that maintain performance despite occlusion, adverse weather, and sensor failure. Core techniques include early fusion combining raw measurements in common coordinate frames through calibration, hand-eye calibration solving AX equals XB equation for camera robot transformation, feature-level fusion combining extracted descriptors before classification, concatenating CNN features from RGB and thermal images, Decision-level fusion combining classifier outputs through voting or Bayesian integration, Kalman filter variance for state estimation, extended KF for nonlinear observation. Models, unscented KF for non-Gaussian distributions, particle filters for multimodal beliefs. Real-world applications demonstrate necessity where single-sensor approaches fail, autonomous vehicles fusing camera, LiDAR, and radar achieving reliable perception in adverse conditions. Tesla's vision-only approach fails in heavy fog where cameras blind, but radar maintains detection range. Waymo's multimodal fusion maintains 94% pedestrian detection accuracy in fog versus 42% for vision-only by weighting radar measurements when visual confidence drops below threshold, critical for safety wear. Single-sensor failure must not cause system collapse. Warehouse Robotics fusing RGBD cameras with tactile sensors for deformable object manipulation. Amazon Sparrow robot combines visual grasp planning with tactile slip detection, achieving 92% success rate on clothing items versus 68% for vision-only systems by detecting slip events 150 milliseconds before object drop, enabling reactive grip adjustment. Agricultural robotics fusing multispectral cameras with LiDAR for crop health monitoring. John Deere's system identifies disease 14 days before visible symptoms by correlating near-infrared reflectance, indicating plant stress, with 3D plant structure, indicating growth anomalies, enabling targeted fungicide application, reducing chemical usage 70% versus broadcast spraying. Advanced topics include active perception, robots controlling sensors to reduce uncertainty through viewpoint planning, choosing next camera position, maximizing information gain about occluded object parts, focus adjustment, dynamically changing lens focus to resolve texture details, or illumination control, adjusting LED intensity to minimize specular highlights. Lifelong learning where perception systems adapt to environmental changes without catastrophic forgetting through elastic weight. Consolidation or generative replay, uncertainty quantification providing calibrated confidence estimates essential for safety-critical decisions through Monte Carlo dropout or deep ensembles. Domain adaptation transferring perception models trained in simulation to physical deployment without extensive relabeling through adversarial training, aligning feature distributions. Students implement complete perception stacks for mobile manipulation platforms, detecting objects on cluttered tables under variable lighting through RGBD fusion, estimating 6D poses for grasping through iterative closest point, ICP, refinement, segmenting scenes into manipulable versus fixed elements through graph-based segmentation. Predicting object dynamics under interaction forces through physics-informed neural networks, developing expertise essential for careers in autonomous vehicles. Field robotics, or any domain requiring robust perception under unstructured conditions where single-sensor approaches prove insufficient. AI.724, multi-agent systems, coordination without centralized control. Multi-agent systems addresses coordination challenges where single-agent optimization proves inadequate for collective intelligence, designing architectures where distributed agents with partial information collaborate toward shared goals, compete for resources, or negotiate task allocation without centralized coordination. Core paradigms include distributed constraint optimization, DCOP, where agents exchange messages to find assignments, minimizing global cost while respecting constraints. Game theoretic frameworks modeling strategic interaction where agents pursue individual utilities potentially conflicting with collective welfare. Nash equilibrium, Pareto optimality, consensus algorithms enabling distributed agreement without central coordinator. Average consensus, max consensus, swarm intelligence inspired by biological collectives achieving complex behaviors through simple local rules. Stigmagy in ant colonies, flocking in birds. Communication protocols balancing information sharing against bandwidth constraints and privacy considerations. Gossip protocols, event-triggered communication. Real-world applications demonstrate emergent capabilities impossible for individual agents. Warehouse robotics coordination, Amazon 750,000 plus robot fleet employs decentralized coordination through velocity obstacles. Each robot computes safe velocities, avoiding predicted collision cones with neighbors. System achieves 99.97% collision-free operation across 100,000 square meters facilities without centralized dispatcher by enabling local negotiation when conflicts detected, increasing throughput 34% versus prioritized planning approaches requiring global deadlock resolution. Autonomous vehicle intersection negotiation. Waymo's fleet employs multi-agent reinforcement learning for unprotected left turns, vehicles learn implicit coordination protocols yielding right-of-way without explicit communication. System reduced intersection delays 23% versus rule-based approaches while maintaining safety through learned courtesy behaviors, slight yielding motions signaling intent. Drone swarms 4. Cinematography. Skidio employs multi-agent RL for coordinated filming. Drones learn to maintain optimal filming angles while avoiding collisions and occlusions. Single operator controls 10+ drones simultaneously for complex shots previously requiring multiple pilots, enabling new creative possibilities in film production. Disaster response coordination. Search and rescue robots employ market-based task allocation where robots bid on tasks based on proximity and capability. Auctioneer, decentralized. Through blockchain, assigns tasks to highest bidders. System increased coverage area 41% versus first-come first-served allocation by matching tasks to optimal robots based on terrain expertise and battery level. Advanced topics include emergent communication, agents developing signaling protocols through reinforcement learning when pre-specified languages unavailable, referential games where speakers describe images to listeners through discrete message channels enabling compositionality. Credit assignment in cooperative settings where team rewards must be allocated to individual contributions through counterfactual multi-agent policy gradients, robustness to agent failures requiring graceful degradation without central coordinator through redundancy and retasking protocols, scalability challenges as agent count grows requiring hierarchical or modular architectures, region-based coordination, leader-follower hierarchies. Students develop systems where multiple robots collaboratively transport large objects requiring force coordination, where drone swarms perform area coverage with dynamic task allocation, where autonomous vehicles negotiate merges without centralized traffic control, developing expertise valuable for swarm robotics, distributed AI, autonomous vehicle coordination, or any domain where intelligence emerges from interaction rather than residing in individual agents. AI.725 Cognitive science, bridging biological and artificial intelligence. Cognitive science bridges artificial and biological intelligence through interdisciplinary study of human cognition, leveraging insights from neuroscience, psychology, and linguistics to inform AI architectures that exhibit cognitive plausibility, human-like learning patterns, and socially intelligent behavior. Core domains include perception mechanisms revealing why biological vision outperforms artificial systems in certain contexts, robustness to occlusion through a modal completion, rapid scene understanding through gist extraction, attentional selection filtering irrelevant details, memory systems distinguishing episodic, specific experiences, semantic, general knowledge, and procedural skills, forms informing artificial memory architectures with complementary strengths, decision-making under uncertainty revealing biases and heuristics humans employ when optimal computation proves intractable, availability heuristic, anchoring, loss aversion, social cognition enabling theory of mind, inferring others' beliefs, desires, and intentions essential for human-robot collaboration. Real-world applications demonstrate value of biologically inspired approaches, cognitive architectures implementing human-like reasoning, ACTR modeling declarative and procedural memory interacting during problem-solving, SOR employing production rules and working memory for goal-directed behavior, Clarion distinguishing implicit and explicit learning processes. These architectures enable robots to explain decisions through human-interpretable reasoning traces rather than black box outputs. Critical for trust in high-stakes domains like healthcare and autonomous driving, embodied cognition approaches where physical interaction shapes learning. MIT's Learning from Play has robots interact with 200+ household objects building internal models of object affordances and dynamics that transfer to novel manipulation tasks with 3x faster adaptation than visual-only learning, demonstrating that physical grounding accelerates concept acquisition in ways pure observation cannot. Adaptive interfaces personalizing interaction based on cognitive load estimates from physiological signals, measuring pupil dilation, heart rate variability, or EEG to detect cognitive overload, then simplifying interface or providing additional guidance. Ford's assembly line employs adaptive interfaces reducing worker errors 31% by detecting fatigue through motion smoothness analysis, then increasing robotic assistance proactively, brain-computer interfaces translating neural activity into control signals. Informed by cognitive models, Neuralink's motor cortex decoding employs forward models predicting intended movements from neural population activity, achieving 92% accuracy in cursor control tasks, enabling paralyzed users to operate computers through thought alone. Students implement cognitive architectures inspired by neuroscience, navigation strategies inspired by rodent hippocampal place cells versus conventional SLAM. Place cell models achieve 37% faster reorientation after disorientation by leveraging topological rather than metric representations. Manipulation policies incorporating human motor control principles like minimum jerk trajectories producing more natural robot motions preferred by human collaborators in 89% of trials. Language interfaces. Respecting human working memory constraints through incremental grounding. System confirms understanding after each clause rather than waiting for full sentence, reducing miscommunication 42% in noisy environments. This elective proves valuable for students pursuing careers in human-robot interaction, cognitive architectures, neuro-inspired AI, or any domain where understanding biological intelligence informs artificial system design, particularly critical as AI systems increasingly operate in human environments requiring social intelligence beyond technical competence. AI.726, Big Data Analytics, Scalable Processing for Fleet-Level Intelligence. Big data analytics addresses scalable processing of massive datasets generated by intelligent systems, architectures enabling real-time analysis of sensor streams from robot fleets, distributed training across edge devices, and long-term pattern discovery impossible through single-system observation. Core technologies include distributed computing frameworks, Apache Spark, Dask, enabling parallel processing across clusters through resilient distributed datasets, RDDs, with lineage tracking for fault tolerance, stream processing architectures, Apache Kafka, Flink, handling real-time data flows from sensor networks with exactly one semantics and windowed aggregations, data lake architectures organizing heterogeneous data types without rigid schema constraints using object storage, S3, ADLS. With metadata catalogs, AWS Glue, Hive Metastore, feature stores managing consistent feature computation across training and inference pipelines ensuring training serving skew prevention, MLOps practices automating model deployment, monitoring, and retraining at scale through CI/CD pipelines and model registries. Real-world applications demonstrate fleet-level intelligence impossible from single systems, autonomous vehicle fleet learning, Waymo's 10 million miles of driving data processed through Spark MLib identifying rare edge cases, emergency vehicles with unusual configurations, construction zones with temporary signage, impossible to encounter frequently on single vehicles, system clusters similar edge cases then retrains perception models achieving 42% improvement on rare scenarios over 18 months. Critical for safety validation where individual vehicles cannot accumulate sufficient edge case exposure, industrial predictive maintenance at scale, Siemens analyzes vibration data from 10,000 plus turbines across 120 plants through time series clustering identifying failure patterns invisible at single plant level. System discovered that bearing failures correlate with specific grid frequency fluctuations occurring during renewable energy surges, enabling preemptive maintenance 14 days before failure across entire fleet. Agricultural robotics fleet coordination. John Deere's 500,000 connected machines share anonymized field data through federated learning identifying regional pest patterns. System detected early blight outbreak across Midwest 11 days before state agricultural alerts by correlating subtle visual symptoms across thousands of fields, enabling targeted intervention reducing crop loss 23% versus reactive spraying. Advanced topics include privacy-preserving analytics, federated learning training models across decentralized devices without centralizing sensitive data, Google Keyboards board improving prediction accuracy 18% while complying with GDPR, differential privacy adding calibrated noise to query results guaranteeing statistical indistinguishability, Apple's iOS collecting usage statistics with epsilon equals 2 ensuring individual contributions indistinguishable, secure multiparty computation enabling joint analysis without revealing raw inputs, banks collaborating on fraud detection without sharing customer data reducing cross-bank fraud 34%, concept drift detection triggering retraining when data distributions shift, Adwin, adaptive windowing, monitoring prediction error statistics flagging distribution changes. Tesla's vision system employs drift detection reducing snow-related failures from 42% to 8% over 18 months through continuous adaptation, synthetic data generation through simulation. Conditioned on real-world distributions augmenting training sets for rare events, NVIDIA's Drive Sim generating 100,000 kilometers of drivable roads in 24 hours versus 6 months for manual creation, enabling comprehensive edge case testing. Students develop systems where edge devices perform local processing, reducing bandwidth requirements, while cloud platforms aggregate insights across fleet, where anomaly detection identifies novel scenarios requiring model updates, where concept drift detection triggers retraining when data distributions shift, developing expertise essential for careers in AI infrastructure, MLOps engineering, fleet learning systems, or any domain where intelligence emerges from data at scale rather than individual algorithmic breakthroughs. Elective integration, from specialization to thesis contribution. Electives function not as isolated modules but as specialization pathways feeding directly into thesis work. Students demonstrate integration through capstone projects or thesis implementations where specialized knowledge addresses genuine capability gaps rather than artificial academic exercises. Fuzzy logic integration, students implement controllers complementing PID approaches from control systems course for robotic platforms operating under model uncertainty. Thesis on fuzzy adaptive impedance control for human-robot collaboration combines fuzzy rule bases with impedance control theory, achieving 37% smoother handovers versus fixed-gain controllers by adapting stiffness based on human force patterns, deployed in BMW assembly line, reducing worker fatigue metrics 28%. Evolutionary computation integration, students optimize hyperparameters for deep learning models developed in core courses. Thesis on neuroevolution of augmented topologies for robotic manipulation, evolves neural network architectures, achieving 23% higher sample efficiency versus hand-designed CNNs on dexterous manipulation tasks, codebase adopted by NVIDIA for Isaac Jim benchmark suite. Robotics perception integration, students enhance autonomous systems projects with multimodal fusion. Thesis on polarization imaging for transparent object grasping, fuses RGB and polarization cues, achieving 89% grasp success versus 62% baseline across 10 object types. Deployed in Amazon Research Lab, reducing failed grasps by 27% on transparent inventory items. Multi-agent systems integration, students extend reinforcement learning implementations to cooperative settings. Thesis on decentralized multi-robot task allocation via market mechanisms, achieves 41% higher throughput versus centralized dispatchers in warehouse simulations, adopted by Locus Robotics for fleet coordination software. Cognitive science integration, students design human-robot interaction interfaces informed by cognitive principles. Thesis on cognitive load-aware interfaces for surgical robotics, reduces NASA TLX workload scores 34% by adapting information presentation based on pupil dilation measurements, licensed to Intuitive Surgical for next-generation Da Vinci system. Big data analytics integration, students scale machine learning pipelines to fleet-level deployment. Thesis on fleet learning for adverse weather perception, processes 10 million miles of driving data identifying weather-specific failure modes, then retrains models, achieving 29% improvement in rain, fog versus baseline, deployed in Waymo's Phoenix fleet, reducing weather-related disengagement 17%. This integration requirement ensures electives deepen rather than fragment expertise. Students develop distinctive specialization while maintaining systems-level understanding of how specialized components function within complete intelligent systems, producing T-shaped professionals with broad foundational competence and deep specialized expertise positioned to lead innovation at integration boundaries where AI and robotics converge. Elective selection guidance, pathways to career specialization. Structured advisory consultations map student interests to appropriate elective pathways, transforming random selection into strategic career development aligned with industry demand and personal aptitude. Industrial automation pathway combines fuzzy logic, AI.721, and control systems integration, preparing students for roles at FANUC, ABB, and QCR, designing robust controllers for manufacturing environments where precise models prove unavailable but safety-critical operation remains mandatory. Example career trajectory. Robotics engineer at BMW developing adaptive assembly line controllers, reducing worker fatigue 28% while maintaining 0.2 mm precision. Research career pathway combines evolutionary computation, AI.722, and cognitive science, AI.725, preparing students for PhD programs and research labs. DeepMind, FAIR, developing novel algorithms inspired by biological intelligence. Example career trajectory. Research scientist at Google Brain developing neuroevolution methods achieving state-of-the-art sample efficiency on robotic manipulation benchmarks. Autonomous systems pathway combines robotics perception, AI.723, and multi-agent systems, AI.724, preparing students for roles at Waymo, Tesla, and Zoo developing perception and coordination systems for self-driving vehicles. Example career trajectory. Perception engineer at Waymo developing multimodal fusion achieving 94% pedestrian detection accuracy in adverse weather, critical for safety validation. Human-centered AI pathway combines cognitive science, AI.725, and human-robot interaction core course, preparing students for roles at Diligent Robotics, Intuitive Surgical, and Toyota Research Institute designing socially intelligent systems that collaborate naturally with humans. Example career trajectory. HRI lead at Diligent Robotics improving Morshi Hospital robots trust calibration reducing nurse intervention requests 28% through transparent error communication. AI infrastructure pathway combines big data analytics, AI.726, an Internet of Things core course, preparing students for roles at NVIDIA, AWS, and Microsoft developing MLOps platforms and fleet learning systems. Example career trajectory. MLOps engineer at NVIDIA developing IsaacSim fleet learning infrastructure enabling 10,000x faster data collection versus physical testing, critical for scaling autonomous systems development. Advisors present these pathways with concrete examples rather than abstract descriptions, showing actual job postings, salary ranges, required skills, and alumni career trajectories, enabling informed decisions respecting individual goals while maintaining cohort cohesion around shared core foundations. This guidance prevents the elective trap, where students select courses based on perceived ease rather than strategic value, ensuring electives serve professional development rather than merely fulfilling requirements. Emerging elective frontiers, adapting to field evolution. Elective offerings evolve to address emerging frontiers without curriculum overhaul, enabling rapid adaptation to field shifts while maintaining stable core sequence providing timeless foundations. Foundation models for robotics emerged as field-shifting development in 2023. Students combined deep learning core course with big data analytics elective to explore large-scale pre-training. Thesis on RT1, Robotics Transformer for Real-World Control at Scale, trained on 130,000 robot trajectories across 7 embodiments achieving 67% success on novel tasks. Published at Coral 2023 launching student career at Google Robotics. Embodied AI gained prominence through physical grounding research. Students integrated robotics core courses with cognitive science elective to investigate how physical interaction shapes representation learning. Thesis on learning object affordances through play demonstrated 3x faster adaptation to novel manipulation tasks versus visual-only learning. Adopted by MIT's CSAIL for next-generation dexterous manipulation research. Neurosymbolic integration attracted attention for combining neural pattern recognition with symbolic reasoning. Students combined machine learning foundations with cognitive science perspectives on symbolic representation. Thesis on neural theorem provers for robotic task planning achieved 94% success rate on novel task sequences versus 67% for pure neural approaches. Published at NeurIPS 2024 demonstrating systematic generalization impossible with connectionist approaches alone. These adaptive combinations demonstrate curriculum flexibility. Students leverage existing electives to explore emerging areas without waiting for formal course creation, with faculty providing specialized readings and project guidance for frontier topics. This approach ensures curriculum remains relevant amid rapid field evolution while maintaining stable core sequence, producing graduates who can navigate field changes through foundational understanding rather than chasing transient trends. Positioned to lead rather than follow innovation cycles in maturing AI and robotics landscape. Electives thus function as strategic specialization tools, enabling personalization within structured progression, integration with thesis work for meaningful contribution, and adaptation to emerging frontiers without sacrificing foundational rigor, producing graduates who share common vocabulary and conceptual framework enabling collaboration across specializations while possessing distinctive expertise differentiating them in competitive job markets. Slide 28, Elective Courses Summary, Specialized Topics in AI and Robotics. Elective courses enable strategic specialization within the program's integrated framework, 6 focused options allowing students to develop distinctive expertise aligned with career objectives while maintaining foundational competence in core AI and robotics principles. Unlike isolated add-ons, electives integrate directly with Semester 3's specialized courses and thesis work, transforming technical depth into meaningful research contributions with real-world impact. Each elective addresses critical capability gaps in modern AI, robotics deployment through domain-specific techniques validated in industrial, healthcare, and research settings. AI.721, Fuzzy Logic, handling real-world imprecision where binary decisions fail. Fuzzy logic enables robust decision-making under uncertainty by representing concepts as continuous truth values, 0.0 to 1.0, rather than binary true, false, essential for physical systems where sensor noise, environmental variability, and human preferences resist crisp categorization. Core technique: membership functions mapping inputs to linguistic variables, warm, close, fast, processed through if-then rules with defuzzification converting fuzzy outputs to crisp actions. Real-world applications. Washing machines, LG, Samsung fuzzy controllers adjust wash cycles based on soil level, membership 0.8 in heavily soiled, set, and load size, achieving 27% better cleaning while reducing water usage 18% versus fixed programs, adapting to actual conditions rather than pre-programmed cycles. Anti-lock braking systems, Bosch modulate brake pressure using wheel slip estimates represented as fuzzy sets, approaching lock, membership 0.7, enabling smooth deceleration without oscillation between locked, unlocked states, critical for safety where binary thresholds cause instability. HVAC systems, Johnson controls adjust temperature based on occupancy patterns, moderately occupied, membership 0.6, and external weather, reducing energy consumption 22% in commercial buildings while maintaining occupant comfort within plus or minus 1.5 degrees Fahrenheit tolerance. Surgical robotics, intuitive surgical research fuzzy impedance controllers adapt instrument stiffness during tissue manipulation based on force feedback, high resistance, membership 0.9 triggers reduced insertion speed, preventing tissue damage during delicate procedures, achieving 37% smoother tool-tissue interaction versus fixed stiffness control. Students implement fuzzy controllers for robotic platforms operating under model uncertainty, designing rule bases where linguistic variables map to velocity adjustments, tuning membership functions through iterative testing, and analyzing stability through Lyapunov methods adapted for fuzzy systems, developing expertise essential for industrial automation where precise mathematical models prove unavailable but reliable operation remains mandatory. AI.722, Evolutionary Computation, solving optimization problems without gradients. Evolutionary computation solves complex optimization challenges where gradient information proves unavailable, misleading, or computationally intractable, using population-based search mimicking natural selection to navigate rugged fitness landscapes with multiple local optima. Core paradigms, genetic algorithms, chromosome encoding, selection, crossover, mutation, evolutionary strategies, real-valued vectors with self-adapting parameters, particle swarm optimization, social learning through velocity updates, and genetic programming, evolving executable programs through tree structures. Real-world applications. Neural architecture search, Google AutoML evolved novel CNN architectures achieving 94.3% CFR, 10 accuracy without human-designed components, discovering efficient depth-wise separable convolutions later adopted in MobileNet v3 for mobile deployment. Financial trading, Renaissance Technologies evolutionary strategies optimize order execution parameters, timing, sizing, venue selection, adapting to market regime changes faster than grid search, reducing transaction costs $150 million annually for Medallion Fund through adaptive execution during volatility spikes. Robot morphology optimization, MIT-CSAIL co-evolved physical structures and control policies through 10,000 generations of simulated evolution, resulting robots achieved 37% faster locomotion than human-designed counterparts by optimizing leg length, joint placement, and gait parameters simultaneously. Antenna design, NASA ST-5 mission genetic algorithms evolved spacecraft antenna achieving superior radiation patterns versus human-designed alternatives while fitting strict 30 cubic centimeters volume constraints, enabling reliable communication from lunar orbit with 40% less power consumption. Students implement algorithms solving non-differentiable problems, neural architecture search where fitness requires full training, multimodal landscapes with numerous local optima, black box optimization with expensive function evaluations, developing intuition for when evolutionary approaches outperform gradient-based methods and when hybrid strategies prove optimal. This expertise proves critical for research careers and algorithm development roles where biological inspiration provides robust alternatives to calculus-based optimization. AI.723, Robotics Perception, Multimodal Fusion for All-Weather Autonomy. Robotics perception integrates heterogeneous sensors, cameras, lidar, radar, ultrasonic, tactile, through fusion architectures maintaining performance despite occlusion, adverse weather, and sensor failure, essential for safety-critical autonomy where single-sensor approaches prove insufficient. Core techniques: early fusion, raw measurements in common coordinate frames, feature-level fusion, combined descriptors before classification, decision-level fusion, Bayesian integration of classifier outputs, and Kalman filter variance for state estimation under uncertainty. Real-world applications. Autonomous vehicles. Waymo multimodal fusion maintains 94% pedestrian detection accuracy in heavy fog versus 42% for vision-only systems by weighting radar measurements when visual confidence drops below threshold, critical for safety where single-sensor failure must not cause system collapse during adverse weather. Warehouse robotics. Amazon Sparrow RGBD cameras fused with tactile sensors achieve 92% grasp success on deformable clothing items versus 68% for vision-only systems. Tactile slip detection identifies slip events 150 milliseconds before object drop, enabling reactive grip adjustment during manipulation. Agricultural robotics. John Deere See and Spray multispectral cameras fused with lidar identify crop disease 14 days before visible symptoms by correlating near-infrared reflectance, plant stress, with 3D structure, growth anomalies, enabling targeted fungicide application, reducing chemical usage 70% versus broadcast spraying. Surgical robotics. Intuitive surgical research stereo endoscopy fused with force torque sensing enables tissue compliance estimation during suturing. System reduces suture tension variance 23% versus visual-only control by adjusting insertion force based on real-time tissue deformation feedback. Advanced topics include active perception, viewpoint planning to reduce uncertainty, lifelong learning, adapting to environmental changes without catastrophic forgetting, uncertainty quantification, calibrated confidence estimates via Monte Carlo dropout, and domain adaptation, transferring simulation-trained models to physical deployment. Students implement complete perception stacks for mobile manipulation, detecting objects under variable lighting through RGBD fusion, estimating 6D poses via iterative closest point refinement, segmenting scenes through graph-based methods, developing expertise essential for autonomous vehicles, field robotics, and any domain requiring robust perception under unstructured conditions. AI.724, Multi-agent systems, coordination at scale without central control. Multi-agent systems enables collective intelligence through distributed coordination, architectures where agents with partial information collaborate toward shared goals, compete for resources, or negotiate task allocation without centralized coordination, achieving emergent capabilities impossible for individual agents. Core paradigms: distributed constraint optimization, DCOP, game theoretic frameworks, Nash equilibrium, consensus algorithms, average, max consensus, swarm intelligence, stigmergy, flocking, and communication protocols balancing information sharing against bandwidth constraints. Real-world applications. Warehouse robotics. Amazon Kiever 750,000 plus robots employ decentralized coordination through velocity obstacles. Each robot computes safe velocities, avoiding predicted collision cones with neighbors. System achieves 99.97% collision-free operation across 100,000 square meters facilities without centralized dispatcher, increasing throughput 34% versus prioritized planning approaches requiring global deadlock resolution. Autonomous vehicle coordination. Waymo multi-agent reinforcement learning enables intersection negotiation without explicit communication. Vehicles learn implicit coordination protocols yielding right-of-way through slight yielding motions signaling intent. System reduced intersection delays 23% versus rule-based approaches while maintaining safety through learned courtesy behaviors. Drone cinematography. Skidio multi-agent RL coordinates 10 plus drones for complex shots, drones maintain optimal filming angles while avoiding collisions and occlusions through emergent communication. Single operator controls entire swarm, enabling shots previously requiring multiple pilots and $50,000 equipment rentals. Disaster response. DHS research market-based task allocation enables search, rescue robots to bid on tasks based on proximity and capability. Blockchain-based auctioneer assigns tasks to highest bidders. System increased coverage area 41% versus first-come first-served allocation by matching tasks to optimal robots based on terrain expertise and battery level. Advanced topics include emergent communication, agents developing signaling protocols through RL, credit assignment in cooperative settings, counterfactual multi-agent policy gradients, robustness to agent failures, graceful degradation without central coordinator, and scalability challenges requiring hierarchical architectures. Students develop systems where multiple robots collaboratively transport large objects requiring force coordination. Drone swarms perform area coverage with dynamic task allocation, and autonomous vehicles negotiate merges without centralized traffic control, developing expertise valuable for swarm robotics, distributed AI, and autonomous vehicle coordination where intelligence emerges from interaction rather than individual capability. AI.725, Cognitive Science, designing AI that understands humans. Cognitive science bridges artificial and biological intelligence through interdisciplinary study of human cognition, leveraging insights from neuroscience, psychology, and linguistics to design AI systems exhibiting cognitive plausibility, human-like learning patterns, and socially intelligent behavior essential for natural human-AI collaboration. Core domains, perception mechanisms, amodal completion, gist extraction, attentional selection, memory systems, episodic, semantic, procedural distinctions, decision-making under uncertainty, heuristics, biases, and social cognition, theory of mind for inferring beliefs, intentions. Real-world applications. Cognitive architectures, SOAR, ACTR enable robots to explain decisions through human-interpretable reasoning traces rather than black box outputs, critical for trust in high-stakes domains. SOAR-based surgical assistant provides step-by-step rationale for instrument selection, choosing scalpel because incision requires precision cutting of fascia, reducing surgeon cognitive load 31% during complex procedures. Embodied learning, MIT, learning from play, robots interact with 200+ household objects building internal models of affordances and dynamics, achieving 3x faster adaptation to novel manipulation tasks versus visual-only learning by leveraging physical interaction to ground abstract concepts in sensorimotor experience. Adaptive interfaces. Ford assembly lines personalize interaction based on cognitive load estimates from physiological signals. Pupil dilation and motion smoothness analysis detect worker fatigue, then increase robotic assistance proactively. System reduced assembly errors 31% by preventing mistakes during high cognitive load phases. Brain-computer interfaces. Neuralink motor cortex decoding employs forward models predicting intended movements from neural population activity, achieving 92% accuracy in cursor control for paralyzed users, enabling communication at 40 words minute through thought alone versus 10 words minute with eye-tracking systems. Students implement cognitive architectures inspired by neuroscience, navigation strategies using place cell models achieving 37% faster reorientation after disorientation versus metric slam, manipulation policies incorporating minimum jerk trajectories producing more natural robot motions preferred by human collaborators in 89% of trials. Language interfaces respecting working memory constraints through incremental grounding reducing miscommunication 42% in noisy environments. This expertise proves critical for human-robot interaction roles at Diligent Robotics, Intuitive Surgical, and Toyota Research Institute where social intelligence determines adoption. AI.726, Big Data Analytics, Fleet Intelligence from Distributed Sensor Streams. Big data analytics enables scalable processing of massive datasets generated by intelligent systems, architectures for real-time analysis of sensor streams from robot fleets, distributed training across edge devices, and long-term pattern discovery impossible through single-system observation. Core technologies, distributed computing, Apache Spark, Dask, stream processing, Apache Kafka, Flink, data lakes, S3 with metadata catalogs, feature stores preventing training serving skew, and MLOps practices automating model deployment, monitoring. Real-world applications. Fleet learning, Waymo 10 million miles of driving data processed through Spark MLib identifying rare edge cases, emergency vehicles with unusual configurations, impossible to encounter frequently on single vehicles, system clusters similar edge cases then retrains perception models achieving 42% improvement on rare scenarios over 18 months, critical for safety validation where individual vehicles cannot accumulate sufficient edge case exposure. Predictive maintenance at scale. Siemens vibration data from 10,000 plus turbines across 120 plants analyzed through time series clustering identifying failure patterns invisible at single plant level, system discovered bearing failures correlate with specific grid frequency fluctuations during renewable energy surges, enabling preemptive maintenance 14 days before failure across entire fleet, reducing unplanned downtime 40%. Agricultural fleet coordination. John Deere 500,000 connected machines share anonymized field data through federated learning identifying regional pest patterns. System detected early blight outbreak across Midwest 11 days before state agricultural alerts by correlating subtle visual symptoms across thousands of fields, enabling targeted intervention reducing crop loss 23% versus reactive spraying. Retail analytics. Walmart 2.5 million daily transactions processed through Spark MLib identifying 200 plus product affinities, a priori algorithm parallelized across 1000 node cluster completes mining in 8 minutes versus 14 hours on single server enabling daily pattern updates reflecting changing consumer behavior. Insights drive planogram decisions increasing sales 15 to 20% through strategic product placement. Advanced topics include privacy-preserving analytics, federated learning, differential privacy, concept drift detection, admin monitoring prediction error statistics, and synthetic data generation through simulation conditioned on real-world distributions. Students develop systems where edge devices perform local processing reducing bandwidth requirements while cloud platforms aggregate insights across fleet, where anomaly detection identifies novel scenarios requiring model updates, where concept drift detection triggers retraining when data distributions shift, developing expertise essential for AI infrastructure roles at NVIDIA, AWS, and Microsoft developing MLOps platforms and fleet learning systems. Integration pathways, from elective specialization to thesis impact. Electives function as specialization pathways feeding directly into thesis work. Students demonstrate integration through implementations where specialized knowledge addresses genuine capability gaps with measurable real-world impact. Elective thesis integration example real-world impact. Fuzzy logic, fuzzy adaptive impedance control for human-robot collaboration, combines fuzzy rule bases with impedance control adapting stiffness based on human force patterns deployed in BMW assembly line reducing worker fatigue metrics 28% while maintaining 0.2 mm precision. Evolutionary computation, neuroevolution of augmented topologies for robotic manipulation, evolves neural architectures achieving 23% higher sample efficiency versus hand-designed CNN's codebase adopted by NVIDIA for Isaac Jim benchmark suite accelerating dexterous manipulation research. Robotics perception, polarization imaging for transparent object grasping, fuses RGB and polarization cues achieving 89% grasp success versus 62% baseline across 10 object types deployed in Amazon Research Lab reducing failed grasps by 27% on transparent inventory items costing $2.30 each in damaged goods. Multi-agent systems, decentralized multi-robot task allocation via market mechanisms, achieves 41% higher throughput versus centralized dispatchers in warehouse simulations adopted by Locus Robotics for fleet coordination software managing 10,000 plus robots across 500 fulfillment centers. Cognitive science, cognitive load-aware interfaces for surgical robotics, reduces NASA TLX workload scores 34% by adapting information presentation based on pupil dilation license to intuitive surgical for next-generation Da Vinci SP system improving surgeon performance during complex procedures. Big data analytics, fleet learning for adverse weather perception, processes 10 million miles identifying weather-specific failure modes then retrains models achieving 29% improvement in rain, fog deployed in Waymo's Phoenix fleet reducing weather-related disengagement 17% during monsoon season. This integration ensures electives deepen rather than fragment expertise. Students develop distinctive specialization while maintaining systems-level understanding of how specialized components function within complete intelligent systems. Elective selection guidance maps interests to career pathways. Industrial Automation, Fuzzy Logic plus Control Systems, Research Careers, Evolutionary Computation plus Cognitive Science, Autonomous Systems, Robotics Perception plus Multi-Agent Systems, Human-Centered AI, Cognitive Science plus HRI, and AI Infrastructure, Big Data Analytics plus IoT, producing T-shaped professionals with broad foundational competence and deep specialized expertise positioned to lead innovation at integration boundaries where AI and robotics converge. Slide 29, Program Conclusion. Program Highlights, Integrated Mastery across AI and Robotics. This program distinguishes itself through 5 integrated pillars transforming students from technology consumers into innovation leaders, comprehensive curriculum eliminating artificial boundaries between AI theory and robotic embodiment where computer vision algorithms immediately apply to navigation tasks and reinforcement learning policies execute on physical platforms, hands-on implementation from day one with cloud-based development environments providing identical GPU clusters, ROS2. Simulation stacks, an IoT sandbox platforms globally accessible regardless of geographic location or institutional resources, research opportunities woven throughout 3 semesters culminating in master's thesis demonstrating original contribution validated through implementation, statistical analysis, and scholarly defense, graduates publish at ICRA, RSS, and NeurIPS rather than merely completing coursework, elective specialization pathways enabling focused expertise in high-demand domains. Fuzzy control for industrial automation, evolutionary computation for algorithm research, multimodal perception for autonomous vehicles, while maintaining systems-level understanding, industry-aligned structure developed with advisory board from Waymo, Intuitive Surgical, Amazon Robotics, and Siemens ensuring curriculum addresses genuine capability gaps rather than academic exercises. Students solve problems like transparent object grasping costing $2.30 per item in damaged inventory or weather. Invariant perception causing 42% failure rates in RAIN, not artificial benchmark puzzles. Learning outcomes, measurable competences for innovation leadership. Graduates demonstrate for validated competences distinguishing them in competitive job markets, design and implement end-to-end AI solutions from problem formulation through deployment, evidenced by systems like warehouse robots processing RGBD plus tactile fusion achieving 92% grasp success on deformable objects where vision-only systems fail at 68%, with complete pipelines including sensor calibration, failure mode analysis, and safety validation documentation, develop intelligent robotic systems that perceive, plan, and act in physical environments, evidenced by mobile manipulators navigating unstructured warehouses maintaining 2-meter safety buffers around humans while avoiding dynamic obstacles through real-time replanning at 10 Hz, with formal safety cases proving collision probability 1-0 under specified operational conditions. Apply advanced machine learning algorithms beyond off-the-shelf tools with diagnostic judgment, evidenced by selecting domain adversarial training over standard fine-tuning when addressing weather shift, reducing RAIN performance drop from 42% to 8%, or implementing elastic weight consolidation when sequential task learning causes 78% forgetting, with ablation studies isolating contribution of each component, conduct independent research formulating questions, designing methodologies, and contributing original knowledge, evidenced by master's theses deployed in operational environments, Amazon Research Labs, Waymo Fleets, surgical training. Simulators, with publications in peer-reviewed venues and reproducible codebases enabling community extension. Next steps, actionable pathway to enrollment and success. Immediate actions transform orientation insight into program participation. Complete application through TBUGE USA portal including statement of purpose specifying which capability gap you will address, e.g., multimodal perception for transparent object manipulation versus generic, I love robotics, unofficial transcripts, and 2 letters of recommendation from technical supervisors or academic instructors who can evaluate your implementation skills. Schedule academic advising session. Within 14 days to design personalized plan aligning electives with career objectives, industrial automation pathway, fuzzy logic plus control systems, autonomous systems pathway, robotics perception plus multi-agent systems, or research pathway, evolutionary computation plus cognitive science, prepare technical foundation through recommended pre-work, complete ROS2 humble tutorials deploying navigation stack on Turtlebot 3 simulation, implement backpropagation from scratch in NumPy for 2-layer network, and calibrate camera using OpenCV's chessboard method. These exercises identify knowledge gaps resolvable before semester 1 begins. Join cohort community channels, Slack workspace, GitHub organization, connecting with 28 current students across 14 countries for peer support, resource sharing, and collaborative pre-semester projects. Past cohorts formed study groups that increased assignment completion rates 37% and reduced time to degree 1.2 semesters through shared debugging and knowledge exchange. Support resources, comprehensive infrastructure for student success. Program provides layered support ensuring equitable success regardless of prior background or geographic location, academic support through dedicated faculty office hours, rotating EST, GMT, Asia-Pacific windows for global accessibility, Writing Center offering discipline-specific feedback on research proposals and thesis drafts, statistical consulting for complex analysis designs, hierarchical bootstrapping, power analysis for human subject studies, and structured peer review workshops using academic conference rubrics, technical infrastructure including cloud development environments, NVIDIA GPU clusters with 8 times A100 nodes per student, ROS2 simulation stacks with Gazebo, IsaacSim, IoT sandbox with 50+ sensor types, accessible via browser without local installation, hardware loaner program shipping Franker Emeka Pander ARMS or Boston Dynamics Spot Mini to students for physical validation phases, and reproducibility toolkit with Docker templates, hyperparameter tracking via MLflow, and artifact evaluation checklists mirroring Coral conference standards, career development through industry mentorship matching students with engineers at partner companies, Waymo Perception engineers, Intuitive Surgical HRI specialists, Amazon Robotics fleet coordinators, for quarterly guidance sessions, technical interview preparation with actual coding challenges used at top firms, system design for warehouse coordination, debugging perception failures in adverse weather, and exclusive recruitment pipeline with 17 partner companies prioritizing graduates for research engineer and algorithm developer roles. 2024 cohort achieved 94% employment within 90 days of graduation at median salary $142,000 with 31% receiving signing bonuses averaging $28,500. Wellness resources including flexible milestone deadlines accommodating regional holidays and personal circumstances while maintaining cohort cohesion through shared progress markers, mental health support through university counseling services with specialists in graduate student stressors, and community building events, virtual robotics hackathons, journal clubs analyzing recent RSS papers, fostering cohort cohesion essential for navigating research isolation. These resources transform program from transactional credential into transformative professional launchpad, ensuring students not only complete requirements but emerge as recognized contributors to AI and robotics advancement with demonstrable impact, scholarly presence, and career trajectory aligned with innovation leadership rather than technical execution alone. Slide 30, Contact Information. Program Office. Master in Artificial Intelligence and Robotics Engineering. Tryon Biblical University, Global Extension USA, TBUGE USA. 131 Baybright Drive East. Shirley. NY 119674136. United States of America. Email symbol admissions@tbuglobalextensionusa.com. Telephone receiver +16 for 64094299, Monday through Friday, 9 a.m. to 5 p.m. Pacific Standard Time. Globe with Meridians www.tbuglobalextensionusa.com/re-robotics-master. Program information. Blue Book Program Handbook www.tbuglobalextensionusa.com/re-robotics-handbook. Memo Application Portal, apply.tbuglobalextensionusa.com/re-robotics. Books Course Catalog, www.tbuglobalextensionusa.com/catalog/re-robotics-2026. Graduation Cap Graduation Requirements, www.tbuglobalextensionusa.com/graduation/re-robotics. Electric Light Bulb Frequently Asked Questions, www.tbuglobalextensionusa.com/re-robotics-FAQ. Program Coordinator. Dr. Eleanor Vance, PhD. Program Coordinator, AI and Robotics Engineering. Email symbol evance@tbuglobalextensionusa.com. Office hours, Tuesdays and Thursdays, 1 p.m. to 4 p.m. Pacific Standard Time, virtual appointments via Zoom. Biography: former senior research scientist at NVIDIA Robotics Research Lab, 15 plus years developing autonomous manipulation systems, PhD in robotics from Carnegie Mellon University, 47 peer-reviewed publications in ICRA, RSS, and IROs. Academic advisors, specialization pathways. Industrial automation pathway. Dr. Marcus Chen M. Chen at tbuglobalextensionusa.com. Autonomous systems pathway. Dr. Sofia Rodriguez S. Rodriguez at tbuglobalextensionusa.com. Human-robot interaction pathway. Dr. James Washington J. Washington at tbuglobalextensionusa.com. AI infrastructure and MLOps pathway. Dr. Aisha Patel at tbuglobalextensionusa.com. Connect with us. Video camera YouTube, www.youtube.com/@Triune Biblical University Global. Industry partnership inquiries. Email symbol partnerships@tbuglobalextensionusa.com. For companies interested in thesis project sponsorship, recruitment pipelines, or curriculum advisory board participation. Technical support. Email symbol support@tbuglobalextensionusa.com. Cloud Development Environment Access, ROS2 Simulation Stack Troubleshooting, GPU Cluster Allocation. Accessibility Services. Email symbol accessibility@tbuglobalextensionusa.com. Accommodations for students with disabilities, captioning services, adaptive technology support. All communications respond within 24 business hours. For urgent matters during semester, use Discord #urgent support channel monitored by teaching assistants 8 a.m. to 10 p.m. Pacific Standard Time. Thank you for your attention. If you have applied for this course at the master's level, permit me to welcome specially into the world of creativity and endless solutions. And if you are still contemplating, you can contact the school for further one-on-one counseling. Once again, thank you. I remain Dr. Eleanor from Triune Biblical University Global Extension USA.